Well, good morning, everyone, and welcome to today's course on an introduction to drilling. Today, we've got a number of detailed presentations on drilling, which goes all the way from the physical drilling itself, all the way through drilling fluids, how to log a borehole, structural logging, downhole surveying, and the sampling of drill holes. We've got a number of speakers. Each one of them is an expert in their own right, and we thank them very much for their time and effort to be here with us today. As usual, a very special thank you to our sponsors for this event. These are our annual sponsors, without whom none of the events that we do will be possible. So thank you very much to our annual sponsors, and also a request to any of you, your companies, who might wish to sponsor in the future. Right, so we're going to start off with an introduction to drilling by Colin Rice. Now, Colin is unfortunately not able to physically be with us, so we are doing the recording.
Okay, what I've kind of briefed with today is to chat to you guys about drilling, and to kind of answer a question: what do geologists need to know about drilling? And just to give you a little bit of background, I started my career in the drilling industry in 1984. I did my degree in maths and chemistry, and I taught senior school mathematics for 8.5 years in Zimbabwe. And moved to South Africa, and I got a job as a development chemist with a mud company. We manufactured drilling fluids. So that was my introduction into the drilling industry. I won't bore you with the other detail, but through the years that I've had in the industry, a large part of the work I've done has been to kind of interact between mining companies or exploration companies and contractors. And what I found over the years was that many of the disputes or misunderstandings or conflicts that arose between contractors and mining companies arose because neither one really understood what the other one wanted. And very often you find that geos or exploration geologists, mining companies, don't understand how a contractor works. They don't really understand drilling. And so they have these misconceptions about what's possible and what they should pay for and what they shouldn't pay for. And then from the contractor side, it's exactly the same. They don't really understand what the geologist wants. Geology, a drilling exploration course is not about drilling meters. It's about producing information. And very often we lose sight of that. So this training, all of these training programs I've done over the years, and I've done, I'd love to know how many I've done, but I've done literally hundreds and hundreds of them. All of them have been aimed at trying to improve understanding of drilling technology. Because I believe the more a geo understands about drilling, the better he will be at managing a drilling project. And that's really what it's all about. And eliminating this notion that contractors and geologists are the opposite side of the fence. It's all got to be a joint effort if we're really going to achieve what we want to achieve out of an exploration project. Okay, so with that background, let's get started. We know that all geological information is founded on rocks. And the only way we can get rock samples at depth is by drilling boreholes. And so clearly, good knowledge of drilling, a good understanding of drilling principles and drilling technologies is central to a geologist, absolutely critically important for a geologist. Now, there are many different methods of drilling that we can use to produce samples, but essentially we can categorize these into two kinds. We've got drilling methods that produce chip samples, and we've got drilling methods that produce core samples. And I'm going to talk about these, a couple of these methods today. Unfortunately, in the short time we've got available, we can't go into massive detail. I'm just going to tell you enough to make you dangerous. And then if any of you want to, there's the more detailed program in September next month, where we go into a lot more detail on drilling methods and drilling technologies. But the choice of method of drilling will depend upon the stage of the project. So typically in early stage projects, you want to get just indication of what's down there. And so a chip sample will suffice, but as the program advances and it gets into a more advanced stage, you have to have core samples. So that will really direct the method of drilling that you want. So what are we going to try and do today? What do you really need to know about drilling? Over the years, I've come to believe that geos need to understand different methods of drilling and techniques, and most particularly, you need to understand the capabilities and the limitations of different methods. Very often we get involved in programs or in situations where the geo thinks you can do all of these wonderful things, which in fact you can't do. It's not possible. And so that leads to problems and disappointments. So you need to understand that. Now we're going to touch on that today, only touch on it. Then you need to understand the factors that affect sample quality. Exploration drilling is about producing representative samples safely and efficiently, and quality is critical to all of it. And very often, many of the factors or many of the incidences, if you like, of poor quality sample comes from poor understanding by the driller, and sometimes poor understanding by the mining house as well. So it's important you understand that. I call those technical aspects of drilling. Without question, anybody involved in drilling, if you work for a mining house, you better have your safety hat on, because safety is the most critical part of every exploration drilling operation. And so you need to have an understanding of the hazards associated with drilling equipment. You need to therefore understand about the controls that are put in place to control and mitigate the risk that is associated with those hazards. And then you need to know a little bit about your legal responsibilities and liability. Now, I know we've got a very diverse group. We've got people from all over Africa. But when we talk about this a little bit later on, I'm going to focus on South Africa and what we do here. We have some of the most stringent mining laws in the world. And the consequences of not complying are pretty draconian, and they're getting more and more draconian. If the government had their way, they'd put us all in jail and hang us. We need to understand what our liabilities are. So I'm going to touch on that today. Unfortunately, guys, all of this, we haven't got a lot of time, so we're going to touch on it and just give you a flavor of what it's all about. And then the third aspect of what I believe a geologist needs to know about is about economic aspects of drilling. Drilling is expensive. It's very costly. It's getting more and more costly. And one of the things that I think is one of the most common points of misunderstanding is that mining companies just don't understand how a contractor makes profit. And I'm going to show you two principles later on when we read this little section that I believe is central to a successful drilling operation. Making a profit is not a sin. Everybody's got to make a profit. We all make profits in different ways. Some people get salary, some people run businesses, but you've got to have money to do things. And the drilling contractors have got big demands on in terms of equipment and people and training and processes, and they have to make a profit. And many mining companies believe, this sounds silly, but I promise you, based on my experience, sometimes I think it's true. Many mining companies believe that their sole role in life is to put contractors out of business. And in that kind of situation, you're looking for trouble. And then lastly, the last thing we're going to touch on today is what you can do as a geologist to help a contractor to make profit. Because if he makes profit, your program will succeed. If he doesn't make a profit, I'll guarantee you, I'll give you a letter, you will fail. you will have a problem on site. So these are the three aspects that I wanted to touch on today: technical aspects, safety aspects, and some economic aspects. As I said, these are pretty lengthy presentations. We've got a relatively short period of time, and I don't want to not finish. So I'm going to scoot through this. And in previous years, we've done fairly well with time, but I certainly don't want to take up anybody else's time today. So we might scoot through some of this a bit more quickly than I want to, but let's see how much progress we can make. Okay, let's see how far we can get. All right, let's start talking about some of the technical aspects of drilling. And here I'm going to talk about what I call the components of a drilling operation. We're going to talk about the features of a drilling operation. I'm going to talk about some different rock breaking mechanisms, way in which we can make rocks fail and fragment. And then we'll talk in a little bit of detail about the more common exploration drilling methods and techniques that we use. Okay. Now, all of what we've got here, everything I'm talking about today, is contained in, to some extent, in the longer drilling methods and techniques course in September, but in a huge amount more detail. They're covered in one of our online programs, which we call Drilling Skills for Geologists. It's a very lengthy 9-10-month program that we run, an online program. And we will talk about that a little bit later. All right, drilling is a complex process. I'm going to contradict myself, because just now I'm going to tell you drilling is very simple. But it is complex, because there's many different kinds of machine that are used, many different techniques, different types of equipment, and so on. It can become very, very confusing. But in fact, if you sift all of the commonalities out of it, and if you understand those commonalities, those basic principles, then drilling is much, much easier to understand. That's what we're going to try and do in the next few minutes. Okay. We all agree that drilling is the process of making a hole in the earth. And then we want that hole to be stabilized. So either we'll put casing in the hole, or we hope that the rock that we drill, the formation we drill, is stable enough that we have the stabilized void that is left, and we call that a borehole. And there are many different ways in which we can drill boreholes. And I find with geos that very often they get very confused with the different terminologies and so on that are used when we're talking about drilling. I'm going to try and make that a bit more simple for you today, because there is a great deal of commonality between different methods of drilling. All drilling methods, doesn't matter what you're drilling or what method of drilling, there are two components that are very, very important. The bottom bit, the bottommost part of the business end of the operation is a drill bit. We'll have a drill bit at the bottom, and that will be connected to surface by a drill string. And a drill string is just a series of drill rods that are joined together. All drill rods have got box and pin connections, male and female connections, so you can screw them together. All drill rods, all they do, their sole purpose is to connect the drill bit to the drill rig. The other function is to provide torque. They allow you to put torque, in other words, rotational power, into the bit. And all drill rods are hollow. They've all got a hole in the middle. And we pump the drilling fluid through that, through the drill string, through the drill rods, comes out of the bit and flows back up the side of the hole. We'll talk about that in a minute. And the sole function of the drill bit is to fragment rockets, to make hole. That's all it's there for. So the drill bit and the drill rods are the key elements of every drilling operation. Whether you're drilling a hole in the wall or a piece of wood, or you're drilling a 4-kilometer deep gold exploration borehole, it's exactly the same principle, the same equipment that's used. Now, in every drilling operation, we have to have a drill rig. The drill string, the drill rod, is put in connection with the drill rod. It's connected to what we call the rotation head of the drill rig. We rotate it. So we start rotation on the drill rig. We rotate, and then we simultaneously apply a load to the bit, what we call bit thrust, or weight on bit, or bit load. All of these terms mean the same thing. So we rotate and we simultaneously apply a load to the bit. And the The amount of load that we apply will vary depending upon certain factors. But in all drilling operations, we have that same those same two principles. And all that varies really is the design of the bit and the design of the drill string, and obviously to some extent the design of the drill rig. But in this little summary here, these few pictures here, there are a number of different types of drill bits. So this one on the left, what I've labeled as bit A, it's what we call a drag bit. It's got tungsten carbide cutting elements. So the leading edges of those blades is tungsten carbide because it's hard and it's abrasion resistant. And that bit is used where sometimes they call it a scraper bit and a clay cutter. It's used to drill very soft, unconsolidated material. This bit at the bottom here, D, is what's called a tricone bit. And that bit makes rock by crushing. We apply very, very high weight onto that bit. We rotate slowly, but we apply very, very big loads to it. And as the bit rotates, it crushes the rock and creates a chip sample. This bit here on the bottom right, these little cutting elements on here, these little black faces you see here, is what's called polycrystalline diamond, PDC. A very, very hard substance, very efficient cutting mechanism, very efficient cutting element that's used again to drill holes in different formations. Now, all of these three bits, A and D and E, these are all what we call full face bits. In other words, when we drill with those bits, the entire volume of the rock that we drill is fragmented. So the entire volume of the rock becomes fragments and eventually becomes drill cuttings, and they are sampled. These two bits in the top, they've got a hole in the middle, and these are core bits. So these two bits, when we drill with them, we'll produce a core sample. And so really all that varies is the design of the bit, the design of the drill rods, a number of other operations around it. And that's a very important starting point for us to understand the different principles of a drilling operation. Now, it's important that as the bit advances, as we make hole, we fragment rock and we create cutting, what we call cutting. It's not called sludge. People call it sludge. And they give it all sorts of funny names. It's not. It's cuttings. It's drill cuttings that we have deliberately fragmented in order to make rock. Okay, so where were we? So we produce this drill cutting. The bit fragments rock. We have this cutting, and we've got to evacuate. We've got to clean that cutting out. If we don't clean the drill cuttings from the hole, we will not be able to drill any further. We'll get stuck. We'll have all sorts of problems. So hole cleaning becomes very, very important. And to do that, we pump the drilling fluid, what we call a flushing medium, down the middle of the drill string. It turns at the bit and flows up the annulus to surface. The gap between the borehole wall and the drill rods is called the annulus, and the drilling fluid returns to surface up the annulus. So as we produce the cutting, the drilling fluid picks up the cutting and flushes it to surface. It carries it to surface. It's then deposited in sumps or whatever the case happens to be, whatever, depends what system we are using. The important term for me is the term annulus. We use it a lot in the drilling industry. The annulus is the space between the borehole wall and the drill pipe. Very, very important. That's where the drill cutting flows to surface. Now let's look, having looked at those general principles there are 4 features. This is terribly important, guys. This is critically important. And from your assignment point of view, as Tanya pointed out there, this is critically important because this will be one of the takeaways. And just as a little rider to what Tanya said there, I'll help Tanya mark. And at the end of the course, I'll give you my bank account details. If you send me some money, then I'll give you a better mark. Okay, so bear that in mind as well. There are 4 features that are common to every drilling operation. It doesn't matter what method of drilling you're using. It doesn't matter what you're drilling, how you're drilling, where you're drilling. These 4 features are common to every single drilling operation. And if you can train yourself, whenever you go and look at a drill rig, visit a drilling operation, look for these 4 features and ask yourself, how are they done? Because different rigs do them in different ways. and different drilling methods. We do them in slightly different ways, but the same principles apply. Let's talk about them briefly. The first one is rotation. We cannot drill without rotating drill bits. We have to rotate the drill bit. And so in every drilling method, the drill rig has what we call a rotation head. The drill string, the drill rod, is connected to the rotation head, and that provides the torque, the rotary energy. It provides the rotation. So in every drilling operation, we have rotation. Now, just merely rotating the drill bit will not make hole. We have to also load the bit. We've got to put weight on the bit. We've got to push down on the bit so that it's pressed hard into the rock, and it helps the bit to cut. So we need the second feature, the second essential element of a drilling operation is weight on bit, or bit load, or bit thrust. As I said earlier, these are all synonymous terms. Now, the amount of weight that we apply, the amount of load we've got to apply will depend upon various factors. It'll depend upon the diameter of the bit, the type of bit, the hardness of the rock, a whole bunch of different factors that aren't important right now. The important thing is that we cannot drill without weight on bit. So there's two factors there, rotation, weight on bit, two key elements that are common to every drilling operation. The next important feature of every drilling operation is what we call a hoisting system. At some point in time, the drill bit is going to become dull. Dull is the term we use in the drilling industry. It's going to be finished. It won't cut anymore. The cutting elements are worn away. And that means we're going to replace the bit. So we've got to pull all the drill rods out the hole, take the bit off, put a new bit on, and go back down the hole again. And we call that process tripping or hoisting, pulling and lowering of drill rods. And that is done by the hoisting system of the drilling machine. And we can't drill if we don't have a hoisting system. I think that's pretty intuitive. So that's another key element of every drilling operation is the hoisting system. Now, obviously, as a borehole gets deeper, the hoisting system takes longer and longer and longer. It takes you longer to pull and longer to lower. So it becomes a more dominant element of time, and therefore a more dominant element of cost of drilling as holes get deeper. Now, typically holes, all drill rods that we typically drill within surface operations are either 3 meters or 6 meters long. In special circumstances, they're longer, but in exploration operations, they're either 3 or 6 meters long. And so when we pull the rods out the hole, when we are hoisting, we can either hoist 3 meter rods at a time, or we can pull multiples of 3, what we call a stand. And obviously, the longer the stand that we can pull, the more quickly we can complete that tripping cycle, that pulling and lowering cycle. And all of this is part of the economics of drilling. And so generally speaking, the deeper the hole goes, the taller the mast we will need on the drill rig to be able to enable us to efficiently pull and lower drill rods. Now, in the past, this is interesting from a safety perspective. Any of you guys who currently work on drilling projects, and if you work on mines, particularly in South Africa, in fact, not even South Africa, all over the world, there is a massive push by mining companies to automate drill string hoisting. It is literally millions and millions and millions, hundreds of millions of dollars spent every year by companies trying to automate the process. Some of them have been quite successful, some have been terribly unsuccessful. But typically, in the old days, we used to pull drill rods, we used to stack them vertically in the mast, like this, as you see in this picture on the left-hand side here. This picture was taken in the Rustenburg area. How long ago was this? It was probably back in the sort of mid-90s, I guess. It's banned now. You're not allowed to do this anymore because mining companies think it's dangerous. It's not dangerous at all. We had one fatality where the guys did something stupid. Every fatality is because someone does something stupid. Somebody didn't do what they should have done. And to cut a very long story short, the guy fell from here and he died. And overnight it was banned. So we're not allowed to do that in South Africa anymore. So what we do now, all around the world, is we stack drill rods horizontally on racks, like you see on the right-hand side here. or something similar. And it just, this is one of the things that I sometimes get very puzzled about in the drilling industry, and why I think training programs like this are so critically important. This particular drill rig here, the one on the right-hand side, I was called out to do an inspection on a rig. And this particular rig was drilling a size we call BQ. It's a 60 millimeter hole. The drill rod's a 56 outside diameter. And the drill rods weigh 8 kilograms per meter. So a meter of drill rod weighs 8 kilograms. And kind of very long story short, when I got to site, they pulled the rods. This is only some of them sitting on these racks here. But they had 16.5 tons of drill rods sitting on these little rod racks. Now, the mining company said, no, we can't stack vertically, it's too dangerous, so let's stack them horizontally. But nobody had the sense to do a calculation and to work out how heavy those rods were. So we have these tiny little rod racks here that were made of scratch steel. Don't know who welded them. And we're quite happy to put 16.5 tons of steel on these little rod racks. 16.5 tons of steel is, what is that? That's probably about the same mass as 8 or 9 small motor vehicles on these little rod racks. This is unfortunately what we typically see in the drilling industry, and why courses like this are so important, particularly the safety part of it. Now, the last feature. So we've got rotation, we've got weight on bit, and we've got a hoisting system. The last essential feature, the last critical feature that is common to every drilling operation is what I call a flushing system. Drilling involves fragmenting rock. We produce drill cuttings. We pump the drilling fluid down the drill string. It comes out of the bit, flows up the annulus, and we call that the flushing system. And that flushing system, the whole purpose of it is to keep the bit cool and to remove the drill cuttings. Later on, I know from Imdex is going to chat to you about drilling fluids. He'll talk to you about that lot in a whole bunch more detail. But the key point here, guys, is that the whole purpose of that flushing system is to clean the hole, is to remove the cuttings. And if we don't clean the cuttings, we're going to be in big, big trouble. Now, in the drilling industry, we use 2 different kinds of drilling fluid. We use water, or a water-based fluid. We add chemicals to it, or we use air. And so we've either got a water pump or we've got a compressor that produces the fluid that we pump down the drill string. So the key point here is we've got 4 elements that are common to every drilling operation. Now, what I've babbled on about here in 3.5 minutes is a very big part of these other more detailed courses we do. We talk about these features in a lot more detail. But if you look at every drilling operation you go to, whether you're drilling a blast hole on a mine, or drilling a production hole underground, or drilling a water well, or drilling an oil well, or drilling a reverse circulation hole on a mine, or drilling a diamond drill core bore hole, the same 4 features are common to all of them. And all that varies from one drilling method to another is the relationship between them. So please, that is a key takeaway, something that's really, really important to remember. Okay, rotation, weight on bit, a hoisting system, and a flushing system. All right, let's talk now about different ways that we can make rock break. We're talking now, again, guys, please remember just about the general principles of a drilling operation. We can make rock fail. We can break rock in 3 different ways. We can crush it, we can shear it, and we can abrade it. We talk very briefly about these. Okay, when we crush rock, we take a drill bit like this one on the left-hand side, which we call a tricone bit. We put it in contact with the rock, in contact with the formation being drilled, and we put huge load on it, huge amounts of load. Normally about 1.5 to 2 tons per centimeter of diameter. So we've got a 200 millimeter, 20 centimeter diameter bit. We can apply between 30 and 40 tons of load to make that bit cut. So it's the load, it's the pressure of the bit, of the cutting elements, that causes the rock to fracture and spoil and to create a cutting. So it's a crushing mechanism. So in order for these bits to make whole, we've got to have very high load. And if we don't have sufficient load to crush the rock, if we can't overcome the compressor strength of the formation we're drilling, we just won't penetrate. And so we have to have very big, heavy drill rigs when we drill with these Tricone type drill bits because of the very high bit loads that we have to apply to them. But because we've got very high load, it's not the rotational speed that makes the hole. It's the weight on bit. It's the crushing action that makes bit. And so we rotate these bits very, very slowly, 40 to 80, 100 RPM typically is the rotational speed that we'd apply to bits like this. Another way that we can crush rock, another mechanism or another technology, if you like, that we use is what is called a downhole hammer. We're going to talk about these in a little bit of detail later on. The downhole hammer essentially is a cylinder of steel, if you like. At the bottom, there's a drill bit. You see this, I'll show you some pictures just now of some more the drill bit at the bottom there. And sitting in the cylinder is a piston, and the piston basically is a piece of steel. These are all very carefully machined, but this basically a piece of steel. And we pump very high pressure compressed air down the drill string. It flows into this hammer, this downhole hammer, and as it flows through the hammer, it makes the piston reciprocate. And the piston moves up and down very, very quickly, 900 to 1200 times a minute. Very, very quickly it reciprocates. Every time it comes down, it strikes the top of the drill bit. As it hits the top of the drill bit, it transmits an energy wave through the drill bit into the rock, spalls the rock, fractures the rock, chips are created, and then that same air escapes at the bit and blows the cutting to surface. We'll talk about this in more detail just now, but that's a principle of what we call a downhole hammer. Again, it's a crushing action. If the piston doesn't hit the bit with enough force, think of a hammer hitting a nail. If it doesn't have enough force to crush the rock, we simply will not penetrate. So it's again, we make holes through a crushing action. So we've got that Tricone rotary type system. This is what we call a rotary percussion system. We have a percussive energy from the piston that's reciprocating, and at the same time, we rotate the drill string and rotate the drill bit. So those are two crushing mechanisms. The second way we can make rock fail is through what we call a shearing or a cutting action. And here we have bits with very large cutting elements. The one in top right picture, the sort of golden color bit, is what we call a drag bit. Saw a similar picture earlier. And the leading edges here, where I'm trying to point with my mouse now, those are tungsten carbide. We use tungsten carbide because it's hard and it's abrasion resistant. And the cutting action is very much like a knife sliding through butter. The bit scrapes and it shears rock as it rotates. The bit in the bottom here, this one with the green bit body, is what we call a PDC bit, or a polycrystalline diamond compact bit. Fascinating cutting materials, incredibly efficient. Polycrystalline diamond is the hardest substance known to man. It's a synthetic diamond made in a factory. Incredibly efficient as a cutting tool. I'd love to go into a lot more detail about it today, but we just don't have the time. But although these two bits look very different in their design, they cut in exactly the same way. It's a scraping or shearing action. And again, without going into too much detail, because of the cutting action, we don't need to apply as much load to this type of drill bit as we do with a Tricone bit, because of the way that because of the mechanism that the rock that the bit uses, so the mechanism by which the bit makes the rock fragment. So we typically will apply about 0.5 ton per centimeter of diameter, much less than with a Tricone bit. But because of the cutting mechanism, we rotate at a much higher RPM. And typically, the faster we rotate, the quicker we will penetrate. So we've got those two mechanisms of breaking rock. We can crush it, we can shear it. The third way that we can make rock fail, or the third way we can make hole or make rock fragment, is through abrasion or grinding. Now, we've all used sandpaper or emery paper. to sand a desk or a piece of wood or a piece of steel. And emery paper or sandpaper have got very, very small pieces of abrasive material that are bonded to the paper. And the more quickly we sand, the more quickly we make it go backwards and forwards, the more quickly we get the sanding job done. It's exactly the same principle with a diamond bit. So in a diamond bit, all diamond bits cut by abrasion. We've got these very, very hard, very small cutting elements that are set into a bit body. We put it in contact with the rock and we rotate. And generally speaking, the quicker we rotate, the more quickly we will penetrate. And the cutting mechanism is exactly the same as a piece of sandpaper or a piece of emery paper. So we have these three mechanisms by which you can make rock fail. Now, guys, I'm just keywords. We can spend a week talking about this, but we just don't have that much time today. I'm very conscious of the time. I don't want to overrun. These diamonds, if we put too much load on them, they'll fracture and they'll break, and you'll lose your cutting structure completely, and the bit will stop working. So we drill with very, very low weight on bit when we're drilling with a diamond bit. So again, please bear that in mind. Another key takeaway for your assignment with that Tanya spoke about earlier. So let's talk now about some common exploration drilling methods. This, where are we now? We're about, I wanted to give myself, sorry, bear with me, guys. I'm trying to do some timing here. Yeah, okay, we'll be fine. I'm going to talk about 3, maybe 4 common methods of drilling. Some I'm going to scoot through very, very quickly because they're important, but the other ones I'm going to spend a little bit of time on. But again, guys, please, I'm sorry. We've got very limited time, so I can only just touch on this. But if you're a geologist, you have to do some further training. So please try and attend the one in September or do one of our online programs when you have some more time. Based on those, the different ways in which we can make rock fail, we can classify drilling methods. This is also quite important to remember. Very often I get involved in discussions with mining companies and contractors, and they're using different language to describe the same thing. We're terrible with that in the drilling industry. So we call the same thing 4 different names, and it drives me dizzy. And so whenever I talk about drilling, I like to talk about a commonality of terminology. When we talk about classification of drilling methods, I like to classify drilling methods based on the hole making principle. So we could talk about percussion drilling methods, where we have a hammering action. We could talk about rotary drilling methods, where we don't have any hammering action, all we've got is rotation. And then we've got a combination of the two. We have what we call rotary percussion. So we have a rotary action, the bit's rotating, and we have a percussive action. And if we remember those 3, percussion, rotation, percussion methods, rotary methods, and percussion methods, it helps us again to try and understand what we are doing in our drilling operation. Now, I call these 3 things on the left, I call those drilling methods. And within each method, there are different techniques that we can use. And I'm going to try and illustrate that in the next couple of minutes here. In the next slides, we're going to look at. Okay. So when we're producing or when we're drilling an exploration borehole, the sole purpose is to obtain representative samples as safely and efficiently as possible. And the key here is representative sample. When we talk about representativity, we want the sample that we get, if it's a core sample, it must be totally representative of the in situ formation. And that means the depth must be correct. It's no good saying the sample came from 2,500 meters when it came from 2,400 meters. So it must totally represent the structure and the composition of the in situ rock, and it must be at the correct depth. Now, very often we have situations downhole that mitigate against that affect the sample quality. Sometimes they're geological, sometimes they're drilling practice related. But when we're drilling a chip sample, when we're using methods of drilling to produce a chip sample, those factors become even more critical because it's very, very easy to get a chip sample wrong. Core sample, you've got to be a bit of a dumber to get it wrong, but a chip sample is very easy to get wrong. So please bear that in mind when we look at these different drilling methods. Okay, I'm going to scoot through this bit because it's not that important. I was going to talk there a little bit about rotary drilling in mining, but I'm not going to talk about that. We're just going to run short of time. Let's talk about the most important exploration drilling method, and that's diamond core drilling. In diamond core drilling, we use a bit with a hole in the middle. We put it in contact with the rock, we rotate very, very fast, and we make hole through a grinding or abrasive kind of cutting action. And we produce cylindrical core samples. Having said that, I've got a piece of core in my bookshelf here behind me that I must take some photographs and I must publish something about it. It's pentagonal, absolutely amazing. It's got 5 sides. It's a coal sample produced, in fact, in South Africa. Absolutely amazing. But generally speaking, our core sample should be cylindrical. Now, when we're diamond core drilling, the bottommost part of the drill string, the bit that's at the bottom of the hole, is what we call a core barrel. And the core barrel acts as a receptacle for the core as we advance. As we advance, we produce this core sample, and as we advance, the core feeds into the core barrel. So the core barrel becomes a very, very important part of the whole diamond drilling operation. Typically, a core barrel will look like this. This is a very simple, what we call a single tube core barrel. But every core barrel, the terminology is important for you to remember, will have a drill bit. That's the bit, piece at the bottom, the bit that does the work. Behind it, we'll have a reaming shell. Then we'll have what we call an outer tube. And then we have what we call a core barrel head. And the drill string, the drill rods will screw into this core barrel head. And as the hole advances, we'll add more and more drill rods so the hole gets deeper and deeper and deeper. But in general principles, that is what every core barrel will look like. There's huge variety. They're very enormous. We'll talk a little bit about them now. But that's the essential parts of every core barrel. As we're advancing, as we're drilling, the core, as the hole gets, as the bit advances, the core feeds into the core barrel. And in this particular case, for this type of core barrel, we're pumping the drilling fluid down the drill string. It enters the core barrel. It flows over the core. It comes out at the face of the bit and then flows back up the annulus to surface, carrying the cutting back up to surface. So that's the way that the core feeds into the core barrel. It's a little bit more complicated than that, but for the time being, we'll have to just accept that's the situation. Now, core barrels vary enormously in terms of their complexity, in terms of their design, in terms of their diameter, and in terms of the diameter of core sample that you can get. And here's just a sample of some drill bits. I'm not going to name all of these because it's just not that material at this stage. But you can see the variety in terms of hole diameter, and you can see the variety in terms of the core size that we're going to get. And a geologist will select, normally in conjunction with the contractor, will select the core barrel they want you to use, that they want the contractor to use, based on the size of core sample that the geologist needs. Coal geologists need a bigger core sample than maybe a platinum geologist requires. And so you would pick the core barrel to suit the work that you're wanting to do. Now, this might be a little bit abstract for some of you if you haven't been involved in drilling operations. I'm going to go through this fairly quickly. Again, as I say, in the other detailed courses, we're going to this in a lot more detail. Now, we've got our core barrel down hole, and let's assume we've advanced and the core barrel is full of core now. I now have to get that core out of the bottom of the hole. I can do that in 2 ways. The one way I can do it is using what we call a conventional system. And the other way is using what we call a wireline system. Now, in a conventional core retrieval system. I will start my little schematic diagram here. I have my drill bit on the bottom of the hole, and this is my core barrel. I hope you can follow my little bit of drawing here. And then I've got my drill string going back up to surface. Now, this hole might be 1,000 meters deep, for example. I will start rotation. I will apply weight on the bit, and the bit will advance, and the bit will, as it advances, it will create a core sample. That core sample will feed into the core barrel. Or, if you like, the core barrel will feed over the core sample, whichever way you want to look at it. But now, once this core barrel is full of core, I can't drill anymore. I've got to stop drilling. And now I've got to retrieve that core sample. So that means I pull all the drill rods out the hole, either stand by rod by rod or stand by stand. I pull all the rods out of the hole. I disassemble the core barrel, extract my core sample, pack it in the core box, reassemble the core barrel, and I lower the rods back down to bottom. I've now, if this, for example, was a 3-meter advance, my hole would be 3 meters deeper. I then repeat the cycle, and I advance a further 3 meters, and then I go through that pulling and lowering exercise. Now, this is what we call a conventional core retrieval system. And we've got tons and tons and tons of different kinds of conventional core barrel that are used. Now, I think you can all understand that as the boreholes get deeper, the time to pull and lower gets longer and longer and longer. One of the first boreholes that I worked on as a young mud engineer in, it was the latter end of 1984, was a 3,800 meter deep hole being drilled in the western side of Johannesburg. I'm pointing like I'm in Johannesburg. I'm in Melbourne, so I'm a long way from Johannesburg. But it was near a town called Potchefstroom in what in those days was called the Western Transvaal. And that hole, 3,800 meters deep, it took the guys 13 hours to pull and 12 hours to lower. In a day, the drawing assistants, the guys would come on site and they'd be pulling rods. And they would pull rods for the entire shift, their 12-hour shift. He'd knock off, he'd go home, and he'd sleep, and he'd come back the next day and he'd do exactly the same thing again. It took them 13 hours to pull, 12 hours to lower, and it took them about 45 minutes to fill a core barrel. So they drilled for 45 minutes a day. Well, 45 minutes a cycle, if you want to call it that. They would then stop, pull for 13 hours, lower for 12 hours, drill for basically an hour, pull and lower, drill for an hour, and so on. So the deeper the hole gets, the more inefficient this process becomes. And a number of years ago, a company called Boart Longyear, an amazingly clever company, back in the 1950s, in fact, the mid-1950s. I was born in 1954, so about the time I was born, they developed what was called the wireline system. In the wireline system, they recognized that pulling and lowering drill rods all day long was really unproductive. And so they designed a core barrel with a retrievable inner tube. And I'm trying to show it to you. It's very, very hard to see in a two-dimensional picture, particularly on a tiny computer screen that some of you guys might be using. But essentially, we've got what we call the outer tube assembly, this part here, which is just like the core barrel we saw earlier. But inside that outer tube assembly, there is this very complicated-looking inner tube assembly. And the two of them together, you can see in the picture on the left-hand side. Now, this inner tube assembly is retrievable. And the principle here is that the core barrel will be on bottom, the bit's on bottom, we start rotating, we put weight on bit, and we advance 3 meters, for example. When we've advanced 3 meters, this inner tube, this little gray piece here you see at the bottom, that will be full of core. We'll then lower a special device on a steel cable. It'll go down, it latches onto the top, this very top part of the inner tube, and it allows us to pull the inner tube to surface. All the drill rods remain downhole. They stay exactly where they are. We just pull the inner tube out. When we get the inner tube to surface, we disassemble it, take the core sample out, reassemble it, and we literally drop it back down the rods. It floats down in the drilling fluid, floats down until it locks into the core barrel again at the bottom of the hole. We can then start to continue drilling. So it was an enormous technology step forward. Just changed the whole face of deep hole exploration drilling. Made it far more efficient. You could drill holes much more quickly than you could using a conventional system. This is what we call the wireline system. Now, we cannot go into any more detail there because we just basically just don't have the time to go into all of that detail. But those of you who've been involved in drilling and you've seen a wireline operation, you're very, very lucky. If you haven't, please try and get to see a wireline operation. Ask as many questions as you can to try and understand how it all works. Okay. A couple of the key things here in talking about diamond core drilling. A couple of principles that sometimes people don't understand. So let me try and spend 2 minutes on this. The length of the core barrels are typically 3 meters or 6 meters. All of the drill rods we use, I said a couple of minutes ago, all of the drill rods we use are typically 3 or 6 meters. And so the core barrels are 3 or 6 meters. They match the length of the rods that we use. And so when we advance the core barrel, when we do a coring run, we will advance either 3 meters or 6 meters. And so the hole would advance in those stages. And that's something that people very often don't understand, is the lengths of the core barrel and how far you can drill in one coring run. Guys, I'm going to scoot through this because this is not terribly important right now. I'm going to scoot through that part because we are going to run out of time, and I don't want to run out of time in a very short period of time. That's the basic principles of a diamond core drilling operation. We have conventional systems and we have wireline systems. Very seldom will you come across conventional drilling systems. In fact, that's not true. You do come across conventional drilling systems in modern exploration drilling programs, but the bulk of what you guys will be involved in will be wireline type drilling operations. The next method of drilling we're going to talk about here is rotary percussion drilling. Now, this is drilling where we have both rotation and a percussive action. And just purely for the sake of completeness, we've got 2 rotary percussion techniques. We've got what we call top hole hammer drilling and what we call down hole hammer drilling. And this is shown schematically on the right-hand side here. In a top hole hammer drilling application, we have in the rotation head of the drilling machine, there's a piston, and that piston is made to reciprocate. And that piston strikes the top of the drill string. It sends an energy wave through the drill string into the bit. The bit then transmits that energy wave into the rock. The rock fragments, and so we make hole, what we call a top hammer system. The other system that we commonly use, what we call a downhole hammer system. I explained that a couple of minutes ago. So downhole, in the hammer, we have the cylinder, we have the piston, and we've got the bit at the bottom. And the piston is made to reciprocate very, very quickly. Every time the piston strikes the top of the bit, it transmits an energy wave, and so on. So we have these 2 rotary percussion methods of drilling. Now, I just want to talk a little bit about these just so we have an understanding of them. In both cases, both of these drilling techniques make hole by crushing. The bits crush the rock and create a chip sample, which is then flushed to surface. In a top hole hammer drilling operation, any of you guys who work in an open cast mine or an underground mine, they do what we call production drilling. So in an open cast mine, they'll drill what are called pre-split holes that basically shape the walls, the angle of the walls of our pit. And in an underground operation, we use it to drill blast holes to create tunnels and haulages. And we use what's called a rock drill. Not important that we understand that. It's not a drilling it's not an exploration drilling technique. It's an incredibly important drilling technique in a mining context, but it's not an exploration technique. So I'm not going to talk in any detail about it. I'm going to leave it there. I'm going to talk about downhole hammer technique because that's more, we use that more often as an exploration technique. As I explained earlier, it's a pneumatic system. We have this hammer. It's a 1.5 meter, 1.3 meter long cylinder of steel with a piston inside it and a bit at the bottom. And the compressed air makes the piston reciprocate, strikes the bit, transmits the energy wave into the rock, makes the rock fail, and then the air blows the cutting to surface. It's a very, very efficient way of drilling holes. And this schematic here just kind of shows you the passage of the air as it flows through the hammer. Now I've put this cutaway in for a particular reason. I've made the hammers sound like they're very simple. It's a cylinder with a piston. It's not quite as simple as that. There's a whole bunch of other very important machine parts in it. But the important thing to understand is that all of these things, all that this stuff at the top here, all that this does here, is it piston reciprocates. In this case, this yellow piece here is the piston, and this orange piece is the drill bit. So all that happens is all of these other parts, they're valves and all sorts of things, doesn't really matter what we call them. All they do is they make the piston reciprocate. And the piston comes down, hits the bit, transmits an energy wave, fragments the rock. This air that made the piston reciprocate escapes through the bit and then back up the annulus to surface. So the same air that makes the hole clears the hole. It removes the cutting, it blows the cutting to surface. So you have this dual action, or the dual function, if you like, of air in this case. Now, downhole hammers are fantastic tools. They produce a chip sample, and I'm going to talk a bit more about the sample just now, but they produce a chip sample, and they're very efficient. They drill hard rock incredibly quickly. It's a cheap method of drilling, a relatively inexpensive method of drilling. So roach percussion methods of drilling are used in early stage exploration projects where you're not worried about structure or grade. You just want to know what is down there, just get an indication of what is there, and it will produce this chip sample for you very, very inexpensively, much cheaper than diamond core drilling. And so it finds a lot of application in that. In fact, here in Australia, I'm living in Australia now, and in Australia, they do a lot of what they call chip sampling on their coal and a lot of their other hard rock mines as well. They do a hell of a lot of it, using hammers and using other techniques as well. So it's one that's the correct application will give you good, cheap, rough and ready samples. The one problem with it, though, is it's pneumatic, and compressed air is a very inefficient way of transferring energy. Again, guys, I can't go into a lot of detail. We just don't have the time. But essentially where the problem comes is the deeper the hole becomes, the greater the pressure loss, the air, the compressed air that you blow down the drill rods, it's got to overcome friction as it flows down the drill pipe. It's got to flow through restrictions in the drill pipe. And all of this consumes energy, and it creates what we call a pressure drop. So we'll have a compressor at surface delivering 24 bar air at 24 bar pressure. By the time it gets to the hammer, it's only 20 bar. It loses pressure on its way down the drill string, and it becomes a limiting factor to the effectiveness of this drilling technique. There's some other things as well, but for the time being, that's as much as we can kind of talk about in this case. Okay, so we spoke about diamond core drilling in a little bit of detail. We spoke about downhole hammer drilling, rotor percussion drilling methods. Now, there is a very, very special technique. I'm going to spend a little bit of time talking about this now. A technique that can both be used with rotary drill bits and with downhole hammer drill bits. So it's a rotor percussion and a rotary drilling technique, what we call dual tube reverse circulation. Now, I know I've been babbling on for over an hour now, but please work with me on this one. This is very, very important. Okay. Earlier, somebody asked a question about sampling with drag bits. We can circulate the drilling fluid through a borehole in 3 different ways. All the examples I've spoken about now, all of the examples you've spoken about, we pump the drilling fluid down the middle of the drill string. The drilling fluid comes out the face of the bit and flows up the annulus to surface. As it flows up the annulus, it takes the cutting with it to surface. Now, in some applications, we reverse that flow, and we use what we call a reverse circulation system. So what we do now is we pump the drilling fluid down the annulus. It flows across the face of the bit, picks up the sample, and returns the sample to surface up the middle of the drill pipe. So we've got what we call a direct circulation, we've got a reverse circulation, and then we've got a third system, what is called a dual tube reverse circulation system. And a dual tube reverse circulation system works like this. The drill rods have got an outer tube and an inner tube. And what we do is we pump the drilling fluid down the annular space between the 2 drill pipes. So the air comes down, I don't know if you guys can see my mouse terribly clearly, comes down through here, through that annular space between the outer pipe and the inner pipe. So it comes down there, it exits just above the bit, there's a little gap here, it flows around the bit, and the sample flows back up the inner tube to surface. And this is what we call a dual tube reverse circulation system. So we've got a direct circulation, we've got reverse circulation, we've got dual tube reverse circulation. Now, earlier I said to you that I'm a bit of a stickler for the correct terminology. Reverse circulation, what you see here, very often in the exploration industry, we talk about RC drilling. This is what we call RC drilling. It's not RC drilling, it's dual tube RC drilling. This is RC drilling. And if you guys fully understand what I'm trying to say there, we've got 3 ways of flushing: direct circulation, reverse circulation, and dual tube reverse circulation. And typically in the exploration business, when you talk about reverse circulation, what we actually mean is dual tube reverse circulation. And please remember that, okay? Now, the important thing here is in both systems where we have a direct circulation or a reverse circulation system, we produce a contaminated sample. The sample here in the direct circulation system flows up, it's in contact with the annulus as it's flowing to surface, and so the potential exists for the sample to become contaminated as it gets to surface. Similarly, with a reverse circulation system, the drilling fluid is in contact with the annulus, with all the formations you've just drilled, that too can become contaminated, and so the sample is contaminated. So these will produce contaminated samples. And so from a sampling quality point of view, they have limited quality or limited value because of the fact that they are contaminated. A dual tube system, however, produces an uncontaminated sample. The air that is blown down between the 2 tubes is not in contact with the formation. It escapes just above the bit. I'll show you just there how it happens. It comes out just above the top of the bit, flows across the hammer, flows across the bit, and the sample comes back up to surface. And again, because it's inside a tube, inside the inner tube, it is an uncontaminated sample. And that is why dual tube RC has become such an important part of the exploration industry, because we can produce these uncontaminated samples. They're chip samples again, guys. It's not a core sample, it's a chip sample. We can produce these uncontaminated chip samples relatively quickly, relatively cheaply. And how do we do that? In a minute, I'll show you there's 2 different ways we can do it, and I'll show you those 2 ways in a moment. One quick thing I just want to talk about before we move on, important for you to understand, is the flow path of the sample. So we have a compressor delivering compressed air, and that compressed air enters what we call the air swivel. And this air swivel allows the air to travel down the annular space between the two drill rods into the hammer or whatever makes the hole. It comes out at the base of just above the top of the drill, but flows across the face and back up to surface. It then flows the whole way through the rotation head into what we call a sample hose or a discharge hose, and then into what we call a sampling system, where we collect the sample. The whole purpose of this exercise is not to drill a hole. The purpose of this exercise is to collect a sample. And so the sampling system, I'll talk in detail about these just now. The sampling system is where the real hard work is done, because we've got to take this sample, we've got to collect it, bag it, and then send it away in a state or in a condition that truly represents what we've just drilled. And I will show you just now the intricacies of that. So this is the sample flow path. Very important for you to understand. The earliest dual tube reverse circulation systems was developed in Canada in the 1950s, where they were trying to core drill very, very soft, friable material. And they just were getting no luck at all. And somebody came up with this dual tube system, but they used a drag bit at the bottom. It was very soft material. They used this dual tube system and they got incredibly good samples. Much better than they got with diamond drillers. And it was incredibly successful, and it changed the whole face of that particular project. They then tried to use that same technique in hard rock conditions. And because they were using a drag bit with tungsten carbide cutters, it couldn't drill the hard material. And so they said, this technique doesn't work, and they put it on the shelf. And then many, many years later, 20 years later, the Australians got hold of it. And a few companies in Australia said, no, we're going to develop this. And so what they did was, instead of putting a drag bit at the bottom, they developed what we call a face sampling hammer. So it's a downhole hammer. And please excuse my terrible schematic here. It's a hammer, just like the one we spoke about earlier. We pump compressed air down the annular space between the two drill rods. It enters the hammer. The piston operates. The bit makes hole, creates chips. The air escapes at the top of the bit, blows across the face, and carries the cuttings to surface. And this is what the basic principle, what we call a face sampling hammer. It's a downhole hammer, so it drills hard rock incredibly fast. And so what you can do now is you can take this dual tube system and you can drill very, very quickly. You can produce uncontaminated chip samples in hard rock. And that development just changed completely the face of shallow mineral exploration in hard rock conditions. So these face sampling hammers now are efficient drilling tools. It allows us to drill in hard rock and produce uncontaminated samples very, very quickly. And as I said, it changed the face of shallow depth. You can't use them to massive depths, but it changed the face of shallow depth hard rock exploration. So we have these hammers that change the face of exploration because of their efficiency. The beauty of them is that they produce these uncontaminated samples, and they produce in the right formations. They produce a really, really large cutting, which is very advantageous in some cases. In some cases, it's not, but they are very, very efficient. And over the years, since I guess about the mid-1970s, maybe later than that, maybe since about the sort of mid-1990s, the development of these hammers has been incredible, and they are now incredibly efficient drilling tools. They cost a fortune, but they're incredibly efficient as drilling tools. In this little picture here, all I wanted to show you was this is where the air comes out. It's quite hard to picture this, but imagine this is your downhole hammer. You've got a string of drill rods up to surface. The air comes down in the little annular space in the drill rods, enters the hammer. The piston operates. It then escapes here. There's a series of holes here. It escapes there. It flows down next to the bit into the holes in the face of the bit, and then the sample goes back up to surface. This little tube here on the left-hand side is what's called the sample tube, and that's where the sample disappears into the bit, into the hammer, and back up to surface. Now the key thing here, let's scoot onto this next part here. The key thing here is that the sample we produce, it's uncontaminated, but it is a chip sample, and when we drill a full hole, the volume of cutting, the massive cutting we produce is enormous. And there's a range of different sizes of reverse circulation hammer that we can get, but I've just showed you schematically here. If we drilled a 95 millimeter hole in 2.8 SG material, we'll produce about 20 kilograms of cutting per meter of bevel. If we drill a 114 millimeter hole, a 4.5 inch hole, we'll produce about 29 kilograms of cutting. If we drill a 5-inch hole, a 127 millimeter hole, we'll produce about 36 millimeters of cutting. Now, there's no way in the world that we can send those volumes, that mass of cutting, to a lab for analysis. So what we've got to do is, out of these primary samples, these bulk samples, we've got to extract from them a much smaller sample that we can send away to the lab. But that sample we extract must be representative of that bulk sample. So what we really want to try and do is, from these, is get a 2 or 3 kilogram sample. Different mining companies have different requirements, but we'll get a much smaller sample. But that sample must be representative of that total bulk sample that we produced. So bear in mind, guys, these are 36 kilograms per meter of advance. So if I've drilled 100 meter or 150 millimeter hole, multiply 150 by 36 kilograms, and you've got a bunch of cutting there. So we need a way to split the sample. We need a way to make it smaller. And there's different ways that we can do that. And this is the heart of a dual tube reverse circulation system. Drilling a hole is a doddle. That's a piece of cake. That's easy. That's very, very simple. We've got all the correct tools here. We've got these beautiful hammers and beautiful drill rods and beautiful drill rigs and compressors, and they can drill the hole for us. But we don't. That's not why we're doing an exploration project. We don't want a hole in the ground. We want sample. And I see time and time again, I see monstrous amounts of money spent on drilling these holes, and the sampling, the capturing of the sample, the bagging of the sample is just done incredibly poorly, and you lose all the value that you created in your project. So there's different ways we can do it. The simplest way, and you see a lot of this in very early stage projects around the world, is you use what's called a manual splitting system. So the sample comes up through the drill pipe, through the rotation head, into the sample hose, into a cyclone. And the cyclone is a conical device, and the purpose of the cyclone is purely and simply to slow the sample down. So as the sample enters, it spins, it slows down, and it falls down this conical chute into a very sophisticated bucket arrangement you can see here, and they collect the sample in a bucket. That bucket is then poured through a riffle splitter. If you're a gear, you would have seen what a riffle splitter is. It's got several tiers in it, and it sequentially splits the sample. I'll show you just now how that works. And this picture on the right is a typical early stage exploration project. I don't know where this photograph was taken, but you can see here, there's the sampler, there's the cyclone, I beg your pardon, and these poor guys sit and breathe in copious amounts of dust all day long as they take the bag of sample, pour it through the riffle splitter, and that's what they do the entire day long, the whole day long. It's a it's a manual sample splitting system. Now, a riffle splitter, I'm not sure I'm telling you the truth now, but I think most of the ones I've seen are 4-tier riffle splitters. The principle is very simple. You pull your sample into the top here, and it goes through a tier is made up of identical slots, sets of slots. And so the sample falls in, half of it goes to the left, half of it goes to the right. So 50% of it will be discarded, it falls onto the ground. The other 50% is retained, and it goes into the next level of slots, the next a riffle or the next a series of splits. Again, half of it is discarded, half of it's retained, then it goes through the next 2 levels. And so what we end up with is if, for example, we had 36 kilograms of bulk sample, our primary sample, we pour that 36 kilograms into the riffle splitter. Sequentially, half is discarded at each split. And so we will end up, after the first split, we'll have 18 kgs, we'll have 9 after the second one, we'll have 4.5 kgs after the third, and 2.25 kgs after it's come out the bottom of the riffle splitter. So we'll have 2.5 kgs of sample, which theoretically is exactly representative of that primary sample we put in there. And I don't know. I'm not a statistician, but I have seen sometimes the sample comes out. There's 1.5 kg. Sometimes there's 2. Sometimes there's 3. The riffles get blocked, particularly if the sample's damp, and all sorts of things go wrong. Then you have biases, and so you land up with a non-representative sample. But this is the way many early stage projects work, with a riffle splitter, and it's manually loaded. I hate seeing it because we speak all the time about safety, and we speak about the conditions that people work in. And let me just go back here quickly, guys. And this is actually, the picture on the right is actually quite a nice one. The others that I've seen with these poor guys, they breathe in that dust 12 hours a day. It's cannot possibly be allowed to happen, but it does. Happens in lots and lots of exploration projects. Now that's a manual way of splitting the sample. The other way that we can split the sample, the other way we can do it automatically. And most rigs that you guys will come across will have an automatic splitter. Again, without going into huge amounts of detail, this is your sample hose. The sample comes up through the hose into the cyclone. It drops into what we call a drop box. It then falls into the riffle splitter. And this, you can see that the little the blades here, not blades, I forgot what the terminology is, where the sample will fall through. It'll sequentially be discarded or retained. And this is what an automated riffle splitter will look like. Now, riffle splitters are not that popular anymore. And most companies now use, or they specify what is called a rotating cone splitter. And this one looks, if you look at the left-hand picture, again, we've got the discharge hose or the sample hose. We've got the cyclone. This part here is called a drop box. Not important for us to understand right now. And then this bit at the bottom here, this is the splitter. This is the important part. That's the bit that takes that bulk sample and splits it and gives us our reduced mass sample at the end. And basically the principle behind it is that the sample is dropped onto the top of this cone. And the theory is that as it's dropped on the top of the cone, it will spread evenly across the cone. Mm-hmm. And then fitted on the cone, you can see these little blades here on the left and right-hand side. And those have got an opening that will capture either 3% or 6% or 9% of that sample. And so the principle is if you have a 36 kilogram sample, you drop it. The theory is if these blades are set at 6%, for example, you're going to have 6% of that sample coming out the one chute and 6% out the other. You can get 2 samples, what we call an A and a B sample. And that's roughly the principle of a rotating cone splitter. Again, I've seen cases where in good rock conditions, in good formation conditions, you'll have an A and a B sample the one will be double the size of the other. And it's again, we can't get into too much more detail, but the purpose of the purpose of the project is not to drill holes. The purpose of the project is to produce samples. And so what you want to do is we want to make sure that the sampling, the collection of the samples, the labeling of the samples, the bagging of the samples is perfect. But unfortunately, what we tend to do, and please forgive me back again, guys, with a beautiful compressor, with a beautiful downhole hammer, and all the people are trained and they're skilled. And then these people who are doing the sampling, if you'll pardon the term, they're at the lower end of the food chain. These poor guys are not trained. They're just told to pick up bags, chuck them in there, and then grab what comes out and tie it up and put a label on it. They're not motivated to work to any kind of quality system. And this is the business end. This is where a sample comes. And I've seen countless examples of these poor guys. They earn the lowest salaries of anybody in a drill rig. They have the most important job when it comes to gathering the sample or collecting the sample from from an RC system. I'll give you one little story, and I must be careful because we're out of time. I was on a project in Guinea doing some work, and for some inexplicable reason, I got asked to attend a meeting on a Saturday morning. It was a fight between the mining company and the contractor. And the mining company did their mass balance calculations. In other words, they took these samples that were supposedly 6% of the bulk sample. They knew what the density of the material was. They knew the volume of the hole. And they said that they were consistently 10% down. So in other words, somewhere in the system, they were losing 10% of that sample. And there was this huge fight between the mining company and the drilling company, and neither of them was giving way. Kind of very long story short, we left the meeting with no resolution at all. And I was taken out to where I was doing my work on some diamond drill sites. And on the way, we drove past one of these reverse circulation rigs. And I said to the guy, stop, let me go and have a look. And I went and had a look, and it took literally 2.5 seconds to work out where the problem was. What these guys were doing on their sampler, in this example here, the sample comes out of these chutes on the right and the left-hand side, and you'll put a bag at the bottom, and you'll collect the sample in a bag. This particular sampler didn't work like that. This particular sampler, where this sort of screen is here, in fact, I lied, below it, below the screen, there was an opening and there was a jug. It was a square jug that fitted into a slot. And the sample came out of the chute into the jug. And the guy would then take the jug out and pour the jug into the bag and then seal the bag and label the bag. But the problem was these guys were drilling 5.5-inch holes, and the Cyclone was designed for 4-inch holes. So the volume of sample in the jug, it was peaked, if you can picture what I mean. And when he pulled the jug out, all it did was it took the top part of the sample off that fell onto the ground, and he put that in the bag, and that's where their 10% was. And nobody had bothered to go and have a look at the operation and try and understand it. You know, they just assumed that the samples are collected perfectly. And so it's a wonderful, wonderful expression technique, but it can be a real dog if it's not done properly. Okay, so that's RC. Wonderful drilling technique, as I said, but it's got some limitations and problems. Okay, guys, I'm going to leave this part there, this technical part now. I'm sorry you've had to rush through it, but that's just the nature of the beast. You've got a wonderful opportunity to attend the program in September, where we talk about this in a hang of a lot more detail. Okay, the second key aspect that I believe a geologist must have a good understanding of is the legal basis of your drilling operation. And I just want to touch on some of this now. This is very South African specific, but it's applicable. It doesn't matter. In every country in the world, we've got laws that you have to abide by, and these are just examples of South African laws. So let me run through this quickly for you, okay? In South Africa, in every country in the world, we have a legal hierarchy. And we have a layering, if you like, of different types of laws, different types of statute that affect the way that we work. And in South Africa, we have our constitution, we have our Bill of Rights, which sets us apart from previous administrations in South Africa. And then under that, we have just thousands, not thousands, hundreds of written laws, statutory laws. And these fall into different levels. We've got national laws that apply to everybody in South Africa, like our Road Traffic Act, that only applies to a third of the people in South Africa. We've got provincial laws, we've got municipal bylaws, and so on. And then we have what we call common law. So we're governed in terms of the way we operate, the way we work as citizens, by written law, statutory law, and by common law. For example, there's no law in South Africa that says you cannot murder anyone. There's no law that says you can't murder. It's common law. Of course, you can't murder people. What we do have in the statutes is different procedures that, given a murder, for example, a terrible thing to talk about, I'm sorry, but given a murder, there'll be different circumstances. And based on the circumstances of that murder, will be argued in court, and they will then a judge will say it's different levels of seriousness and then impose different levels of sentence. It's not cut and dried. But there's certain things that there's no laws about. It's common law. So in South Africa, the Constitution is the guiding principles that govern what we do as citizens of the country. And Chapter 2 of our Constitution is what's called the Bill of Rights. And the Bill of Rights essentially lays out all of the rights, the right to equality before the law, and so on. Very, very important part of our Constitution. Every person, anybody who works for a mining company would have heard these words before. Every person who comes to work has an expectation that he can go home in the same condition he came to work. He can work in safe conditions, and he can go home healthy every day. And so there's a fundamental duty for every employer to make sure that his employees can work in a safe and healthy environment. There's statutory laws that enforce that, but there's also common laws and obligations that are imposed or that employees and employers must abide by. But similarly, a very, very important point is that employees too must play their part. And employees have a duty to take care of themselves and their fellow workers in their place of work. We've all got to make sure that everybody acts within the law. And in South Africa, this becomes a big, big, big problem, particularly in mining environments. Now, unfortunately, in many industries, and our mining industry is a perfect example of this, in many industries, we have not created safe and healthy workplaces. And South Africa has got a very, very, very sad history of fatalities in the mining industry. In recent years, it's declined. Our number of fatalities has declined quite dramatically. Everybody pats themselves on the back. But then if we look at mining activity, we're producing ever decreasing tonnages of ore. And so one would expect our fatality rates to drop. So we're not that smart. We think we are, but we're not quite that smart yet. So the mining industry here was really, really bad. And it was an excellent example of where trade unions put pressure on government to improve safety standards, and it resulted in some amazing work in South Africa. A perfect example of that was the Leon Commission, which was commissioned in 1994, I believe it was, to look at safety in the mining industry And as a direct result of the work that the Leon Commission did, the new Mine Health and Safety Act of 1996 came into effect. And it's fantastic legislation. I'll talk a little bit about it in a couple of minutes. So as a geologist, you unfortunately need to be aware of many different statutory acts of Parliament that affect the work you do. In the context of South Africa, we have the Occupational Health and Safety Act, we have the MPRDA, and we have the Mine Health and Safety Act. Those are the three main ones. Then there's a whole bunch of others, depending upon the type of work you do, will have a greater or lesser impact. Environmental Management Act, Water Acts, etc., might have a bigger impact on you. But the main ones that concern us is the MPRDA and the Mine Health and Safety Act. I'll talk very briefly about those, and we'll see how far we get. I'm not going to talk about the Occupational Health and Safety Act. The MPRDA, the Mineral Petroleum Resources Development Act, defines prospecting as intentionally searching for any mineral by any means or any method. So prospecting is intentionally searching for a mineral which disturbs the surface of the earth. I'm paraphrasing here, okay? There's drilling a borehole, intentionally searching for a mineral. Without a question, it is. Does it disturb the surface of the earth? It most certainly does. So prospecting, because we're prospecting, it means we need a prospecting permit issued by the Department of Mineral Resources. That's the DMRE, it's called in South Africa now. But one important distinction I want to make here. The MPRDA says, let me just go back here quickly, prospecting is intentionally searching for any mineral. And then it goes on and it defines a mineral. And a mineral is any substance excluding water. That's critically important. Any substance excluding water, but including sandstone, blah, 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 blah. So if I'm intentionally searching for a mineral, blah, 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 prospecting permit from the DMRE. If I'm searching for water, if I'm drilling a water well, no problem. I do not need a prospecting permit. That's one of the biggest problems we've had in South Africa, is because we've got all sorts of people drilling for water, haven't got a clue what they're doing, and every day we destroy a very, very important natural resource. So one quick point here, because water is not a mineral, we don't need a prospecting permit. So it's not regulated by the normal laws that would regulate mining, but it would be regulated by the Occupational Health and Safety Act. If we're drilling a water well on a mining lease area or a prospecting area, we then do have to have a prospecting permit. It's covered by the prospecting permit. And you'll see this will get a little bit more complicated. Blah, 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 blah. I'm going to scoot through this because this is not so important. Blah, 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 blah. From a mining point of view, in South Africa, one of the most important pieces of legislation is the Mine Health and Safety Act. This is our Bible. This is what people get the shivers and the shakes about when they go to work on mines. It's a wonderful piece of legislation if you read it and if it's correctly applied. The Mine Health and Safety Act consists of 8 chapters and 106 sections, and each chapter deals with different aspects of mining. I'm not going to go into that in detail now. I just want to talk about one or two aspects of this quickly. The first one is that in the definition of a mine in the Mine Health and Safety Act, a mine is defined as any borehole in the earth, including the portion of the earth that is under the sea or other water, made for the purpose of searching for or winning a mineral. So any borehole that is made with the purpose of searching for or winning a mineral is a mine. So it's very, very clear that an exploration borehole is a mine, and therefore it must comply in every aspect with the provisions of the Mine Health and Safety Act. Now, that is an enormously onerous task for a drilling contractor. And any of you who work on mines will understand why mining companies are so incredibly pedantic about health and safety on mines, because you've got contractors, many kind from different, not only drilling contractors, work on mines who do not understand what the law says. It goes on and it says that a mine, when it's used as a verb, when the term is used as a verb, the making of any excavation or borehole referred to in paragraph A. So in other words, the purpose of drilling, or in fact the process, I beg your pardon, of drilling is the process of mining. And so an exploration borehole is a mine. So the bottom line here, guys, is this. If you're involved in exploration drilling in South Africa, you had better understand the Mine Health and Safety Act. You need to buy yourself a copy of it. The best copy of the Mine Health and Safety Act you can get from LexisNexis. They're based in Durban. It's an excellent publication, and people laugh at me, but I promise you, I read it. Although I live in Australia now, I've got a copy that I put next to my bed because I still lecture on it. And I read it not every night, but very often I'll pick it up and read it. It's amazing. It's easy to read. And if you understand the context of it, you can understand where it applies to a drilling operation. Now, we could talk about different aspects of this till the cows come home. There's a course, there's a program I do on the Mine Health and Safety Act. It's a very, very, very lengthy training program we do. But when you come out of it the other side, you'll understand exactly why the Mine Health and Safety is such an onerous piece of legislation. I want to just quickly talk about a few other definitions in terms of the Mine Health and Safety Act, and then we're going to leave this and we're going to talk about some economic aspects. A couple of definitions here that are important that will help to put this whole thing in context to make you understand why it's such clever legislation and why it's so important for you to understand it. Again, another definition that is contained in the Act is the definition of an owner. Who is the owner of a mine? And it's very, very clever legislation, very, very clever. It says that the owner of a mine is the holder of a prospecting permit or mining authorization issued under the NPRDA. So in other words, if you go along to the NPRDA, go to the DMRE, the Department of Minerals and Energy Resources, whatever they call themselves now, go along to the DMR and apply for a prospecting permit over a piece of land, you then are the owner of that prospecting permit, or if that matures into a mining authorization, you'll be the owner of the mining authorization. It then goes on. It says, if a prospecting permit or mining authorization does not exist, in other words, you're doing it illegally, you don't have a mining authorization, you have a prospect, but you're drilling anyway, then the person for whom the activities are being done is deemed to be the owner. So you've got some crook who comes along and says, listen, I want you to drill some boreholes for me over here. The contractor doesn't know that he's operating illegally. It's the crook who is the owner. And there's lots and lots and lots of that goes around in South Africa and other countries in the world. Then there's a third possibility. It says if neither one or two is applicable, then the last person who worked the mine or that person's successor in title is the owner. This is critically important, what makes this legislation so clever. In South Africa, as in many other countries in the world, there is huge problems with abandoned mine workings. And in Johannesburg, acid mine drainage is a massive potential problem that threatens water resources and buildings and all sorts of activities in the Johannesburg area. Now that acid mine drainage, all of that contamination came from mines that were mined many, many years ago, and all of the money that was made left the country decades ago, and all of the people that have made that money have long since said goodbye to South Africa, and they're sitting in other countries, and we're left with this massive potential disaster. Now, this little third clause here attempts to take care of that, because it says even if you've stopped working it, even if you've died and you've left that mine to your son or daughter, they are the owner. And therefore, they are responsible for all of the duties and responsibilities that are placed on the owner by the Act. Now, these are the little parts of the act that when you sit down and you read it, it all starts making sense. And you start saying, gee, this actually is quite clever. The way that the way that this is all put together. So it's very, very clever, very, very clever legislation. I'm going to, there's a whole bunch more I want to talk about here, but I'm going to leave this part now. In the time we have available, there's no way in the world that I can give you a proper overview of the Mine Health and Safety Act. All I can leave you with is, if you are going to work on a mine in South Africa, or any other country for that matter, you better understand the legal framework under which you're working. In many countries in the world, there is legislation that governs exploration drilling. In many countries of the world, the law is silent. There's nothing. Many African countries, there's no law at all. And your exposure then is massive. Because if something goes wrong, it's kind of, well, the punishment can be fairly subjective. Whereas in countries where there's defined laws, it's more objective. So just make absolutely sure you understand. And don't think that just because you work for a big mining company, they understand all of this, because that doesn't always work. Make sure that you understand what the legal framework is in the area you're working. Guys, I'm going to leave that there because else we get out of time. I'm sorry, but we just have to do that. There's just too much stuff to do, and we don't have enough time. Let's talk now about the last part. What does a geologist need to know about the economic aspects of drilling? Well, I think this is one of the most important parts. The technical stuff, sometimes for geos is quite hard to understand. The safety stuff is quite hard to understand. But this stuff, every geo can understand, because we all work with money. We've got to run our lives and run our budgets and our homes and so on, so we can all pretty much understand that. So I'm going to try and get through this and give you a good understanding of what it means. So I believe that a geo needs to understand the relationship between the geologist and the contractor. You need to understand a little bit about how the contracts, how that relationship is structured. The most important part, you must understand how a contractor makes profit. And then even more important than that, you must understand what you can do to ensure that the project runs smoothly. In other words, to ensure that the contractor makes a profit. That might sound a bit silly, but you'll understand what I mean in a couple of minutes. Let's get stuck into it. Okay. Every drilling contract is based on contract. So you'll have a mining company or exploration company with a fixed budget normally, and they want to get as much information as they possibly can. They want the maximum number of meters at the lowest possible price. The contractor, on the other hand, has got massive capital investment in his drill rigs, people, trucks, loaders, you name it, huge amounts of capital investment. And he has to maximize his profit. He has to make a profit. And so he wants the highest price per meter. So between these two seeming extremes, we have to arrive at a contract that allows both of these entities to achieve their objectives. And as I said earlier, very often, one gets the impression that mining companies believe that their role is to put contractors out of business. And so you have what's called scope creep, where we're gonna drill 20,000 meters in the next year. All of a sudden that drops to 15 and then to 10, the contractor can't make money, and then the fights stop. So very often we have these things that affect the structure of the project, and it leads to conflict and problems down the line. There's two very, very, very important principles, guys. And if you remember nothing else, remember this. If a contractor is not making a profit, he cannot perform on site. I'll say it again. If a contractor is not making a profit, he cannot perform on site. Nobody, no commercial entity can work at a loss unless you're the South African government. You cannot work at a loss consistently. Somewhere along the line, things are going to fall flat. So the contractor must make a profit. If he's not, he's going to have production issues, he's going to have quality issues, he's going to have safety issues, without a question. Please bear that in mind. He must make a profit. We don't want him to make $14 million a day, but he's got to make enough that he can do what he needs to do to sustain his business. The second principle that's critically important is that profit is the reward for risk. Every mining company wants to load the contractor with all the risk. You take all the risk, geological risk, community unrest risk, you take all of it. And sure, the contractor will do that, but he's going to lather you in terms of price. Because he's carrying all that risk, he's going to increase his per meter rates and his other charges so that if something does go wrong, he's got some money in the bank to get him out of trouble. And so a good contract is one where you share the risk. You identify what all the risks are and you share them. Or you apportion them to risks that the contractor control and risks that the mine can control. And then you could have an equitable and workable contract. So please remember those two principles, guys. They're critically important. Okay. I'm going to scoot through this. I'm sorry I have to do this, but I want to get to the most important parts here. There are different kinds of contracts. And one of the most common contracts that are used, certainly in South Africa, but less so elsewhere in Africa, is what we call a variable rate contract. And in a variable rate contract, the contractor will have fixed costs and you'll have variable costs. So what the contractor will do, you'll go out to tender and you'll say to him, we want to drill 20,000 meters of in-queue drilling over the next year, and we need 3 drill rigs, and you give him all of the specifications, the work you want done. The way the contract will work out his costs is to work out his fixed costs. These are the costs that he incurs whether he drills or not. Salaries, wages, repayments on equipment, insurance, rentals, lights, water, cell phones, etc., etc. He'll have these fixed costs, and he'll calculate what those total costs are for the year. Then he'll say, how many meters am I going to drill in this year? The mines say they want me to drill 20,000, but I know they lied to me last year. I'm only going to drill 15,000. So he'll take that total fixed amount, he'll divide by 15,000, and he'll get his fixed cost per meter. It'll add to that his variable costs. That's the cost of his bits, drill rods, drilling fluids, oils and greases, bonuses, etc., etc. The costs he'll incur only when he's drilling. He'll add those two together, and that will be his total cost per meter. He'll then look at the mining company. He'll say, I'm going to add 30% or 40% or 50% to that, and that will be my rate. That's how much I'm going to drill for. So the key element here, and I'll show you the impact of this in a minute or two, you'll have fixed cost per meter and his variable cost per meter. So, for example, let's take a silly example here. Let's assume a contractor has total fixed costs of $150,000 a month, and his variable costs are $35 a meter. That's his bits and reaming shells and core springs and all the other stuff that goes into drilling. He's drilled for many, many years. He knows what that costs him. And so he estimates he can drill 900 meters a month. His fixed costs are going to be 150,000 divided by 900, which is $167 a meter. That will be his fixed cost. And then he will add to that his $35 per meter. And so his total costs will be $202 per meter. That's what he's calculated is going to cost him to go and drill those holes for him. Then he'll add his profit margin. And the profit margin will be based on his perception of risk. If there's 6 companies bidding for the work, he might reduce his profit margin. If he thinks he's in the running and the mining company like him, and he can charge a little bit more than the other guys, he'll try and charge a bit more. But you have to pick a level, submit his prices, and then the tender will be evaluated. But the point is this: in times of tight work conditions, when there's not a lot of work, contractors will underbid. They will bid below their costs just to get the work. It sounds stupid, but they do it. And that is dangerous, because that means he's not going to make a profit, and I'll guarantee he's going to have an accident. You're going to get poor quality samples, you're going to get terrible production, and I'll guarantee you'll have an accident. And that's one of the key things that mining companies have got to understand, is that contractors cannot work below cost. It's important for you to know that they're making profit. It's important for you to know that they're not making a profit. Now, the problem is what happens is that very often what unfortunately happens, guys, is this. You tell him in the tender spec he can drill 900 meters a month, but the geologist forgets to peg the next site. Oh, he hasn't moved equipment, or the roads haven't been prepared yet, or there's no water, or the geologist had a fight with his girlfriend and doesn't feel like coming to work. And so the guy can't drill. And so instead of drilling 900 meters a month, he only drills 600 meters a month. And all that does is that instead of dividing 150 by 900, you divide 150 by 600. And that increases his fixed cost per meter. The variable costs remain exactly the same. But all of a sudden, his total costs now escalate to $285 a meter. Now, all of a sudden, he's not making money. And this is where the problem comes. I see it every single project I ever work on is the contractor, the mines say one thing, people don't do their work properly, and the contractor can't drill the meters that he thought he was going to drill. His costs go up and he loses money. Then everybody wants to beat him up because he's not producing the meters that he should. The quality is poor, and he has the odd accident. Everybody wants to throw him off site. So the key thing here, the key takeaway here that I want to share with you, and I think it's fairly obvious now. As a geologist, I believe one of your key roles in terms of the economics of a drilling operation is make sure that what you do does not stop the driller from drilling. I go so far as to say it is your job to make sure the contractor makes a profit. That sounds terribly controversial. But what I'm trying to say is this: don't stop him from drilling for a frivolous reason. Do your work. Frequently, we see cases where guys stand for a week because a site hasn't been paid. You can't do that. You just can't do that. If you do that, then you must pay him standing time. And standing time in a mining company is a swear word. You don't pay standing time. Nobody wants to pay standing time because it proves you didn't do your work. So do your work. Make sure the guy can get drilling. Help him with infrastructure on mines. Mines are notoriously bad at providing infrastructure. So make sure you do that. Safety officers. I see countless times. You go onto a drill site, the guys are staying, you say, why are you staying? Oh, they did a safety audit this morning and the fire extinguisher was in the wrong place. And so they've stopped us from drilling. We've all got to get retrained on fire extinguishers. That has got to be the dumbest thing I've heard in my life. There are a million things that'll kill you in a drill site. Promise you, a fire extinguisher is not going to kill you, or it's not going to save your life either. Promise you it's not. I think anybody's ever been saved by a fire extinguisher. So don't stop the guys for frivolous reasons. Stop them for serious reasons. Without a question, you stop them. You stop the operation if there's a fatal risk or a serious risk. But make sure you do your work. Make sure that contractor can produce a profit. If he's a bad contractor, he shouldn't have been in the first place. You guys made a mistake in selecting him. But if he's a good contractor, help him, because he'll be there next year when you need him again, or the year after when you need more work done. I'm going to leave that there, and we can now have some questions. Okay, while people are putting their hands up, let me answer these ones quickly. Johannes Kutsia. Johannes, in South Africa, you do not need to be registered or have qualifications to drill. There's no such thing as a legal driller in South Africa. There's the difference between a competent driller and a not competent driller. I'm not sure what kind of, when you say boreholes, you want to drill water wells. My suggestion would be get hold of the BWA, the Borehole Water Association. There in the middle. I'm a little bit involved with trying to set up some training programs for water well drillers. So that might be a place to go. But basically, there's no qualification you're required to be a driller in South Africa. generally speaking, the ability to breathe unaided is about all you need. How often are tricones used these days? I know they was quite extensive historically in some countries. Tricone bits. Tricone bits. The original tricone bit was designed, was patented by Howard Hughes. You've all heard of Howard Hughes, and you might have seen that movie. I forgot what it's called, about Howard Hughes. He's an amazingly clever man. He designed the first tricone bit, and they're widely used in mining, in oil and gas exploration. Sishen Iron Ore Mine used to be one of the biggest users of tricone bits in the world, drilling their very, very hard banded ironstone. So they're still very widely used, very, very widely used. Patients, what's the possibility of losing valuable parts of the sample in the riffle splitter? Very good chance of losing valuable parts of the sample, without a question. Robert asked, early express uses AC drilling. AC drilling is air core drilling. Air core drilling is a special type of dual tube reverse circulation drilling. It doesn't use a hammer at the bottom of the dual tube drill rods. You've just got a drag bit, if you like, and you get your sample coming back up the middle. Air core drilling is used in shallow soft rock applications, Robert. I don't know where you've seen it before. It's very common in Australia, very common in Zambia, for example, for some of the exploration they do there. Saul Rivera asks, when we use auger drilling for secondary deposits and gravel beds, how can we be representative using a riffle splitter? Well, you can't, because an auger by definition will produce an uncontaminated sample. So there's little point in putting a contaminated sample. I beg your pardon, let me rephrase that. An auger will produce a contaminated sample. You're going to take that contaminated sample, you're going to put it into a riffle splitter, you're going to make it even more contaminated, or more heterogeneous, I guess would be the correct term. So I would say it would not be a great idea, but I'm open to discussion on that time. And then Patience says here, spending time in the mining industry, it really is a swear word. It's really sad. You're right, Patience. Yeah, I'm very lucky. I'm very, very lucky. I do a lot of tender work with mining companies, and it is a swear word. People don't like paying standing time. Let's move. Ntobeko, do you want to ask your question quickly?
Yes, Colin, thank you. That was nice. And so I just wanted to ask you about the question I have. Yeah. So let's say in a situation where you're drilling something like mine tailings or just cut dams, what type of negative droppage should we use, or type of flashing system should we use? Air or water? Which one is best in those kind of cases?
When you say what kind of tailings are they? Are they gold, platinum, coal?
Let's say it's coal.
Okay. One of your biggest problems is going to be getting a drawing onto your tailings dam. We didn't talk about it here, but the most successful drilling I've seen on that type of tailings is what's called sonic drilling. Very expensive, but very good samples. RC diamond drilling, I think you're wasting your time, because the tailings have got no real cohesiveness, so you're going to tend to blow out. You're going to cause all sorts of problems. I would say, and if you want to give me a call sometime, I'd be more than happy to pass information about sonic. Sonic drilling would be, I think, is the way to go in that situation. But you're more than welcome to send me a mail or give me a call and we can chat about it a bit further. Sorry, let's move on quickly. Vic, you wanted to raise a point?
Yes, thanks, Colin. Thank you very much for this really lovely presentation, although broad in scope, maybe a bit shallow in detail, as you say, but very good coverage. What I wanted to say was the difference between the rotating cone and riffle splitting. The problem is that the rotating cone violates one of the most important principles of sampling, in that it cannot sample the whole stream. It samples a portion of the stream all the time. It doesn't sample all the stream, just a portion of the time. So from that point of view, it is flawed, and you will never get a representative sample. Look, there are companies currently working on this to develop samplers that will obey that principle. And I agree with you 100% about riffle splitters. They do create a lot of dust and so on. But in the principle underlying the use of the riffle splitter, if it's used carefully, if it's designed carefully, then it works well. What you should not do is have 2 or 3 riffle splitters welded above one another. That is disastrous. That's going to induce bias and inaccuracy straight away. But I thought I would just make those 2 comments about the rotating curling riffle splitters. Thanks, Colin.
Thank you for that. I don't want to overstep our time, but I just want to add one comment. There was I was involved in a little while ago at the front end of a project. There's a company in Ireland who have just released what they say is the world's first autonomous RC drawing, where it will sample without a human being anywhere near it. And this is, there's been huge fanfare, and it's been applauded all over the world. I said, I share the applause. It's fantastic. But we must not forget, the reason why we're drilling that hole is not to drill a hole. So it doesn't matter how fancy the rig looks. So it's how good that sample splitter is.
Exactly.
And that's what I want to see. I think you, Dick, over your years of working, you've got incredible knowledge in terms of sampling a theory and practice that I think many companies could use. Because yes, I'm certainly not an expert in it, but I just see things on site that just clearly can't be right. So thanks for your comment. Is that Pete Roberts from Anglo, ex-Anglo?
Yes.
How are you, Peter?
Well, thank you. How are you?
Good, man. It's good to see you again, or hear you.
Yeah, great presentation, Colin. Thank you. 2 quick questions, one of which you've half answered. I was going to ask you to comment on sonic drilling and continuous coil tube drilling.
Oh, yeah.
You've done half of that. And then my second question is, what stops the air when the dual tube RC? What stops the air coming up the annulus of the hole?
Okay, yeah, I didn't talk any detail about that, Pete. In any RC system, there, just behind the bit, you have what's called a shroud. And the shroud is almost the same size as the drill bit. So, for example, if you had a 127 millimeter drill bit, you'd have a shroud that is about 124 or 123 millimeter. And so it causes there's a pressure drop, and it's easier for the sample to go back up the inner tube than to go up the annulus. So it almost acts as a seal, if you like. It's a critical part of that RC system, of that downhole system. It's what's called a shroud or a skirt that fits behind the bit.
Okay, thanks. Any comment on continuous coil drilling?
Look, that is exciting. The Aussies are doing it at the moment. I would give my right leg to go and see this, but it's all still very secretive. Yeah, I can't. We just haven't enough time to talk about the technology behind it, but it's very clever. Please, if you get to see it, tell them I'll come along and carry your briefcase. Okay, I would dearly love to see it. Yeah.
Thanks, Colin.
Guys, I'm sorry, we're gonna have to leave it there because I don't want to step on anybody else's time. So thanks, guys. Thanks again for joining us, and thanks, Tanya. We'll chat soon.
Okay, guys, thank you for that. Colin was speaking about various courses that he gives, and I just wish to share a screen here for a moment. If you go to the GSSA events page, you will see this course here. It's the online course that he still gives. looked under more information, there's contact details as to how you can get in on this course, and also the various other courses that Colin gives online as well. Okay, folks, well, welcome back to the next session. And with us, we have Heino Woops. Heino is with Imdex as their operational manager for Southern, East, and Central Africa. Heino has over 30 years experience in drilling fluids. You can read his bio in the document that you have. And so, Heino, over to you for the next hour talking to us about drilling fluids. Thank you.
Yeah. Thank you, Tanya. Morning, everybody. Just so that you can place the face and the voice together. If there's maybe some issues with internet connection, I do apologize. I'm currently traveling in Namibia. However, if you want to jump in or ask a question, I don't think I will be able to see any hands. But please just go for it. Or you can wait till after the presentation and then ask any questions. But you guys are more than welcome to ask questions. Morning, everybody. Like Tanya said, you can have a look at my all the wording under my name. Today, I'm going to spend a little bit of time by introducing you guys to drilling fluids in exploration drilling, and mainly we're going to focus on diamond core drilling. You can use drilling fluids in any type of drilling, but I think majority of drilling currently happening in South Africa for exploration is core drilling. So just in short, what does Imdex do? What solution sets do we have for you guys out there? Is drilling optimization products. Like I said, we're just going to focus today on drilling fluids, the AMC range, a little bit of the solid removal units, and some other equipment we have in the drilling optimization space. Then it's rock knowledge sensors. I think you guys are well familiar with the downhole survey instruments, the core orientation tools, structural orientation centers, and so on. And then also real-time data that we have to offer. But like I said, I'm just going to focus on the drilling optimization or drilling fluid side. Just in short, as you guys can see, guys and ladies can see, Imdex is fairly spread around the globe. We have presence in 27 countries. Imdex in South Africa or in Africa specific. Our head office is in Germiston. That's where our warehouse and our manufacturing plant for the drilling fluids are set up as well. And then we have a fully functional Ghana office in West Africa, and the Ghana office is looking after West Africa in total. Let's dig into the stuff while we are all here for this hour. What is the definition of a drilling fluid? A drilling fluid is any medium circulated down the hole while drilling taking place to remove cuttings and to extract information. So this type of drilling includes air drilling. This is now your normal RC drilling, air with water, polymers or foam, water-based fluids, oil-based fluids, and synthetic-based fluids. So what fluids do we use? We use the water-based fluids. Oil-based fluids are mainly used in oil and gas operations, and that is really expensive. Excuse me. So, why do we have to use drilling fluids? It's not just a matter of putting stuff into the water, put it down the drill rods and turn the rods, and there you go. Drilling fluids plays a massive role in productivity. In order to get down to TD, total depth of hole, in order to achieve all the objectives set by the end client. It also helps to drilling through very difficult geological formations. It improves downhole conditions. It prevents tool losses. It does have an impact on drilling cost, but the drilling fluids mustn't be looked on as a cost. It must rather be looked on as a useful tool to assist the drillers to get to those objectives that the client's US client set out for them. Drilling fluids have an impact on the total of drilling operations. It's only between 30 and 60%. So that is why, it's so important to focus on drilling fluids and not just think of drilling fluids as stuff that we chuck into the water, like I said earlier, and pump down the hole. There's a whole lot of primary functions of a drilling fluid. Number one is definitely to maintain wellbore stability. I'm not going into too much depth on lithology and types of formations we're drilling through, but you do get formations that's really water sensitive, and we need to counteract those water sensitive formations to get down to TD. Other primary function is removal of cuttings from the wellbore. If we don't remove the cuttings, you won't get the hole down to TD. So another very important function of a drilling fluid is to minimize the impact that it have on the environment. It also assists by cooling and lubricating the bit and the whole drill string at the end of the day. One can just imagine if you're drilling a 3,000 meter hole, that hole is not going straight down. It curves and goes into all different directions. And for that, you still need to lubricate the rods so that you don't have too much high torques. Too much high torque can cause us a lot of other problems. So for us as mud engineers, there's a couple of properties we're looking at when we're mixing drilling fluids. These properties are very, very important for us. It tells us a story of what's going on down the hole. And, we also set these properties before we start a new hole. But I'll get to, I think there's another couple of slides we need to run through before we get to that. So what is these properties? And I'm not going into too much depth. I just would like you guys to understand, why we use it and what we're looking for. So the first one is viscosity. In short, it's just, the thickness. If you put a polymer in the water, that polymer has a lot of other functions, but it also makes the water thick. That is viscosity. Another property is density. A very, very important property is rheology. There's a couple of tests that we do, and I'll run rheology a little bit in depth with you guys. Then filtration control, sand content, and then very, very important is water quality. So just in short, viscosity are measured by that picture on the left-hand side. It's a Marsh funnel, and it's a cup. So if you fill the Marsh funnel up with clean water and you release that and take time to fill up a 1 liter empty bucket, the viscosity of water is 28 seconds per liter. It's just to give you an indication. So once we set up a mud system, we will check the viscosity, and depending on what products we add to the water and what quantities, the viscosity will go higher. So in normal drilling conditions, we're looking at the viscosity of plus minus 33 seconds. That will give you hole cleaning properties. And this is only when you're drilling in nice solid rock. The second one is rheology. So that is the rheology hand crank item we use to do rheology. So there's three main points that we're looking at rheology. The first one is plastic viscosity. The second one is yield point, and then the last one is gel strength. I do have a slide going down just to explain a little bit more what is plastic viscosity and why do we look at plastic viscosity and why do we look at yield points. Then the mud balancer, that is to check the weight of the mud. Why do we need to check the weight of the mud? If you're drilling in a very sandy formation, you do take recordings of this mud weight. In normal practice, just to give you an idea, a normal mud system will give you a mud specific gravity of anything between 1.01 SG to 1.03 SG. Should you're drilling sands and you haven't got proper settling systems, that mud weight will go up, and it will go up to a 1.05, even to a 1.08, and this might cause other problems for you in the hole. So that is why this is also a really important tool that we have in our kit. Then filtration control. Filtration control, we test via the apparatus on the left-hand side. It's called the filter press. So when you're drilling in very sensitive formations, there is a part of the water that will penetrate into those sensitive formations. So we need to cut down on that penetration. And that's why we need to do a filter press to see how much fluids do we lost into the formation. Again, just to give you an idea, we recommend 14 milliliters in half an hour's time. So if you run the filter press test and that 14 goes up to 20, it tells you a story that you need to add some product into your system because you need to cut down on that filtration control. If it's up to 20, there's a lot of water that goes into the formation that will also give you some headaches, especially for the drillers. Also very important is sand content. You don't want to get your cuttings out of the hole and put it back into the hole. So with the sand content, we do check that. And should that be the case, it's either that your whole surface system are saturated with sludge or with cuttings, or your surface system is not proper set up. Viscosity versus rheology. So the plastic viscosity gives you an indication of how many solids you have in your system. So again, the higher the number you get, the more solids you have in your system. So now you can go back to your sand content, you can go back to your viscosity and your mud balancer. And if those numbers are also high, then you really have a problem. A very, very important factor of rheology is yield point. Everybody thinks that the thicker the viscosity, the thickness of your mud, the better hole cleaning you get. It's not true. It's not true. Rheology this is where rheology comes in. So the yield point tells us how good do you clean the hole. So there is a calculation that the mud engineers will do depending on hole size. So before we set up a mud system, we will get the hole sizes, we will do the calculation, and normally in a 96 millimeter hole that's into, your yield point must be roughly around 5.5. So then we prepare a system and decide on what polymers we're going to use to get you that yield point in order for you to get all those cuttings lifted from the bottom. Then a very, very important thing is water quality. So water quality plays an enormous role in the performance of drilling fluids. It's always very good to test the water before you start doing any mud mixing. So you guys will hear I sometimes use the word mud. It's just a quicker word. I normally it refers back to the drilling fluids. It's just a term that we use in the industry. So in the water you have calcium and magnesium, and there's other heavy metals that also plays a part of how good your muds will go into the water, and then also the chlorides. So first of all, we will check the pH. That is very easy. Everybody's familiar with pH. So we do it. There's a lot of different products on the market that we use to check pH. But for our products, for the AMC Index product range, anything between 7 to 9 is good. Should the pH be a bit lower, there's a lot of products in the market like soda ash, a water conditioner that we manufacture to lift up those pH. Then total hardness. So anything that's calcium and magnesium above 400 ppm. Some of the products will not yield that quickly to the water. It will take some time, and then also you will use a little bit more to get polymers and lubricants into that water and to get to the right properties. However, there is products on the market like soda ash to precipitate the calcium and magnesium out, as well as the ANC water conditioner. Another big headache for our guys in the field is chloride, salt. Unfortunately, there's nothing that we can add to the water to precipitate the salt out. Anything above 1000 ppm is not good. However, Index does have a product that can even work in seawater. It's called Zandvoort. You will use a bit more than normal, but at least you can get that in. So I'm not a chemist, so please spare me if there's any chemistry questions afterwards. But just in short, polymers. Why do we use polymers? It improves the pore recovery. Polymers are much more powerful than bentonite. Polymers are lightweighted, easy to transport. If you work with polymers, it also gives you a solids-free mud system, like in the case where you will do bentonite mud systems. Bentonite is a clay, it's a solid, and that particle stays in your system all the time. So for us at Index, there's three polymers. It's your natural polymers. It's like the Zandvoort that can work in seawater. Then you have your semi-synthetic polymers. We use that quite a lot in the diamond drilling industry. And then also your CR650s and Cap 21s. That's quite familiar products that we also use in diamond drilling. When a drilling contractor come to us and tell us, he would like to have a mud system, it's not just a thump suck. There's a lot of questions we ask, a lot of things we need to get in order to prepare a proper mud system. So again, it's not the thump suck, and it's a nice to have a thick viscosity and a couple of drums that's on the side. It's very important for us to understand the geological and lithology on the hull. And if you guys can see here on your left-hand side, this is not all the Imdex ANC products. It's mainly the main products that we normally use. And so depending on what formations we're going to drill, we go to this chart and then we look at what properties do we need. If there's any clays that we're going to encounter or shells that's water sensitive, then the mud engineers know that we need to have encapsulation, we need to have inhibition, and then sometimes we even need filtration control. So then we will make a call whether we're going to use Corwell or whether we're going to use CR650. So this chart on the left-hand side is just to guide us through all the questions we need to get on the right-hand side. And once we've got all of that, then we will do a proper proposal with our recommendations. With those recommendations goes the mud properties. So we will tell the drilling contractor for as example, your pH must be between 7 and 9. Your viscosity must be between 35 and 38 for argument's sake. When we drill really bad formation, we will have a mud engineer on site, and then we will do the rheology, because that's a specialized piece of equipment that you need to understand how to use it, how to read the numbers. But again, it's not thumbsuck. We put it out there on a piece of proper paper and present it to the client. Then from Imdex side, it's not just about drilling fluids. It's a whole circle. If one link is out of the circle, you might not get down to TEDI. You might not get proper core recovery. So there's a couple of engineering factors that plays a major role on getting the information out of the hole and getting down to TEDI in a timely manner and a cost-effective manner. So one thing that we looked at when we're on site and when we do visits on site is to check the pump volumes. One would think that if you pump a lot of water down as quick as possible, you will really get good hull cleaning properties. You will not get good hull cleaning properties because you will get a turbulent flow in your annulus. So the annulus is the space between the outside of the diamond of the rods and the inside of the hole. That's where your fluids will go up to surface. That's called the annulus space. So these recommended pump rates are not set by Imdex. That's been set by drill bit manufacturers. Very, very important to pump down the right amount of water down the hole to get all the properties you need on the fluids. The hole cleaning, you don't want to pump too much water when you're drilling in very sensitive, water-sensitive formations, because you can start washing away those formations, even if you have the right drilling fluids in the system. This is one of the links that's very, very important in the whole process to get down to TEDI. Very important is mud mixing, especially when the guys are using powders. Powders need some sharing before it goes into the water and hydrate proper. If you don't have proper mud mixing equipment, you will find if you go out on the site, there's a lot of lumps lying on the surface, and then normally the driller will tell you, product is not working, but half of the product is lying on top of the surface. It's not mixed in. So mud mixing also a very, very important tool in our RCO. We do have a solid removal unit, or we have a couple of solid removal units. As you can see on the left-hand side, that's normally how most of the drilling sites look like. Nothing wrong with it. But using a solid removal unit, you can cut down on the site layout you can have a more or less picture like on the right-hand side. What does this ultra lightweight solid renewable unit look like? In your left-hand side, you can see it's towable. You can use any UV you want. Toyota, the Ford. Normally, Toyotas are doing a little bit better than the Fords, but nevertheless, we will not go into that depth. So, as you can see, you will reduce water consumption up to 80%. Why? You don't need to have all those surface volumes to have good settling systems, because the SRU is doing all that for you. It also reduces drilling fluid cost. In a way, we shoot ourselves in the foot, but we're also there for the environment and for the end client to try and save cost where we can. Why do we say we reduce on drilling fluids? Again, you don't need all those surface systems. Just to give you an idea, back in the 80s, when there was a lot of people drilling in South Africa, we were looking at surface systems of 20 to 30,000 meters at surface. With the ultra lightweight unit, you're looking at 10 to 15,000 meters. But as you can see, there's a lot of other benefits that you can get out of the ultra lightweight SRU. Another piece of equipment is the AMC Boss tool. It's a Chrome Active downhole solution, especially when you're drilling in very friable formations. It's not a grout like in cement, but it saves you a lot of time, can save you a lot of time. And when you have minor seepage losses, so in other words, when drilling fluids is going into very fine cracks in the formation, you can seal those cracks off with the AMC Boss tool and AMC Boss Fix. So then it's not necessary to grout these holes. Then we also have the AMC Mud Kelp. You can go to your Play Store and you can download this app for free. What you can see on your screen currently, the annular volume, the tank volume, it's just part of all the calculations this app can assist you with. Very powerful and almost a need for anybody on a drill site. I would just like to briefly to introduce you to a new range of products that Imvex came up with, part of the old traditional AMC products. It's called X-Form. And I'm not going into too much depth, but X-Form is a multifunctional drilling fluid. What is a multifunctional drilling fluid? It is one product that gives you a whole lot of properties. So you only would need to have one product on site to do almost all the drilling to get down to dead end. It eliminates drilling fluid product waste. It's a one sack system. So you only have one product on site. We try to make it very easy for the people that works with it. So you can just think for yourself cases where you would need to have 3 or 4 products that you need to mix in. And believe me, sometimes you need to have all those products to get all the properties out of it. Now you can solve that problem with only one product on site. It is commercialized, but saying this is that you will not use this product, this multifunctional product on each and every bore that's being drilled. It's also selective bores with, if I can call it that, lithology to go through, that this product will really assist in making life easier for any driller, any end contractor at the end of the day. So this brings me to to the end of this presentation. You guys are more than welcome to email me or give me a call when you come across any problems on site. If I don't have the answers, and believe me, I'm still learning after 30 years. If I don't have the answer, we will get you the answer, and we will get you the right product to get your information out of this route. Thank you so much.
Thanks very much, Heino. Are there any questions? I see there's something in the chat. I think everybody's interested in the app again. Would you like to tell them more about it and repeat the name of it a couple of times, please?
Yeah, it's called the AMC app. So if you go to, well, I've got now I'm still most probably old school, but I've got a Samsung phone. You just go to Play Store, and I just want to get it, then I can walk everybody through it. If I can just get to my Play Store, I get this. So then you can just type in there at search AMC, AMC app, and then Mud app, and then you can just download it as needed. Just go back.
Search AMC Mud Calc. AMC Mud Calc.
Thanks, Kev.
There's a question that just came in, I know.
Yeah. In a situation where you continually lose mud down a hole, how do you fix that?
All right. Oh, very, very, very good question. So the last thing one wants to do in a case like this is to grout the hole. But now, depending on how big the fracture is, will depend whether we can close it down with what we call it as lost circulation material. So we do have products that you put down the hole. These products goes into the crack or cracks, and then it will expand over time. But remember, it's not rigid. So over time, it will wash out again. As water passes by, it will wash out again. So in short, yeah, we do have products that counteract those problems. If the crack is way too big, then you will have to grout it with cement. If it's a seepage loss, like you lost about 20% of your fluids, then it tells us that it might be a seepage losses, and then you can use the AMC Boss tool to do that. Like I said, cement is the last option. I hope I've answered that your question, Estelle. Sure.
Anybody else?
Estelle, yeah. If the cement also disappears, then if possible, depending on what size you're currently in that hole, assume you are drilling HQ and this happens, then you can run down a casing and you can go over to NQ. Or you need to drill blind. If it's a deep hole, even with shallow holes, if I say drill blind, there's no circulation coming back. That's what I mean. It's not good to drill blind because you don't know what's happening then down in the hole. What we then normally will do is we will start, if we can't get the loss, the circulation back even after cement, you can't run casing down, you can't step down to a smaller hole size, then we start cutting down on the products in order for the cost not to go sky high. Remember, if I can use examples, if you drill the hole and you encounter the problem at 100 meters, it's always good to treat it right away. If you drill further, then, and you can't get it closed, Then you need to put packers down the hole. There's a lot of calculations that you need to do, and then it becomes a big problem. But even if you come to 100 meters and you drill 3 meters past, you can't close off, you can't step down to smaller size, and you drill further. Remember, as you drill further, all those cuttings still needs to be lifted from the bottom, and it will go into that fracture. So you still need to have a polymer in your system. You still need to have lubrication, but then we start cutting down on these drilling fluids. You might find that people will not drill with a lubricant. They will rather put rod grease on, or they will rather go with a biodegradable liquid rod grease, and we will cut down on the polymer use as well. In terms of drilling HQ for bulk sampling, I encounter a lot of mud cut. Okay, so if you refer to mud, I believe it's the sludge that you refer to. It's unfortunately you used the wrong muds, but I believe your surface system was not proper set up. So what's happening here is you start pumping down sludge into the well again. So there's a lot of variances that can cause this, but definitely it's a sludge problem, and I would rather think that your surface system is not proper set up. You're pumping sludge back into the hole.
Okay, well, I know. Thanks very much again.
Tanya, thank you so much. Much appreciated.
Okay, so we now move on to lithological logging. And for that, we have Masi Zintwana with Anglo American. And as is quite often the case with somebody who's working on a mine, things happen. So Masi will join us a little later. In the meantime, we're going to start a recording of Masi's presentation, and as soon as he is able to log in, he will continue on live, and he hopes to at least be with us to be able to answer any questions.
That you want to interact, please raise your hand. Then we take the call and the question at then one. So the intention for me largely that is not to necessarily talk for the 2 or so hours, but to basically have an interaction to some extent. So we will have some context that we need to set in the discussion about why are we doing this. Then drill management and a lot of these aspects are things that Colin already touched on, and some of them in the previous talk. I know in terms of what considerations you need to take. Then the drill methods QC. And this will focus particularly around core logging and things that is the largest part of this talk. The logging itself, and then some parametric considerations. And this for me is probably the one differentiator as a geoscientist that you need to keep in mind. And the last part is just beginning with the end in mind. Before we jump into it, and as Tanya said, I am an employee of Anglo American. I am also a fan of the GSSA and registered professional scientist. Even though participating annually in this event for me is sponsored by the employer and giving this in my personal capacity. So anything I say is not and should not be taken as a comment that is attributable to my employer or the GSSA or SACNAS itself. I will try and be honest with the talk. So before we jump right into it, may I request that you either scan or jump into the forms of this. And as we go along, please, we will come into these questions that I need you as an audience to reflect and answer. It takes about a minute to complete the entire survey that I've put up there. But as we go in, we will touch on
on these questions that I put in there. And obviously, you see there's already one response when you get in there. That's what I reflect as the day I started working, what I would have wanted to know about personally, that is about logging. So feel free to put your answers. And the first consideration, I think, right up front is, what would you want to know about logging? If logging is not something that you already are doing or knowing, even if you are knowing and are logging professional geo, are you comfortable that what you know about logging is what the intention of the exercise is? So jumping then right in, and I'll come back to the answers as we go along, is setting the context. Just move this. In establishing why you do the logging, it's all around the concept of reasonable prospects of eventual economic extraction. And this is now applicable particularly to mineral resource management. Other forms of drilling would have a different framework of managing. And the key aspect in this part is the relationship of what we call mineral resources to mineral reserves. And as you go about your drilling campaign, for whatever the reason it is, with time and more drilling, more logging, and eventually modeling, you're increasing your geological or geoscientific confidence and reporting in situ mineralization and estimates. With application of modifying factors, and assuming now you have a reasonable prospect of eventual economic extraction, the consideration is around modifying factors that talk to your mining, metallurgical processes, infrastructure, socio-economic factors that impact your ability to extract the commodity with which you are planning to do, and applying that into your resource statement essentially gives your mineral resource. And what that means is, much as we understand that mineralization and ore bodies are 3D entities, it's a careful and delicate relationship that we need to manage between what is a resource and what can you economically extract. And depending on where you are then in the mining value chain in that process, you would have variable considerations of what type of drilling you want to do. Most of the talks that we give in this nature, most of our focus is around exploration drilling, which is about delineating and estimation eventually of economic deposits. And there might be different stages even in there between reconnaissance, the actual prospecting, defining the resource estimation and stabilization campaigns when you want to consider concept studies for infrastructure development, and all the way into the operation of a mine, where you have aspects of grade control variation issues that you still need to drill for. Maybe core drilling might not be the method that you turn to. Might be other options, as Colin touched on this earlier. In some instances, and which is something that's fast gaining traction in this day and age, is something called geometallurgy, which is basically the integration of, let's say, physical properties of the rocks and how they physically behave in your mining and processing processes systems to be able to extract the maximum value in out of the ore body. Typically, most of the grade control do historically would be focusing purely on grade, which is what analytes you're dealing with. But the grades alone does not mean that your liberation and other processing consideration would be optimized. That's where geometallurgy as a field comes in. And obviously, then there's always brownfield, which is trying to keep your mine economically producing as long as possible, and close and on-lease exploration. That's where brownfields would sit, and drill and blast where you need to blast hard rock particularly. You might still need to do further drilling in that space. But again, there might be a couple of considerations of what mining engineers want out of that that you need to take in as a geoscientist. And failing those results, you would need to come back to that. The key thing, though, in terms of why drill to begin with is the fact that anything you see from a surface point of view is largely an XY expression, which is the 2D geological information, a map, a model in plan view most of the time. The third dimension is basically what you want to see from drill core trenches, road cuts, or sidewalls of a pit if you are in an open pit environment. But again, ore bodies are not 2D, they are 3D entities. So the logging aspect fundamentally talks to, in the absence of any of the road cuts or crops and trenches, when you have drill holes and drill core particularly, what is it that you want to look for in the third dimension, in the Z dimension, to complete the story? As I've been saying in the previous slide, you'd see that here is basically a summary of a mineral system. So what is a mineral system? And this is what basically sets your broad scanning view of why you're logging. Is any economic deposit is anomalous in nature, meaning that it's a concentration of a particular commodity metal in a particular horizon in a controlled fashion, which is different from the surrounding rocks. It could be the same rocks that you're dealing with. It could be host rocks, which are fundamentally different information and age from what you are targeting. And the four basic things you are looking for is a fluid and a metal source. Where is the fluid and the metal that you're concentrating generally coming from? How is it moving to where it gets trapped? That's the second part. And the third part, and obviously once you have your concentration mechanism and you're forming the mineral deposit, the excess fluid that has nothing to do with upgrading or preserving your mineralization needs to escape the system. And this outflow in other areas will be expressed as a flushing mechanism. And the idea is if you do not flush, you cannot concentrate behind in enough scale the metal or the commodity you're after. No concentration, no deposit, straightforward. And in most ones where there is a fluid in the form of aqueous fluid immobilized in some sort of plumbing structures, geology structures, there is obviously a fluid-rock interaction. These are telltale signs of what is happening in your local and regional spaces. In the form of tectonics, most of us being geos, you would recall that tectonic events have major influence of certain types of deposits, and you see that you can have convergent, collisional, and extensional tectonic settings. And down here at the bottom in each view is geological time scale from present to about 3.5 billion years back. And you see where supercontinents have been identified to have formed. There is a general concentration of certain types of commodities. And for the case of South Africa, those that are here or in SADC in general, you would want to see, for example, the concentration of IOCG type deposits. In Australia is also quite big on this. Would typically be anywhere in the Precambrian and the Archean. The likes of the Bushveld and the Great Dyke sit in that space, and in some places like Namibia, where porphyry, copper, and gold deposits are becoming one of the things that people are after. It's much younger in the Pan-African ages in the South African or African context. Why is this important? You may ask in the context, because all of it formulates the field settings. And the important thing here is you know what your 2D view is, and you know where surface expressions of what you are looking for as a commodity looks like. And you start off with a view of this nature where you're having delineation of where potential mineralization is and how it looks like in the XY view, but you do not have the picture of the Z axis if you can. And obviously that talks to your stratigraphic section. What you're looking at here in the previous slide is part of the Transvaal supergroup. And showing here is basically where iron or high-grade iron ore is being hosted and the overburden that is associated with that. And the importance of field relations is to know, once you have drill core in front of you, what are you basically dealing with in that drill core, and can you place yourself in that core where you are in the stratigraphic column? We'll come back to the imaging right a bit later again, but it's the same sequence of rocks, if you will, just not sitting in the stratigraphic order, and there's a number of reasons around that. So before we jump into then the drill management, may I just remind you of the plea I already put up earlier, and indicate that there is another question in there, and you'd have seen by now. The question is around just to set me up and set up the rest of the conversation. Give me an indication, and please answer all the questions and go back to the end and just submit what we're dealing with in terms of this question. So just allow me to bring this to your view. Those are the current responses at the moment. In terms of the first question, that's what most of you is saying. Good practices, logging, data, core importance, the impact, technical aspects, and half of our audience at the moment that have responded is less than 2 years of experience. And there's some might be interested in this group of 5 year plus. I know I'm part of that group. I'd be interested in knowing who's in that group. So please do feel free to raise your hand and comment in some of the things I say, and let's have the discussion as it comes up. So as the responses are coming in the background, I will then continue. Drill management. Colin touched quite a lot on this. And in this part of the discussion is basically going to take off what do you do to manage your drill campaign for the end in mind story I was talking about. What that means is, much as you as a geo are not a driller, to get the best result out of your logging, you need to understand what the driller itself and this equipment that you use in your drill campaign does and does not do to your samples. Because it could be very easy that you do not know, you cannot tell, and your interpretations and your logging is compromised as a result. So what you have here is a diamond rig, and it's a platform rig. It's a type of a diamond rig. It's a coring method, and then Colin would have gone into great detail on this. General site layout, and I picked a very old rig for this purpose, is for me one of the few examples I have worked with that shows general good housekeeping. You could be in the middle of nowhere, far from everything, and you need to make it as convenient as you can for the people that are doing the work to get the best out of the results. So if you're not familiar with the drill site layout, the rig itself, the string and the rod, the drill string and the core barrel in the hole are down that part, as Colin was talking to. Lying in front of the rig there is what is called the core barrel bench, and there at the top would be the inner tube that is going to be used potentially in the next run. This is a wireline method. As you can see, there's a thin rope running through the pulleys there coming down, and there at the back, just next to the engine, there's a drum. It's a reddish thing sitting in there. That Y line is a Y line hoist drum, and in there, that's where the up and down hoist system of retrieving samples sits. Important, the previous talk was talking about drill fluids. There you have the old fashioned of making a sump, and this sitting in here is what is being dug out of the sump to make sure that you have optimal fluid circulation. And as you drill and you put your samples in there, you even wash the core. Obviously, you have to put it in the core box, and that's where you are, and you have stash depending on how you're drilling. The tank at the back is just to make sure if your sump runs dry, you have a backup water that you can use on the side to keep your water pump running, because you don't want to run that pump dry, because downhole friction increases, cuttings are not being washed out, steel, rock, all together cook under the friction and the revolutions that the rigs will be putting out. And the next thing, you have lost a hole in samples, which then calls for efficient exercise. Drills come in many designs and forms. And some of the aspects that you as a geo need to also consider are non-technical aspects. In this view, you're looking at a different type of a drill rig, still diamond drill rig, different configuration of the operating panel. And as you can see, problem number one you have to deal with, and you'd heard Colin talk about legal liability. There you are having an operator that is sitting on top of a drum, on top of something else that is a makeshift chair. Legally speaking, an inspector can stop you if you have a site like this. But more importantly, you can see the background of where your drill rig is. It's within a community, and you will be generating quite a significant bit of noise in your drill campaign if you are drilling close to where people live. And being able to execute the work you have to do, you have to be mindful of what socio-economic agreements and concessions you might need to get from the users and owners of the land within which you operate. You would hear most of these aspects in the mining industry space coming up in sustainability reports and in the form of ESG commitments that mining houses make. And long gone are the days where get in someone's backyard, drill a hole, and tomorrow you're mining. All those non-technical aspects are becoming fast and quickly becoming top priorities for many investors. And it's what you as a geo have to set yourself up to pay attention to and make sure that you address. Secondly, for Anglo American, obviously, that safety is top of mind. And I will say this is not an Anglo American site. It is a site that me, myself, and my CEO has worked on in a different project before. How does modern technology and considerations of how to manage site and influence where we're going as an industry? This is a newer version of what is out there in terms of drill rig technology. The previous two ones, if I can just go back, there's the rod handling system and the Y line. Up there would be an assistant manually handling the rods. The gentleman sitting in there would be standing on that wood pellet there and manually handling the drill rods, as Colin was explaining, the hoisting system, and putting them on this stand here in front of the dome. That is a manually intensive exercise. The only help the drill rig gives you is pulling it out of the hole. Once it's decoupled, it's a lifting exercise manually. So to put each 3 meter or 6 meter, however long your drill rods are on these benches. Newer technology, you have automated rod handling capability and hoisting systems that are included in the drill rig. And you can see some of them carry bigger hoist drums for the cable work. And you would think that technology in this day and age means less employment for people. In the previous sites I showed you, you could operate those sites with 3 people, an operator and 2 assistants on each site, and minus the gentleman standing there being a supervisor. You can see this site is operating with 4 people. The one in the background is just an Anglo person visiting the site. the point I'm making here is technology does not automatically always mean reduction in numbers of people that work on your drill site. It is important to translate the message why you are introducing changes, and the changes of this nature are changes that are there to help the people that operate the drill rig and are entrusted with your core samples while the drilling campaign is underway. The second part of the site is you'd see these drums sitting here at the back. These rigs and this setup is one of the initiatives we took that moves away from digging sumps in the ground and runs rather in contained sump systems where filtration runs through a drum. And at the end of the site, the only thing that we left here that showed that we once drilled here is a 1 square meter footprint where the drill hole is, and showing the corner position of the big drill hole. The rest of the land around it would be rehabilitated to the background until such a time where mining, if that's where you're going, wants to take the exploration or the mining value chain goes forward. Obviously, when you do the drilling, you have to bear in mind, are you doing the green or brownfield exploration type drilling? Critical is manage your drill program accordingly, because it's not about having a hole in the ground. It's your roadmap from converting a resource development strategy or a plan to a life of asset plan if the intentions of the business or your client is turning economic. The geology can make or break a project. And this I cannot emphasize enough. You get the geology wrong, your project is dead. Not every exploration campaign, and the conversion rate is generally less than 20%, much less, in fact, of what starts as an exploration project that ends up, particularly in Africa at this stage, as a mine. And there's a number of reasons why that happens, but it all boils down to reasonable prospects of eventual communication, economic extraction, and what you as a geologist communicate throughout the project as value in the ground. And prospective areas and what brownfields the difference is, for those that know, greenfield refers to a completely virgin ground in the middle of nowhere, no mine exists. Brownfield, there is an existing mine, you see an opportunity to expand in a particular direction, and your local geology and field setting tell you that maybe you are onto something, and that informs your trial management. Obviously, drilling is not unique to geology. As I said in the previous slide, it is definitely not about the hole in the ground. And arguably, when you as a geoscientist are part of a drilling campaign, there are two important outcomes you want to get out of a drill campaign. One is samples you can trust, and this is in no particular order. Samples you can trust and always go back to, and all the people that work with you on that drill site get back home safe. As I said and indicated earlier on, most of this is about core drilling, and particularly diamond. Why you want to pay attention to this? Because it is, comparatively speaking, non-destructive to the internal structures and textures of the rocks you're dealing with. And as you can see, relative to what you get out of a chips sample, you can still see the relationship of all the textures in the core sample, and you can see the original lamination in this piece of core sample. So if you drill something like percussion or dual tube reverse circulation, as Colin was explaining, you'll be destroying all those internal structures and textures you want to capture. It is also your opportunity to get the most representative sample of the in situ rock features. Remember, you are not logging for the core itself, you are logging for the ground within which you drilled that core from. So whatever you're describing needs to be as representative as possible of the XYZ of where that drill hole sits. It is, however, time-consuming and relatively expensive when you consider the other drilling methods. Much as the rotation speed is possibly the highest in diamond drilling compared to the other methods Colin was talking to earlier, the rate at which you recover the samples is actually even slower. And because of its slow and the expensive nature of the equipment, it is cost intensive. And to achieve all of these top four, obviously, it calls for regularly checking in on your drilling quality, because this talks to what you would call a sample representativity index. This becomes very important when you transition into the discussions of mineral resource evaluation and knowing that what your target rocks at depths are, not the depth of the hole, what target rocks are in. So you could very well design a borehole for 250 meters and end up either finishing that hole with 850, or worst case, even much closer to 500 plus meters deep. So you're not drilling for depth, you're drilling for end of mineralization, if you will. And you need to know very well what your regional and field settings are guiding you towards that. And that's why this aspect of drill management is important, because it's not logging itself, but it is a methodological approach to making sure when you do essentially do the logging itself, you are capturing the most correct version of events representative of the ground X, Y, Z within which that goal comes from. Going to get core samples, obviously, from your core drilling exercise. And this table just shows these types of core sizes, depending on the diameter. The one you want to pay attention to generally is the metric system. And for normal exploration, you typically be between the BQ and NQ hole, depending on what purpose that hole will be serving. And the core diameter you're looking at fundamentally, especially in the JSE and SAMREC code space, you're aiming for about 5 millimeters of core sample. The whole diameter you're dealing with, you can see, is much bigger than that, relatively speaking. And these are the annular thing that Colin was talking about to make sure that your circulation system is functional. Your metallurgical core samples typically aim for the bigger core diameters. What I do want to highlight to you, as you can see, the whole diameter of an NQ size is big relative to the core you'll retrieve in this case, because the assumption here is you are dealing with a wireline drilling methodology, and the curve you can use there, if you remember what curve is, as Colin was explaining, is much thicker and your sample is thinner. It is an opportunity, if you are experiencing problems before abandoning the hole and understanding drilling, I assist you as a geo to know that because I have a particular hole in NQ, in that particular hole, if I switch and I do a conventional at the HQ size, I can retrieve bigger core, keep my hole diameter relatively comparable, and advance past the problematic area by simply changing the curve of your drill bit. For various reasons, you might want to do this. That allows you the opportunity to advance through adverse and problematic drilling conditions, such that you do not incur unnecessary expenditures and not retrieving samples, and in the process frustrating your drill service provider if it is contracted out. If you are managing a drill campaign on behalf of a client, you do not want to frustrate the drilling guys and at the same time incur costs on behalf of your client. So understanding that entire exercise is important. Colin did touch on the cost implications as well. And this just shows a real case that I've worked on. I've obviously removed the financial figures here, not to raise eyebrows in this discussion, but the profile is representative of a case. Between concept and post-mining rehabilitation, you need to be considering what your cost movement is going to look like. In your exploration space, you are building up costs and no returns, but those costs, as intensive as they are relatively minute considering what you will be incurring in a full-blown exploration. Because in here, you are still validating your target generation. Once you start the actual exploration, your costs for drilling climb until such a time you can hand over to mining, where your need for drilling might slow down, but it does not completely disappear. And this, for me, is the important bit for GEOs. Most GEOs would be doing exploration and logging and early drilling and logging for the first 2 arrows, if you will, where you want to get to the answer as quick as possible. And there is life forgotten that comes after your R&R statement. So bear in mind that you will be expected to give insights, whether through your original log or additional comments later on in your mine value chain. So do prepare and set yourself up to have those answers. And somewhere in the life of asset plan and budget processes that your business and your client might be running with, that you do highlight upfront what sort of costs need to be taken into consideration for continuous data accuracy and all body knowledge to set up the operation for the best success. And obviously, when it starts closure discussions, it even drops further the need to drilling, because at that stage you're winding down operations. But you might ask yourself, why is this kink there? As I said, this is a real case. This is the brownfield exploration coming in to say we realize that with changing economic and socio-political conditions, there's an opportunity in this particular area to expand the operation. You want to invest. And articulating that investment very well is very important for accountants and mining engineers, because that's what guarantees you the time to do the drilling and the money to actually do it. Andrew Smith, as I share my screen again, you put quite a detailed comment. Do you want to perhaps unmute and let's talk about it?
Yes, I'm happy to chat about it. Just commenting on something I saw in one of your slides, and it's something I've encountered in conversation with people a few times, is that there's often a perception that mapping data and surface data is only a 2D product, which I think lets many people miss out on actually fully making use of the geological information.
Most certainly, and I think it is a very valid point to make. Good starting position, if you will. And the key thing, I think, for me in that discussion is, if you want to put a drill rig on the surface of the Earth in a specific geology targeting a specific commodity, it is very important as a GEO, especially while starting out, effectively experience one, to understand where and why you're putting that project, because you need to be certain of what answers you are looking for. And those answers must be answers you couldn't get otherwise from good old mapping.
Yes, for sure. And I think obviously the benefit in this type of scenario is that what most mappers never get to do is while they can develop a 3D understanding, based on their interpretation, they never necessarily get, or they often don't get to check that understanding or get to test the model they come up with, which is obviously, if you put the drill rig there, you can now really test your understanding of the geology further, because you're getting all of the subsurface data.
Definitely. Okay.
I really appreciate that comment, and it's certainly most valuable. So please, if as a GO you do conduct logging, do keep in mind why are you doing it, and certainly it's because you've drilled away almost.
Guy Fremantle. Okay, so now moving forward, looking at downhole surveys. And with us, we've got Kevin Paper from Index. And Kevin is a mechanical engineer who has been working in business development and exploration for many, many years. So, Kevin, over to you.
Thanks very much, Tanya. Welcome everybody. As Tanya correctly stated, I've been in the surveying industry, exploration industry, for about 15 years. Prior to that, I've been in general industry. I've put together this presentation. I'm talking largely to a presentation from Vanig and our product manager, Lee Webb, overseas. But it's got a lot of very technical stuff in about how gyros work, and yet I don't think that's extremely important. There's some other things that I feel are more important, and I'll highlight them as we go along. More important for geologists on the ground, the QA/QC around survey data. So I'll focus more on that and less on the technical stuff. I'll breeze through the technical stuff. There's a lot of information about different gyros and how they work, different types of gyros and how they work on the internet. Easy to go research them, but it's not really important. They're just different levels of gyro, and they work in a slightly different way, but the principle's the same. So the content here is going to be, why should geologists have basic knowledge about downhole surveys on site? Types of downhole survey tools, different types of downhole survey tools. Then we'll talk about gyros and north-seeking gyros. Survey accuracy and precision. What is the difference? What is the cost implications? When should I use a north-seeking gyro? What sort of applications? And how should survey data be presented? And what does that mean? And you know, what do you look for to see whether it's good? I'll give you some pointers to set up a site so that you get good quality data coming in, and you're always ensuring that the tools are of good quality, no matter the brand. I won't even focus too much on the future of gyros. We don't even know what that is. It's advancing so quickly. So why should geologists have general knowledge of why we need surveys? Because the ore body needs to be where you said it was going to be. You know, everything is tied to the boreal. If you don't get the position of that ore body in space correctly, it's got all sorts of downstream problems. In that you would begin mining, and the ore body is not going to be where you thought it was going to be, and then to change the mine design or the development is going to be really, really expensive. So it's very important to get this correct in the first place. You know, imagine if your ore body was 20 meters away from the position you expected it to be, and you're down there developing the mine. It's really problematic. If you were doing a single shot, and this is why we propose a lot of data points, if you were doing single shot and you only did one survey, one at collar and one at depth on 1,000 meters, a 0.5 degree error at the surface will give you 8.72 meters at 1,000 meters. So you can see what implications this has in setting up walls correctly and in surveying correctly. This is all real technical stuff, and you can. I'm happy to share this presentation afterwards, and you can go through this stuff. But essentially what it says is, if you don't get the survey right, your thickness of your ore body, and where your ore body lies is going to be incorrect. So the errors it can cause. So as you can see here, let me just get my pointer out here. Laser pen. As you can see, this is the space we're playing in when we exploration. This is the space we're playing in, and we need to get this all right. You know, you get higher end gyros, and then you get gyros that are in some structural logging tools. And I'm sure Sarah is going to talk a little bit later, perhaps touch on digital structural logging tools. So, you know, they lower end gyros, but they're still gyros and accelerometers anyway. So when we talk about scale of economics, so, you know, there are tools that are in every sort of segment of the market. We've got lower end magnetic tools. We've got higher end north-seeking tools, higher end north-seeking continuous high-speed gyros, and they're all for certain applications and for certain levels of what can we say, certainty around the data. So you may not necessarily use a high-end tool for certain applications, but you may want to use it for other. And then you may want to use a gyro for an application where you want high speed, so that you can hand drilling back to the hours back to the drillers. So it's really important for the geologist to understand what he's looking at, what each technology gives you, and then make those choices around that. One of the things that we found lately that's influencing and throwing a bit of a dark cloud over just making the right choice is that there's a lot of shipping and freight requirements around batteries nowadays. So some of our tools have got removable batteries, not rechargeable batteries. So the minute the battery is within a tool, it's considered to be in a pressure barrel. It's safe to fly. Any spare batteries now become a bit of a concern. So what's happening is now some tools that use batteries that are lower end tools are having to be replaced by higher end tools that have got rechargeable batteries in the pricing pressure barrel. Sorry, I've just got a message coming in. Let me just ignore that. So if you look at the pricing of tooling and gyros in comparison to lower end magnetic tools, it's minuscule compared to the money that you could be wasting on redeveloping the mining phase. And in fact, when I talk magnetics, you'll see that it could be minuscule compared to the money that you're saving using a magnetic tool to a North Seeker as you go deeper down a borehole. Explain it a bit later. Okay. So it's not just for planning or exploration level. We and other manufacturers are also providing north-seeking gyros now for blasting the drill and blast space to ensure that we get the blast right. So what's happening is drill holes never go where drill holes are meant to go. And if they deviate and you blast and you need secondary blasting or you've got dilution, you are pushing the costs up. So the more we can get accurate data about surveying boreholes and charging those blast holes correctly, the better for us in saving money. So it's also moving very quickly into the blasting arena. So I just need to add this: technology is not everything. The more data points we provide, the more confidence we have in this data is what counts. So, you know, it's no longer of any use if you've only got 10 data points in a borehole. You need as many data points to give you, the geologist, the confidence that you need that, number one, the tool is operating correctly, and number two, that it's a true reflection of what's happening down the borehole. So with the latest developments in the market around continuous gyros, high-speed gyros, they give you the ability to run at 150 meters a minute. And in some cases, we've got gyros that can run vertically 150 meters a minute, where traditionally you would have had to do a multi-shot survey. So when you're doing a multi-shot survey on a 1,000-meter hole, it could take you days. And with a continuous gyro, it will take you minutes, hours. And you can set that so that it gives you survey intervals. So you can set it at 3-meter survey intervals, 6-meter survey intervals, etc. And building a database of as many points at one particular point that you can. And if that's repeatable, you've got good data and you can make a choice from there. Did I go move on? Didn't move on. So let's just run into types of downhole surveys tools. So you get magnetic survey tools. This is more an entry-level survey tool. You get reference rate gyro survey tools, and you get north-seeking gyro tools. Magnetic survey tools, they are very good tools. They are trustworthy. They use the magnetic field of the Earth to determine what the azimuth and the dip of the tool is. Obviously, accelerometers to determine the dip. So it's made up of a board with magnetometers on and some accelerometers on. So it gives you the dip of the tool, and it gives you the azimuth of the tool, magnetic azimuth of the tool, through the magnetometers. So it uses the magnetic field of the Earth. It's age technology, but it's extremely reliable. It has some downside in that you have to. It's influenced by steel, so you cannot survey within the rods. This is number one. And if you're going to survey at a predetermined survey interval, let's say you were going to survey every 3 meters, you would have to pull the rod by 6 meters every time you get to the next 3-meter interval survey point. You pull the rod by 6 meters. The tool is mounted on the end of aluminium rods, which are not non-magnetic. It goes through the bit and you survey. Then you pull the tool out and you then put the drill string back at the point that it was, and you continue drilling. So you lose a lot of time in survey. It has its place in that up to about 300, 400, 500, let's say 400 meters, you would not gain as much by using a north seeker in this environment. So you could still use a magnetic tool. So if you were doing boreholes up to 400 meters, it's still economically viable to use a magnetic survey tool and go through the pulling back of the drill string every time you want to survey. And then at the end, you do a end of hole multi-survey. So it's used in low confidence initial exploration, and it can only be used in non-magnetic ground. So in kimberlites, etc., you won't be able to use this technology, this lower level technology. As I said, it gives magnetic north, and it needs to be converted or presented in true north. And we sometimes have issues around clients not understanding the difference between true north and magnetic north. So it can cause confusion. Some of the tools, as you will see later when we talk about data presentation, can be used in a cloud environment, and you can preload all the parameters. So in other words, you can load what the magnetic offset is. So it automatically reports in true north. But not everybody has that ability to do that. A reference rate gyro is the next level up. It's sort of like the segment is between a north-seeking and a magnetic tool. In this case, it's a gyro, a reference gyro, that you have to give an azimuth. Now, depending on the level of confidence that you want or accuracy that you want, you could set this up using traditional methods. So the gyro needs you to input an azimuth. It calculates the dip. The dip is accurate. It works off accelerometers, but the initial starting azimuth needs to be input. What it does then, it calculates any movement from the initial azimuth that you put into the tool. So the downside of this is that if you get this incorrect, could be finger problems entering the data. Instead of putting 90 degrees, you punched in 190 degrees. It will plot the direction of the hole from the error that you created by punching in the incorrect number. So you can use traditional methods by putting out pegs and lining up the azimuth and lining up the tool and saying, okay, that is the azimuth that we've got, and we entered that in the azimuth. Or you can use it with a rigger liner. Rigger liners normally have got much higher end gyros mounted, and they will give you a true north azimuth that you can input into a reference rate gyro. So if you had a project of 20 rigs, say, and you wanted to have sort of a mid-range gyro, you could do a TN14. You could have one TN14 on site or a rigger liner on site. You can then use that to line up your rigs, and then you use that lineup or collar capture to enter into the reference gyro. And all it does is it calculates the survey from that point on. Another downside of a reference rate gyro, older tech, not so much the newer ones, is that if one station failed, all the other stations will fail because it relies on the previous station for accurate reading. Latest reference gyros, where they employ some sort of drift correction technique, we are able to get around that by orientating the gyro down the borehole. It will prompt you to do that. So most of the older tech market today uses mechanical detectors, and the north-seeking gyros take over. So we, north-seeking gyros now have become the flavor of the month, and for obvious reason, there's a lot of benefit around using north-seeking gyros. So they are not affected by magnetics, so you would not need to pull any rods to survey. You can survey within the rods. It uses the Earth's axis and rotation speed to calculate position. So generally, a north-seeking gyro would want a very accurate latitude. So this is something that you have to be aware of as a geologist. You have to be ensure that the latitude is correctly reported on the drill site or provided through a cloud computing system so that the tool reports the correct latitude, and in so doing gives you the proper azimuth and dip. Most tools, if you use the tool on a latitude that wasn't aligned with the latitude that it's being used on actually in the field, will report you an error. So there is a check around that, and there is a safety net so that if you kept getting what they call Earth Rate Delta, ERD fails, using a north-seeking tool, this is one of the things you would look at. You would check that the driller or the surveyor entered the latitude of the tool when he started the survey correctly. That may be the starting point. It does not need a starting bearing like a reference gyro. It plots its azimuth virtually in space, so it's able to do this. It works on vectoring. They use solid state detectors. That's mostly just the technical jargon or what type of gyro it is, so you can go read up about that. They are consistently more accurate than all other downhole survey tools. So the gyros and these solid state gyros are being made way more robust. Years gone by, even within our brand, the reference gyros were very sensitive, and you drop them slightly and they need to go back to be repaired. This is not the case with these. They're very robust. They're less prone to drift. So what happens is all gyros drift depending on the quality. So if you've got higher end gyros, they will drift less than lower end gyros. And generally what happens is you would need to correct that also within a drift check or a drift correction phase of the tool. But essentially you get different types of gyros with different rates of drifts. You can conduct much quicker single shot and continuous surveys. As I stated earlier, you can run a continuous north-seeking gyro now at 150 meters a minute. This is just all the technical jargon. Like I said, I'm not going to focus on this. I think there's more important things. Unless somebody wanted me to talk about this, it's above my pay grade anyway. It's more engineering, science stuff, and I think we can add value elsewhere. So just where these gyros fit, you'll see that in the bottom left-hand corner here, we're talking about mechanical gyros, and they're used for strategic missiles. Then you've got these gyros, fog gyros, all fitting in the space of ship navigation systems, torpedoes, tactical missiles, and for those who've engaged with most surveying brands, will know at some point there were military controls around some of the technologies, depending on which gyro they were using. It became problematic because to move these tools around, you needed US government approval of where you were sending the tools. So we've moved a little bit away from these gyros to gyros that are more sort of consumer-related gyros that still give us the accuracy that we want. So these are just typically the types of gyros you get: mechanical, silicon MEMS gyroscopes, ring laser gyroscopes, and fiber optic gyroscopes. Most rigger liners use fiber optic gyroscopes, and they're way more accurate than just a general north-seeking survey tool. But they don't travel down the boreal. So this just explains what they do. I will get into stuff that I think is more important. The MEMS gyroscope systems works on electrical sensors with moving particles. So what are the factors that determine if a gyro is good or bad performance? So like I said, depending on the quality of the gyro, you can get what they call angular random walk, where it starts moving off. Bias stability, where you would have a certain amount of bias in that gyro. And then temperature sensitivity is key. Some years back, within our brand, I know that they were probably, they test all gyros for the temperature, and they were probably not using 50% of them. So in other words, we were only using 50% of the gyros were good enough and performed well enough in a temperature environment to be able to use them in our brand's tools. So temperature is really big. We have gyros that perform very differently up in the snow than work down in Botswana in the heat. So, you know, we have to cater for all of that wide spec of temperature. And then this is just a table showing the performance grade. So you can see now consumer, industrial, low-end, tactical, high-end tactical, navigation. That's the bias stability. And then obviously the applications where they're used. We would be working in all of these spaces depending on which technology that we use. And then those are the different types of gyro technology that are employed. I think I went through this earlier, the reference gyro. So the reference gyro point 1A1, that would be your input point. So if you were 90 degrees out or there was an error, it would give you a survey that's out by 90 degrees or 100 degrees, depending on what your error is. So it's very important to get this point correct. And then after that, have smooth transitional surveys to ensure that you don't have a failed survey. Otherwise, everything fails and you have to do it again. So they detect the rate of change when the gyro is in motion or changes orientation. So the plotting of the deviation of the ball is dependent on the reading before that. It requires a reference direction. So there we go. Generally, they're quite small. Higher bias stability, high random angular walk. So they've got higher angular walk. They basically measure the change in the rotational axis caused by excess external movement. So like I said, that's much older technology. That's been replaced by newer stuff. That's a combination of the two almost. This is just to explain the differences between the IMUs that different technologies or different brands use. So you'll see that this is the diameter of the tool, and this would be the accuracy or the bias stability in degrees per hour, or the angular walk in degrees per hour. So you'll see these are much lower, and those tools are really older technology, bigger diameters, down to that. And then we start getting here where we're looking at much better, much more improved bias stability, angular random walk, and turn on bias, and turn on bias. But these tools are the IMU is 24.5, so you're limited by the size of the gyro. And to my knowledge, you're looking at tools from about 25 to about 42 north-seeking gyros that are performing accurately. This, you'll see, is a much lower end, but it's a much smaller gyro. So in other words, if you had like a digital structural logging tool similar to the Logger X, you might be using this type of gyro, where it's not that important to have that accuracy and worry about the amount of drift. You know, in the case of Logger X, you're resetting it every couple of minutes anyway, back to the planned azimuth and dip. So you get accuracy and precision. On the left, you will be looking at reference gyros. So you get low accuracy, low precision. So you'll see it's quite scattered, and it depends on what project you're running at. So you might be happy with that. Then you get low accuracy but high precision, where it's not as accurate, but it's repeatable. Still can be problematic. North-seeking gyros, you get high accuracy, low precision, and then you get high accuracy, high precision. And even within our brand range, we've got some high accuracy, high precision, and some low accuracy, low precision, high accuracy. So just to give you some sort of an idea of the way people report, and this is something that you have to, when you're assessing what technology you're going to use on site, not all technologies are the same, and not all brands report the accuracy of the tool the same. Some people refer to 3 sigma, and some people refer to 1 sigma. 3 sigma is definitely way more accurate, and the preferred choice in a very, very precise type of application. You'd want to be looking at something with a 3 sigma. We've been through this. So they're given a north direction, azimuth direction, They're superior to magnetic tools and can work in magnetic environments. Cheaper than north-seeking tools, so they can work in the drill rod. The con is the human error. So again, the input of the azimuth. Some brands are using a system where they can align with a rig aligner and take that data automatically via Bluetooth into the survey tool as the starting azimuth. And in that case, it's as accurate as a north-seeking. But you need to use that with a rig aligner, and then in the end, it works out the same price point. So it's probably better to run a north-seeking gyro. Sensitive to temperature changes and any impacts, like I said, and you can only survey in multi-shot mode, not in continuous mode. So you have to stop every few minutes and then take a reading. So it's not as quick as a north-seeking gyros. North-seeking gyro is not affected by magnetism and consistently more accurate than reference gyros. So they're much higher accuracy and precision compared to reference gyros and magnetic tools. Like I said, ability to survey continuously at high speed. You don't have to go at 150. You can go slower, and you'll get much better data. But the data, the testing does show that you can run this tool at 150 meters a minute. Yeah, so the price point is much higher, but you've got that comfort level that you're able to survey quicker. It's accurate and precise, and that you would be handing back drilling time. So, there are, if you were going over 500 meters depth and you were surveying with a magnetic tool where you had to pull the drill string, survey, put the drill string back again, you are losing a considerable amount of time. It's probably about 10 to 15 minutes per survey station. So if you were surveying, if your requirement to survey every 3 meters or every 6 meters, every 6 meters, you're going to lose 15 minutes if you use the magnetic tool. If you run a high-speed gyro, this is not the case. You can run down at 150 meters a minute and back. At that time, you're taking a whole lot of interval readings and you're feeding them into your database. So you've got multiple surveys at that depth, at certain depths, feeding into your database, a much better option. This is just talking about the sigma. So 1 sigma is plotted either above or below the average line and includes 68% of all data points. 3 sigma is plotted above or below the average value and includes 99.7% of all the data points. So you can see a tool quoted in 3 sigma is much better, or I wouldn't say it's much better, but the 3 sigma reference is a better reference than a 1 sigma. This is just explaining the difference of how people report on their accuracies, and in no way does most of these people report the sigma. So you need to, if you're going to be assessing different technologies against each other, you need to determine, is this reported in 1 sigma or in 3 sigma? Okay. So now down to the nitty-gritty. When should I be using a north-seeking gyro? So what size of type of drilling am I doing? And what orientation am I drilling? So is it deep or shallow? The deeper you go, it comes into its own, but it's not to say that you can't use a north-seeker for shallow holes. What are the characteristics of the deposit? We spoke before that it's a magnetic kimberlites or magnetite. You've got a problem, and you would need the north-seeking. In what phase am I? Am I defining or delineating? You can decide on the technology. What will my drill rates be? Magnetic tools need aluminium rods, and we spoke about pulling the drill string, etc., etc. It can also be used in RC, but there's a work flow that's needed, and you need stainless steel rods, 6 meters of stainless steel rods at the bottom, or copper beryllium, and they work out very expensive. So at the end of the day, you have to weigh up whether those costs and the cost of lost time are offset against a cost of a north-seeking gyro and the speed of a north-seeking gyro, and then what level of data am I comfortable? There again, if any magnetic. So worst case deposit where I feel I really need the best gyros, so thinner deposits. So where you have thinner deposits and you're looking for that accuracy, you're going to need to consider a north-seeking gyro. Additional consideration is magnetic. We spoke about that. Where you need maximum structural information? It's not only for resource estimate, but also for mine development planning. Deep surveys do not lose accuracy and precision exponentially at depth. So the deeper you go, the more you're going to start moving towards continuous surveying. Drill rod diameters become less of a selection as tools are becoming smaller. So the smallest north-seeking gyro I know of is 38 millimeters. So they're getting thinner and thinner as we progress. I just wanted to, maybe I should talk about that a little bit. I'll talk about that in the QAQC. So most survey tools on site either require manual depth inputs or drillers lowering rods. So this is in the case of manual entry of the depth. And some have a form of a depth encoder. So it's a piece of equipment that has wheels with a depth encoder. As the wire line runs through the depth encoder, it's registering the depth of the tool is progressing. Some of these are built into the survey. Some of these are standalone, where you would go to a certain depth. If you were multi-shot, you would go to a certain depth. You'd say, I'm at 10 meters now, and then you would record 10 meters on the handheld, and you would press for a survey. Some of them are integrated, so it needs the depth encoder to be running the tool. Otherwise, the tool won't operate, especially in continuous mode, because it registers the speed. The data is transferred to an external PDA, a tablet, usually via Bluetooth or infrared methods. The more you move towards this technology, the less you have to disassemble the back end of a tool, the less safety issues you've got. So those are a consideration. And then obviously the data transfer and presentation to the client. Sometimes it's into a cloud database via an internet connection, which some companies offer, or directly downloaded via USB. So you can download via USB to the device in CSV format, or directly to a paired PC or a third-party device. The problem is that the more we introduce different steps in the workflow, like a USB, the more prone to errors we have or loss of data integrity. Some companies offer cloud-based depositories. So what happens is you're able to feed your data directly via Wi-Fi into and most companies are moving this way now. So it's not as if that's a big consideration to be making. The advantages of this type of technology is that you can conduct a single shot survey, let's say at the end of every day. It goes against the same borehole within the cloud. So what happens is you're able to build surveys as you go. At the end of the hole, you do a continuous high-speed survey going in and back out again. So you've got all of your single shots during production or exploration. You've then got a QAQC, a high-speed gyro at the end. So you've got enough data points to make a decision around where that ball actually went. Very important. So In the old days, every time you took a single shot, it reported it as a separate survey, and you had to plug it into a CSV spreadsheet, and you had to put all the single shots together to be able, and that took time. With these latest data packages, you're able to build a survey and then match that against the continuous survey at the same time. So again, the less the data is manually handled, the less errors. So in this case, where you're running cloud-based options, you have the ability to set what you feel is the QA, QC parameters. There's a couple of things that are important. You may want to set a tolerance on the azimuth and dip. You may want to set a tolerance on the start azimuth and dip. If it's outside of the spec, you would want to be flagged, and there would be a system within that cloud system that would flag you that it's outside of what you would have expected it to be. Any major 3 to 4 differences in tool azimuth or depth or dogleg severity, you could then flag. And then gravity tool face. I want to talk about gravity tool face. It's a very important QA consideration. And you can build flags or warnings around these gravity tool faces. What the gravity tool face reports is the role of the tool. So when we are surveying, all tools roll. They naturally roll. If you come across a survey where the gravity tool face is consistently the same, no movement, and you see the trend of the azimuth and the dip over the depth of the hole remains the same, that tool was stationary or highly likely stationary, and you need to interrogate that and how that was achieved. So we have had instances in the past where people have unscrupulously surveyed and it hasn't been in the borehole. And this gravity tool face is an important metric for ensuring that the survey was conducted downhole. So these are the things you need to look at. I'm going to jump into something now before we go any further. I can't remember if it's listed further down the presentation, but it's in my mind now. If you at any point have got queries about a tool, every single site or project should have what we call a confidence jig. You should have a drill pipe, a NQ rod or a BQ rod cemented in the ground with a known azimuth and dip that you consistently check the tools against, be it once a day, be it once a week, depending on what you specify. You get the initial readings, and you have people perform a roll test in the drill pipe. So when I talk about roll test, you would take a shot, you would do multi-shot test, you would take a shot, you would rotate the tool 90 degrees, take a shot, take it, turn it 90 degrees, and do 5 readings back to 0 again. And what this does is it determines whether you're getting the same azimuth and dip of the drill pipe that was originally set out, and that you, over the 5 readings, you get the same dip and azimuth. If you're not getting the same dip and azimuth, it indicates that the tool could be bent. And if the tool is bent, you will get errors downhole. The tool will automatically find a sweet spot while it's running down, and it won't rotate, and you won't get through this, you won't get the accurate azimuth and dip. So it's very important to set up a confidence jig and a confidence jig register on site, and to monitor this regularly. It's a major oversight in a lot of cases where we start interrogating the tools were not monitored. You have the ability to pick up an error in a tool very quickly. We've had sites where sometimes 400 boreholes have been drilled and surveyed by a faulty tool. You have to identify whether the tool is still in good condition as you go regularly. And the more important the drill site, the shorter that times. that time span should be. I get it that it takes time to go to a jig. If the project's that big and it's that important, a confidence jig concreted into the ground close by, you could have 4 or 5 of them. They don't all have to have the same azimuth. You're just monitoring that jig against that azimuth and dip. On the magnetic tool, we're talking about magnetic tools now. There is some QA/QC. If you were using a magnetic tool, the magnetic strength and the magnetic dips are predetermined or are determined by the position on Earth that you are surveying. And the tool QA/QC and the accuracy of the tool is governed by the signal that tool is getting. So if you were using a magnetic tool in a magnetic environment, and the tool was sensing a much higher magnetic force, you need to reject that reading. And the only way you're going to reject that reading is by monitoring the nanotesla strength, the magnetic strength, against what you should have got for that region or that location. So you can build QA/QCs around where was I 1,000 nanoteslas out from what the prescribed was, and then you can reject those readings. North seeking, after the tools producing glows means set correctly. So the north seeking is main measurement that will be the earth rate delta. So when you're working with a north seeking tool, things to look for: earth rate delta. If you are using it in continuous mode, you need to monitor that there was a speed associated with this tool to ensure that it was actually moving to do this continuous survey. Practical do's and don'ts at the drill rigs: always make sure you're running your snug in your drill rod. Survey is centralized and sits as snug as possible. So the further you get towards vertical, the more you're going to start looking at using centralizers. It's not that important when you're on an angled hole. The tool sits quite nicely in the drill string. The bigger the diameter, the more the tool will be prone to let's say, wobble. So it's important that the bigger you go and you don't have a comfort level around that sitting in the drill holes centrally, then you can use centralizing. Vibration is your enemy. So when it comes to all this surveying technology, particularly in production environments, underground environments where they're still doing exploration work or near a haulage, the survey has to be very aware of this. And in some cases, we've needed to switch off the drill rig just to ensure that there's no vibration through the wire line to the survey tool. If you're doing very precise gyros, clamp the wire line so you can switch the rig off and clamp the wire line, and make sure that the tool does not oscillate. So, once you've dropped it to the depth that you want it to drop to, we're talking now about multi-shot, not continuous surveys. Once you've dropped to your depth, you will stop and you will make sure that tool settles before you take your shot. Avoid stopping the wire line abruptly during surveys, again on multi-shot or single shot. Operate it as smoothly as possible. And then when not in use, store gyros in a cool place. So you don't want a tool laying out in the hot sun. It certainly will affect the performance. So with magnetic tools, all forms of magnetic influence can influence the performance of your survey. The machine, the drill rods, aluminium rods, so you'd have to put aluminium rods to survey, the geology, and remember that it's not just magnetite that is magnetic mineral. And even if you were testing a tool on the surface, a magnetic tool, and you just wanted to test it in an aluminium jig, so in the case of a magnetic tool, the confidence jig that you would build would be plastic, PVC pipe, or aluminium. Because if you put a drill pipe, a BQ or an NQ drill pipe, you would affect the performance of the magnetic tool. If you were doing a confidence jig test of a magnetic tool on surface, and you had a plastic, a PVC jig, a confidence jig, or you had an aluminium confidence jig, ensure that people that are doing the survey stand well clear of the tool when they take the reading. Your steel cut boots, a cell phone, a mobile phone in a pocket, all of these things will affect the tool if you're standing too close to it. So this is when you're doing magnetic confidence checking. Yeah, we've been through this, so give it time to settle. Confidence jigs, here we go. So I've spoken about it. This is extremely important. If you take nothing away from today other than the fact that on a critical project, you need a confidence jig and you need to log the surveys, confidence surveys against this. This is it. The most important thing. You can save yourself a very big headache. Oh, and I'm at the end of my slide here. Thank you very much. Any questions?
Thanks very much, Kevin. Okay, guys, floor's all yours to ask questions.
Hello, Kevin. I've got a
Yes.
question.
Yes, Josiah.
Yeah, thank you so much for the great presentation. I just want to find out, like, as a geologist now, when you get a report from the, let's say, the drillers, what is that we should look out for in the first place just to make sure that the data is making sense? Besides the speed, you mentioned the speed if you're doing continuous survey.
Yeah, so it depends what technology you're using, right? So
Oh
if
yeah.
you-
Sorry.
Yeah,
If you're
so
using a gyro, because we're using gyro.
okay, so if you continuous gyro or a
Yes, continuous
multi-shot?
gyro.
Continuous, yeah. So one of the things you're going to have to look for in continuous, your first stop is the earth rate delta. If you're using it in continuous mode, if you use that gyro in multi-shot, which some of them they allow you to do, I would also monitor the gravity reading of the tool. So if you use it in multi-shot, you would have a gravity reading because it needs to be stationary when you take that gravity shot. If you're using it in high speed, obviously it's moving, so your gravity reading is not reportable. But if you continuous survey, you would look at earth rate delta. If you multi-shot, you would look at the gravity readings. Okay?
Yes, all right.
And then,
Thank you.
so earth rate delta on all gyros, and then if you're doing continuous, first stop is earth rate delta, and then look at your misclass. Because high-speed gyros, what they do is they have an in-run and they have an out-run. In-run, out-run, and then what the misclose is, they reported that the discrepancy between the in and the out start position. So as you start the tool, the azimuth and the dip, and when you return to that position, the azimuth and the dip, and the plotted coordinates. So it does that all automatically. And if the surveys are separated and they're not less than 1%, you will get an error on the misclose, and you would have to do the survey again. So all it's doing is it's saying somewhere down the hole there was a deviation and the tool didn't understand this, and you cannot rely on this reading. So those are the things you look for in the high-speed continuous gyro.
Thank you very much, Kevin. Just another quick one. On the magnetic survey tool, is it practical in areas where you have magnetite, like beef, iron formation?
No, that's a problem.
All right.
So it's effective. You can use it, but it's not reliable. Look, there are some instances where not all of the formation is magnetic. I've seen some projects where we had about 40% of the formation was magnetic, and we still had enough good data to be able to plot a survey, but with relatively low confidence. So you still could plot it, but it wasn't as good as a gyro in that application. So it depends what you want out of the project. That same project, eventually they said, no, our requirement now is we want to go to north seeking. We were happy with the data before. We were happy with 40, 50% of data, But now we've gone to a phase in the project where we want better data. And then they move to North Seeking.
Thank you very much. I appreciate it.
No problem. Yeah. Thank you very much for the opportunity, guys. Tanya, thank you.
Thank you very much, Kevin. Right, so moving on. Next up is Sarah Solway. And Sarah's going to be talking to us about structural logging. Sarah is a geologist with over 30 years of experience and has a broad range of technical and management skills with mining equipment technology and service companies. So Sarah, over to you. Thank you.
Thanks very much, Tanya. What I'm going to talk to you about in this session is the significance of structural logging. Now, more often than not, when we talk about structural logging, most people jump straight in to how to measure the bedding planes, the faults, the foliation. But here's the thing, if your core isn't properly orientated or hasn't been prepared carefully, those measurements might be meaningless or misleading. So I'm going to spend a little bit of time explaining the actual process of core orientation, starting with how digital core sort of orientation tools work, the workflow undertaken by drillers to get that ori mark on the core, and where errors can occur. Core orientation gives us the reference frame to convert alpha and beta angles into real-world strike and dip. And without reliable orientations, we're essentially just guessing. So after that, I'll then move on to preparing the core for logging, the tools that we use to measure those structures in diamond core samples, and then the application of stereo nets for data visualization and analysis. And finally, crucial aspect of quality assurance and quality control. So when we look at the Earth's surface, we see landscapes that have been shaped by time, pressure, movement, and erosion. Extending our understanding of these landscapes beneath the surface is done through drilling and subsequent logging of those drill samples. So what is structural logging? Well, essentially, it's the systematic recording of geological structures, faults, folds, fractures, bedding planes, and the like. It's not just about collecting data. It's also about understanding the architecture of the Earth itself. You can think of it as a study of the skeleton of the Earth. So why is this important? Well, firstly, it's vital for geological modelling. Accurate models of subsurface geology depend on detailed structural data and other logging as well. These models guide everything from mineral exploration to groundwater studies and infrastructure development. Secondly, structural logging helps us to predict geological hazards. By identifying fault zones, unstable rock masses, and deformation patterns, we can assess risks like landslides, earthquakes, and subsidence, protecting lives and infrastructure. So, of course, structural information is just one of the properties we can capture from rocks. Rocks hold a wealth of information, providing valuable insights into the Earth's history, processes, and resources. Through observations, logging, and the application of advanced technology, we can extract details about their composition. The mineralogy tells us a lot about understanding the geometallurgical characteristics of the rock. The chemistry tells us about the chemical composition, but more importantly, the grade of the rock, and which is critical to economic potential of a deposit. Geophysical or petrophysical data can be used to identify boundaries and is quite often used as a proxy to geology. Texture and the structure of the rock can help us guide as to where the ore may be. But of course, all of this information is completely and utterly useless if we don't know where it came from, if we don't know its in situ location and its orientation. All this data is collected and it's integrated with other information to reconstruct the sequence of events that have occurred over millions of years. As we collect additional data, we can refine our geological interpretations. Now, the confidence that we assign in these interpretations and subsequent resource estimation relies heavily on the quality of the underlying data that informs those models. And that confidence is the foundation upon which exploration companies decide which projects to pursue and which to put on hold. Similarly, investors base their decisions on which companies to invest in on this confidence level. I guess the point I'm trying to make is that the value of data collected and its interpretation directly impacts the cost of these critical decisions. So building rock knowledge through the collection of high quality data is key to successfully navigating the mining value chain. And of course, exploration is where this journey begins. We know we're looking for something valuable, a concentration of economic minerals in a quantity and location that can be extracted at a profit. However, we don't yet have a good understanding of exactly where it is, what it looks like, or even how much it will cost to find it. At this early stage, decisions are based on limited data. The more we invest in collecting high quality geological information, the better our chances are of success. Now, as our knowledge increases and geological models and resource estimations are refined, this is where rock knowledge starts to shape investment decisions. So better data means better models, better forecasts, and higher confidence. By the time we get to the grade control phase, precision matters. We're no longer asking if the resource is there, we're asking exactly where it is and what it is. Grade control is about reducing uncertainty, maximizing value. The quality of the data directly impacts how efficiently we can mine. Whereas blasting isn't just about breaking rock. It's about doing it in a way that maximizes downstream efficiency. With good rock knowledge, we can tailor blast designs to the geology, improving fragmentation and reducing costs. Now, structural logging features across every single stage from exploration to production. And it adds to, well, the better we understand the rock, the better we can plan, operate, and deliver value to the operation. So even with all of this really advanced technology that surrounds us, drilling is still the major source of the rocks from which information is extracted and used to inform geological models. But it's expensive and it's time consuming. If it's carried out without accurate geological information and planning, it can lead to the wastage of valuable resources and misinterpretation of geological structures and models. So determination of structural data from drilling can be done either using borehole imaging techniques, such as optical or acoustic televiewers. Now, these methods involve lowering sensors downhole after drilling has been complete, capturing high-resolution images of the internal drill hole walls. These images are then sort of folded out the book onto a flat 2D image where they can be analysed and interpreted. The second method involves determining the orientation of that core sample before it was extracted from the ground, and using that information to measure the orientation of structures within that core sample during the logging process. And it's that method that I'm going to focus on during this presentation. So I think it's worth just talking a little bit about the fact that determination of structural geology from core samples presents several challenges, which can be grouped into three sort of categories. Ground conditions are one. If those ground conditions are poor, if the rock is very, very fragmented and you've got fractured and unstable formations, it is actually very hard and almost impossible to orientate core using this method in drill holes. The second category is looking at the core orientation process itself, keeping in mind that it all starts at the drill rig. Thirdly, technology used to orientate and measure those structures and move that data around between systems. So there's a lot of challenges that we've got to think about here. An added complication in the sort of end-to-end structural geology workflow is that the process of core orientation, structural measurements, and geological interpretation is divided into several different stages, each occurring at different locations. So the actual orientation tools are used by the drillers at the drill rig. That core is then transported to the core shed, where it is handled by a different team, usually from a different company. It's in the geologist and the resource company. And then the data collected in the core shed quite often is transferred by computers and cloud technology into an office where potentially different geologists are actually doing the interpretations. So this often results in a disconnect between people and also data. And that disconnect can potentially reduce the data quality as errors are introduced at each stage in the process. Why is it so important that we get it right? Well, if we look at this lovely piece of core here and we consider this fracture, let's assume that it's associated with a mineralization event, and knowing its orientation is really important in terms of drill hole planning. We know through downhole survey tools that our hole was dipping at minus 65 degrees with a dip direction of 90 degrees. We know that that piece of core was located at 135 meters beneath the surface. Now, based on the orientation mark that was generated by the drilling operator at the rig, the core is orientated at this angle within the hole, meaning that the plane of fracture runs like this, so sort of in and out of the screen as we're looking at it. However, what if that core was actually orientated just 10 to 15 degrees differently? Sorry, I went a bit far there. What we would see there is the plane shifts. If we then look at the actual trajectory of that drill hole, according to the downhole surveys, you can see that the orientation of that structure shifts again. Now, depending on the spacing of your drill holes, that could have a really large impact on where your next drill hole will be. So because of this, I'm going to spend a little bit of time discussing the actual process of orientating the core. So the concept of orientating core has been around quite a while, with the first system developed over 150 years ago in 1854. Over the next 30 years or so, rotary drill cores were developed and a system developed that marked the core before it was extracted. First half of the 20th century, compasses and cameras were incorporated into the process, and by the 1950s, core orientation was pretty much standard practice at many drilling operations. The processes used at that time stuck around for quite a while. And it wasn't until 2004 that the first digital device was released into the market. And this method orientates the core tube and it marks the core face at the bottom of the drill run rather than at the top. And it's this method that is by far the most commonly used today and the one that I'm going to talk about. So Digital core orientation solutions, no matter which ones you look at, they all comprise a downhole unit, which is incorporated into the drill string and basically goes down the hole during drilling. It contains or comprises a controller, such as this, that remains at the surface, and a marking jig. Now, this particular device that I'm showing there combines the marking jig and the controller in the one device. A lot of the solutions, you will also see a separate controller and a marking jig, which is like a V block with a blade and a spirit level in it. So the way that it works, the sensors, is that the downhole unit includes an accelerometer. Now, that accelerometer is the same technology that is used in your smartphone or tablet, and that's what controls or allows the display in your device to switch between horizontal or vertical. An accelerometer essentially detects motion and orientation with respect to gravity. In other words, it measures down towards the center of the earth. The workflow used to get the mark on the face of that core is the same, regardless of what tool is being used. So the first step, I'll just find my laser pointer here. So the first step here is to initialize the downhole unit. And this is done by using the controller. So in this one here, you can see that Actex orientation jig is placed over a water port in the grease cap, where a button is pressed. And essentially what that does is synchronize a stopwatch in both those devices. The other thing that happens is that downhole unit starts measuring down. All right, so it starts taking a reading. Depending on the tool that you're using, those downhole units take measurements every 30 to 60 seconds. So whilst that tool is in the drill string and it's drilling, every 30 to 60 seconds, a reading is taken. So which way is down? Once that inner tube is full of core, the driller stops drilling and will press a button on that controller that will start a countdown. The purpose of that, pressing that button, is that it's registering the time. So when the downhole unit comes back up to the surface or comes back up to the rig, then that's how the device knows which measurement to use for the actual orientation of that core. This point in the process is quite important, because if the drill string is vibrating and still rotating, then that reading is not going to be reliable. So it's one of the points in the workflow that errors can occur. So by the end of that countdown, at this point I should mention that the core in the tube is still attached to the bedrock. So when that countdown timer stops, then the driller will pull back on the drill string, causing the core to be grabbed by the core lifter or shoe and breaking the core from bedrock. So this is another possible point of error, because if the core lifter is old or damaged, or the way that the driller breaks off bottom, the core can slip slightly and spin in the tube. Once the inner tube is retrieved and laid out on the trestles at surface, the orientation reading that was taken after the countdown was completed at that break point is read from the downhole unit. And then depending on the tools used, the Actex is slid over the end of the core lifter, and then the jig rotated until all of the LEDs are lit up green, at which point the driller's offsider or helper knows it's in the right position within plus or minus 1 degree of the reading, and they can mark the core. If they're using a V-block type arrangement, then the driller will actually rotate the core tube full of core into the correct position, and then you sort of use that marking jig, making sure that the spirit level is level before marking the base of the core. With this particular solution, there is an extra step whereby the orientation jig is used to check that this tube hasn't rolled between this read mark and this final QA step. Because if it has, then this point here is incorrect, right? It's unreliable. The mark will be in the wrong place. That's the sort of what happens at the rig and the workflow there. So once the core has been removed from the core tube and put into core trays, it's transported to the core shed. And at this point, we need to get the core ready for structural measurements by actually taking that ORI mark that was made at the rig and drawing an orientation line along the side using the ORI mark as the starting point. Now, this process can actually be done at the rig by either a geologist or somebody from the drilling crew. Just a word of caution in doing that. Drillers tend to be very, very focused on meters drilled. A lot of contracts are based on that. And so they are motivated by meters. They want to be able to get this mark on the core as quickly and as easily as possible and then start drilling again. If you are going to use somebody from the drilling crew to draw this, to generate the ORI line, then I recommend spending quite a bit of time with them explaining why they're doing it and how important it is, so you get the best possible result. Now, if we're doing this in the core shed, what is commonly considered best practice is to actually remove the core from the tray and lay it into a V channel or an angle iron, like you see here, which is like a V sort of shaped rack. Here, the core is pieced together, the sections of core are pieced together as best as possible, and then using a straight edge, either of the angle iron, as you can sort of see here, or quite often there is a straight-edged ruler that is used to extend that line along the edge, crossing over the breaks. The downhole direction of the drill hole is also marked on the core at this time, and you can see that in the top image here or photo here, with those arrows showing the downhole direction. This line, of course, is used as the reference from which we take our structural measurements. The sensors that we use in these downhole units are highly accurate and very precise. So how is it possible that when the core looks together perfectly, the ORI lines between the two consecutive runs don't? Is it because one or both of the marks are wrong due to either tool error or something's happened in the workflow? Or is it because one or both of the orientation lines have been drawn incorrectly? How do we know which one is more reliable? Keeping in mind that it does have quite a big impact on our structural measurements. So it's a geologist's responsibility to understand what can affect the reliability of this data that we are being given in regards to location and orientation of the drill hole. Let's spend a little bit of time discussing that. So there are a number of factors that can compromise the integrity of data, and these fall into one or more of the categories shown here. If we look specifically at the structural geology workflow, errors are most commonly associated with human error and tool error, which in turn can be linked with inadequate understanding of the process workflow. So if we look at the errors associated with the tool itself, it can be due to them not being calibrated properly. Now, all vendors should run calibration checks on the tools when they return from the field, either after a rental period or if there's a routine maintenance period has come up. And a calibration certificate is generally included in the kit when it's returned to the field to prove that it is working correctly. If you are worried about the reliability of the tool, there are confidence check procedures that can be performed on the tools in the field to confirm that they are working correctly. And the vendors should be able to provide you with a procedure to do that. Other issues that could affect the performance of the tools and affect the reading and marking of the core is if they are being operated outside the recommended sort of specifications. Temperature is one of those. Now, most tools have a temperature rating of between -30 to +60 degrees Celsius. And some of them, Actex is one, will report the maximum temperature that the tool has reached during that particular drill run. Now, this allows the driller to monitor the situation, and it also provides this information to the geologist when looking at assigning a confidence rating for the drill run. The dip of the drill hole is another thing that needs to be taken into account. Now, because accelerometers in the drill hole measure down towards the center of the earth, as the drill hole approaches vertical, the accelerometer struggles to measure angles relating to gravimetric bottom of hole. So it's always good to check the tolerance of that downhole unit with respect to dip. If you are drilling a fairly steeply dipping hole, say 85 degrees, we all know that drill holes are never straight. They vary a lot, especially as you get deeper. So monitoring that dip for each run, and when it gets to around well, again, it depends on the sensor in each of the downhole units. Our tools, it's around about 86, 87 degrees in dip. That's when it becomes a little bit unreliable. It doesn't mean to say that you shouldn't, or you should ask the driller not to mark, but it just means that, again, if you've got that information handy to you when you're doing the markup and taking your structural measurements, it can explain why some structural measurements seem to be a little bit out of what you're expecting. The angle at which the inner tube is placed on the racks when it comes back to the rig can also affect the accelerometers. So it is a good idea to get them to make sure that when they're laid out on those racks or trellises, it's as close to 0 degrees as possible. If at angles of greater than sort of 20 degrees, or 30 degrees rather, it can affect the reliability. It is sometimes difficult, especially at surface, in early exploration phases, particularly in rough ground, to get those trellises as horizontal as possible, but it really is worthwhile spending a bit of time to do that. So then we come to human error. It's by far the most common errors anywhere. It doesn't matter how accurate or precise sensors you're using, and this goes to any device you're using. As soon as you insert a human being into any workflow, the potential for errors skyrocket, no matter how careful you might be. Common errors that are associated with the core orientation process includes breaking off the bedrock too early. So if that tube was still vibrating or rotating when that orientation reading was made, that will cause an incorrect mark to be put onto the core. And it's sometimes a little bit difficult to monitor when that happens. So again, understand the tools that your drilling operator is using. And if it is a tool that collects that information and flags it, then make sure that you get hold of that information and look at it. Another common sort of mistake that can be made, again, depending on the tool that's being used, is if the operator breaks the wrong joint. So this tool, for example, which is the Act 3, the electronics are actually housed in this the downhole unit here. They're actually housed in that unit there. So in orientating the core, the driller needs to break a joint in order to do that. If they break this joint instead of this one, they'll lose the orientation. It doesn't matter how quickly they do that joint back up again, they've lost it. So again, that can be a problem if when you come to doing your markup, those orientation lines don't quite match. Now, core spin refers to unintended rotation of the drill core within that inner tube. So it generally occurs when the core breaks off bedrock and the core spins. So if the core lifter or shoe doesn't grab that core properly, if it's in poor, it hasn't been maintained, then that could cause this problem. So examine the core for signs of core spin. So that could be polished ends, concentric rings, like is shown in this photo here, or mismatched features across the brake. If this occurs, then the orientation mark is generally unreliable for that particular run. So mark quality is the next one. You can see here a variety of different marks. This first image here, that is quite a smudged mark. So that can occur if the person who has made the mark on the core is maybe using a marker that is like a crayon that is quite blunt and hasn't got a nice sharp edge to it. It could also be that if they're using a one of the V block with blades, then it can be quite difficult, as you can see in this picture here, depending on how the core is sort of broken, to get a mark onto that core. What we're really looking for is something like this, a nice sharp mark that clearly defines which edge it goes onto. Quite often I've seen marks that actually go across the entire face of the core, which can be a little bit confusing. This is the Act X there. You can see it's got a constrained marking kind of sort of slot there that the marker can be inserted through. It's still very tricky when you've got core that looks like this to mark it, but it does make it a little bit easier for the operator. And then reconstructing the orientation line. So if we don't piece the core together with care or correctly, then that could cause problems as you extend the orientation line across brakes. If you use a short or an even guide to draw the orientation line, this can also cause a problem. This picture here shows the technician using the straight edge of the angle line to draw the line. Now, again, you can see how they've got that sort of marker orientated. If they kind of twist it or change the angle at which they're drawing that line, even though they're using the angle line, it can cause a bit of a wavy line. So a lot of sites won't use the angle line, they'll use a straight-edged ruler. Other mistakes are marking the downhole arrow facing uphole instead of downhole. Now, this can cause confusion when you actually go to start taking the structural measurements, as you see when we start talking about the actual tools. And then not extending the orientation line across broken core. Okay, once that core is broken and it comes out the other end, you can't be certain that that piece of core that is competent hasn't rotated within the inner tube whilst drilling has occurred. Okay, so confidence classifications. One element of quality control that is commonly used to assign a confidence rating to the quality of the orientation for each run. This confidence rating is then used to flag the structural measurements taken from that particular drill run, which then in turn feeds into the geological interpretations and resource estimations. Now, there are a number of different methods that can be applied. The simplest form is a rating based on the continuity between drill runs and is assigned with the highest confidence rating is assigned to the drill run where the orientation lines match within a specified tolerance for at least 3 consecutive runs. This tolerance differs between projects, but 5 to 10 degrees is common, although I have seen tolerances for up to 15 degrees used. Another method, which is documented by Rod Holcomb, and I put the reference there, involves piecing together as much of the core as possible and then using the driller's mark on the first run and draw a preliminary line along the entire length of the pieced together core. For each drill run, the mismatch between the mark and the line is recorded. Outlines are discarded and the average mismatch is calculated with drill runs showing significant deviations corrected based on the mean. And then a confidence score between 1 and 5 is assigned. So it's quite an involved process. And so if you want to read more about that, I recommend going and looking at the material that I've referenced there. Another method systematically rates the quality of the orientation mark based on the potential angular error due to the mark not being a nice sharp line, and the orientation line based on how well the orientation lines match between drill runs. A bamboo diagram is quite often used to help visualize the orientation log and identify errors, allowing them to be corrected where possible. And again, I put a reference there if you want to read up more about that particular process. Finally, a confidence rating is assigned to the entire drill hole by looking at the cumulative mismatch angle over the entire hole. So before jumping straight in and taking structural measurements, it's a good idea to take a step back and look at the entire hole. Remember that the core represents only a small linear section of the subsurface, and whilst large-scale structures such as major folds and faults may not be visible in the core, the small-scale structures can indicate the types and direction of stresses that have affected the rock. By examining relationships between different structures, it's possible to establish a relative timeline of geological events, keeping in mind that a variety of different structures can form from a single deformation event or stress field. Faults and folds, for example, are commonly related and form at the same time. Analysis of these small-scale structures can help piece together a better picture of the geological history and processes on a regional scale, even if the large-scale structures are not directly visible within the core. There are a number of tools that can be used to take structural measurements, and before we look at them and how they work, I'm just going to talk about the measurement conventions that are used. Now, a lot of the manual tools measure the orientation of features relative to the core axis and the orientation line. So with planar features such as faults, bedding planes, veins, they intersect the drill hole at an oblique angle and creates an elliptical pattern as shown here. The orientation of these structures is defined by a beta angle, which is the angle between the orientation line and the apex of the ellipse measured in a clockwise direction, whereas the alpha angle is the acute angle between the core axis and the long axis of the ellipse, and is always between 0 and 90 degrees. The alpha and beta angles are converted to dip and dip direction generally using a computer program or stereo nets. Now, to measure plunge and azimuth or a trend of a line on a plane or a lineation, a third angle needs to be measured, and this is the gamma angle. It has a number of different definitions, so you need to make sure that you're consistent with whichever one you use. The literature can be a little bit confusing because authors use different naming conventions for the same measurement. So the first measurement, or first method, I should say, involves measuring the angle from the long axis of the plane in which the lineation lies to where it intercepts the ellipse in a clockwise direction. Whereas the second method involves measuring the angle clockwise from the orientation line to the first intercept of lineation. Okay, so let's look at some of the tools. Now, manual methods. These are the methods that measure the alpha and beta angles directly. They include chronometers, wraparound protractors, goniometers, and protractors with pivot arms. To measure the so with the angle, the chronometer, the beta angle is aligned with the apex of the ellipse at 0 degree mark on the chronometer, and angles are read where the ori line sort of passes through the readings here on the horizontal part of the chronometer, whereas the alpha angle is read off these side markings here. For the goniometer, it is slightly different. The beta angles are the downhole, orientation line is aligned with the 0 mark on the horizontal angles here, and then the beta angle is measured by the angle that is aligned with the apex of the structure that you're wanting to measure. The alpha angles are measured off the using side measurement markings on the goniometer. The wraparound protractor is very similar, with the beta angles measured by aligning the ori line with the 0 mark on the wraparound protractor, and the angle read at the apex of the ellipse, and the alpha angles are measured using the side measurement markings. Now, common sources of error when using all of these tools, very common, the core is placed in the tool in the wrong way round. So you'll see on the tools themselves, you've got arrows showing you which way the core should actually be placed within the device. Another common error is that different conventions are used. So the chronometer is the 0 degree is aligned with the apex of the ellipse, whereas with wraparound protractors and goniometers, it's the other way around. The orientation line is matched with the 0 degree mark on the device. Using the wrong size tool can also cause errors. So you can see in the top image there, the core is actually sort of sitting at the base of the chronometer and is reading an alpha angle of 60 degrees. Whereas if you move it up to the top of the chronometer, then that alpha angle changes to 54 degrees. So wraparound protractors is quite common with the wraparound protractors because you need to use different wraparounds for different size core. The thickness of the line is also a consideration. So this is a B-size core. The orientation line has an angular width of 5 to 6 degrees in the top image there, and that results in a potential error of about 2%. The orientation line, which is sort of almost 10 degrees thick, introduces a measurement uncertainty of around about 3.5%. So again, when you're drawing that line along the side of the core, try and get it as thin and as precise as possible. This one here is identifying the apex of the ellipse with high alpha angles. Can be very, very difficult just simply because of the very gentle curve of the ellipse there. So that can be quite tricky. And then finally, all of these devices require the geologist to enter the alpha beta angles either directly into a computer program or write it on a log that then gets manually entered. Again, human beings are fallible. They make mistakes with that manual entry. So another very common tool used to measure structures is an orientation frame or rocket launcher. Now, these frames are set up to physically orientate the drill core as it was drilled in the hole, or sorry, as it sat before it was extracted from the hole. The geologist then measures the orientation of the features using a compass and planometer or a smartphone app. Now, this method measures the dip and dip direction of the feature directly. There's a lot of different frames. They range from precision engineering, like this one here, to sort of homemade devices and frames. Again, the errors that occur is that you need to make sure that that frame is level. The core is placed in the correct way around with the downhole direction facing downhole. And then, of course, again, you've got the manual entry errors that can creep in there as well. Moving on to digital methods. This is the Logger X. It's a handheld digital device that uses an IMU to measure the dip and dip direction of the structure directly. It uses the orientation line as the reference point. So the IMU combines the functionality of a gyro and an accelerometer. And that gyro is a reference gyro or a rate gyro, and measurements are taken in relation to a reference plane, in this case being the full orientation line. When you align the device on the orientation line and press the button, it actually thinks that it is sitting in space like this. So when you lift that device up and shine the laser around the structure you're wanting to measure, it directly measures the dip and the dip direction, and will also back calculate the alpha beta angles or gamma in the case of lineations. Erroneous measurements can occur if the core is moved after aligning the device because its reference point has changed. And in this instance, you need to realign it again before the measurement. Also, because reference gyros drift over time, it's important to align the device at regular intervals, regardless of whether the core has moved. You don't get manual entry errors with this device because it's captured automatically, but it is a handheld device. And so there is a person on the other end of that hand. And so it's only as good as the person actually operating it. Other digital methods that are being increasingly utilized include determination of structures and measurements from core photos. The process of taking core photos is common practice for a long time now. And there's a number of software solutions that take advantage of these photos to allow the identification of structures either manually by drawing elliptical traces to match the structures or using machine learning to identify structures. Both these methods have the advantage of automatic determination of the alpha beta angles dip direction, eliminating errors associated with manual entry and calculation. Some of the limitations of this approach is that some solutions you can only see one side of the core. Poor image quality and resolution can also be an issue, and subtle structures can often be difficult to see. So, how many structural measurements should you take? Well, this depends on the complexity of the geological structures, the specific project objectives, and the quality of the core. Every project is different, but some general guidelines is that ultimately, in order to be useful, you need to collect enough structural measurements to allow for statistical analysis. And this means measuring structures at regular intervals, ensuring a representative sampling of the entire core. This could include taking measurements every meter or every few meters, depending on the geological complexity. Another way of thinking about this is in terms of the variability of the structures. If the orientation of a structure set is relatively consistent through the whole, then sort of 1 to 2 representative measurements every drill run would be sufficient. Now, the purpose of collecting structural measurements should also guide the number of measurements. If the goal is to understand broad-scale trends and major structural features, then a smaller number of measurements may be acceptable. Significant structures in areas of particular interest, such as zones of mineralization or areas with complex deformation, increase the density of measurements to capture more detailed structural information and ensure that each type of structure is measured consistently and standardized naming conventions. So StereoNets. StereoNet is a method for viewing 3D data in 2 dimensions. It's often something that is a little bit confusing to people and not really sure what they're looking at. So I'm just going to spend a bit of time explaining what it is. So if we imagine a plane cutting through the center of a sphere, we remove the upper half of that sphere. You can see the lines of latitude and longitude marked on that lower half of the sphere. That's what a StereoNet is. So an arc is formed where that plane intersects the lower hemisphere. And if we project the intersection points of this arc to where it intersects the lower hemisphere there, and if we project those points back up to the zenith of that sphere, then where it cuts or intersects the StereoNet, that forms the great circle of the plane. Steeply dipping planes will plot closer to the center of the StereoNet, whereas shallow dipping planes plot towards the edge of the StereoNet. Now, it gets pretty messy when you have a lot of measurements and it becomes impossible to interpret anything useful, which is why it's common practice to represent a plane using the pole. So what that is the pole to the plane is generated by projecting an imaginary line perpendicular to the plane down to where it hits the edge of the lower hemisphere and then back up to its zenith. The point where it passes through that lower hemisphere is the pole. Steeply dipping planes will plot closer to the edge, whereas gently steeping planes will plot closer to the center, so opposite to the Great Plane. Lineations lie on the plane and are measured using plunge and azimuth. They are represented by a point on the StereoNet. Now, in this image, the lineation is represented by the blue line. The point where it touches the edge of the lower hemisphere is projected back up to the zenith, and then the point plotted on the StereoNet at that intersection point. Note that it plots on the great circle of the plane it lies on. So I've talked about various points in the orientation process where errors can occur. These include where the orientation mark is incorrect or of poor quality, errors associated with generating the orientation line due to sort of care not being taken when generating it, errors introduced when measuring the structures, and then statistical errors can also occur through the choice of which features to measure and the number of measurements taken. StereoNets and Rose diagrams can both be useful in identifying errors. A Rose diagram is essentially a circular histogram that displays the frequency of measurements for a particular feature. Now, measurements from well-orientated core will have a relatively small spread. The image that you can see there shows measurements of the same feature in a single drill hole. When you superimpose the small circle, which is essentially a best fit line of the data, the center of that small circle distribution is centered over the drill hole. Now, possible causes of this are spun core, poor quality orientation marking and line generation, or poor quality logging. It could be all of the above. If you have a pervasive feature of a known orientation, it's worth taking at least a couple of measurements in each drill run and checking for relative spin. If you do have a feature with a known orientation, it's quite common for these features to be undermeasured because they're well known and therefore not considered that important to measure. Where you see significant asymmetry or dominant orientations, particularly in a Rose diagram, then this can indicate inaccurate measurements or bias in data measurements. Also, inconsistencies when comparing measurements from different intervals or drill holes can indicate that you have errors. These are the same kind of errors as you see with outliers or unusual orientations. This is an impact of angular errors. So these are angular errors of deviations from differences in the strike and depth of the same structure. If a drill hole is inclined at minus 60 degrees towards 270, then the structure and the structure being measured has an alpha beta angle of 45 degrees each. It should point or plot where that black star is. The red points show a systematic change in the alpha angles of 5, 10, and 20 degrees, and the green points, the beta angle. You can see the spread is really quite large for the same structure. In summary, quality of structural measurements are only as good as the driller and the geologist's care factor. Okay, you're a team. You need to work together. Understand how the ORI mark gets onto the core. That's really important. What tools are being used by your drilling contractor, and are they doing it right? Spend time marking up and assigning confidence classifications to the drill run. Understand how to use those structural measurement tools and understand their limitations. Take as many relevant measurements as you need and beware of cumulative errors. And please don't rely on technology to fix poor data quality. Technology is advancing at a huge rate of knots. And yes, sometimes it can be used to identify and fix errors, but it is always better to collect high quality data in the first place. So if there's one thing I'd like you to take away from this presentation today, it's that structural logging starts before you start taking a single measurement. Orientation and preparation are not optional. They're a foundational part of the structural logging workflow, and errors are preventable if you slow down, verify the workflows, and respect the process. Okay, so that's the end of my presentation. Thank you very much.
Thank you very much, Sarah. Very useful. Guys, questions for Sarah, please? So what's the most accurate method of reorientation? So look, not quite sure what you mean by reorientation. If you're talking about once you've sort of got that drill core and the mark is, or that orientation line is already there, one of the things that you can do is those bamboo diagrams are really, really quite useful in the fact that if you look at the mismatch or the lock angles at each end of that drill run and they match, you can actually reorientate or move that orientation line into the correct position. The other thing that you can do is looking at tools like the ACTX, and I'm in full disclosure here, I work for Index that develops the ACTX, but the ACTX actually captures information about the quality of the mark and at different points in the workflow, what's happening, which gives you information about which line is more reliable, again, allowing you to adjust the one that is less reliable as well. So I hope that answers that question there. Which method for logging oriented core? Okay, so look, again, it depends on what you're doing. The digital methods are, they eliminate manual entry, which is by far the most common form
of errors. They're also quicker. They allow you to collect more information, which can also be a little bit of a downfall, because it's easy to collect data, you can collect a lot of it. Now, some might argue more data is better than less data, and you could always filter it out. So I personally would always go for the digital methods because of that. Manual methods can be very good for checking. And sort of, I would always encourage you, as part of the QA/QC, just like you do with sampling, and you insert duplicates in 1 in every 20 measurements or samples. Do the same with your structural measurements. So 1 in 20, 1 in 30, use a different method to measure the same set of structures and compare them. Does the accuracy measurement of structures in the core matter more depending on the type of deposits one is looking at, or is it equal across all deposits? It does depend on the type of deposits. I'm not so sure whether the accuracy. So if you're looking at, say, a porphyry deposit, arguably not as important to be precise or as accurate as the narrow vein epithermal gold deposit, for example. But it does vary from project to project, and also the stage of the project you're in. Early stage exploration, where you've got very, very little data to work on, and your confidence is lower, you're wanting to collect as much information as possible. When you're in a production environment where the geology is much better known, and you're maybe looking not so much for the geology, but for geotech purposes, then yeah, you're collecting things for sort of different reasons. Okay, but all deposits, as we know, are structurally controlled in some way. How can we differentiate a core if it's a structural fracture or a mechanical break? Okay, so this one, when you have, when the driller or the driller's offside or helper empties the core into the tray, if you spent any time on the coring, you'll see that they get a mallet and they hit and they break the core to fit it into the tray. When that happens, what they should be doing is, maybe you'll see putting a red cross on either side of that core. It indicates it's a mechanical break. The other thing that you can look is actually look at the face of the core along the break there. So if it's a structural fracture, you will see, or will probably see, some kind of striation or indication that of movement along that break there, whereas mechanical breaks tend to be fairly clean. It takes a bit of practice to look at that, but yeah, definitely talk to your drilling contractors, and if they have broken the core, get them to market. It's also quite often core breaks in transporting from the rig to the core shed. So what happens in a lot of operations that I've been to is that the operator will take a photograph of the core tray before it's loaded onto the back of the ute and transported, and that can be digitally uploaded to the database and can also be used by the technician or geologist in the core shed to help ascertain which core or what lengths of core may have been broken in transit. So that's another thing to think about. The missed one, sorry, I have to see. Does this accuracy measurement of the structures in the core matter more depending on the type of deposits one is looking at? Yeah, I think I did answer that one. It does depend on the, so like the amount of structural impact in the core. So an epithermal gold deposit, for a narrow vein gold deposit, for example, as opposed to the porphyry copper, then yeah, the type of structural measurements you take will be different.
Sarah, thanks once again. we're going to move straight on to our last presentation. And Rams is going to be talking to us about drill hole sampling. And Rams Kinyago is a geologist with many years' experience in mineral exploration and resource development. And much of what he has been doing revolves around executing field programs, drill management. So, Rams, we look forward to your presentation this afternoon.
Thank you, Tanya. As Tanya said, I'm a geologist with over 15 years in the industry. I've been involved in a number of production and exploration projects. So I'm keen to share a bit of my experience with you guys today. With our topic today, we need to start by merely understanding why drill hole sampling matters. In its core, it provides us with accurate, representative, and subsurface data, which is critical for understanding our geology, understanding mineralization, and economic potential of a deposit that's in the mining and exploration space. So projects that rely on drill hole sampling in the geoscience space, usually, we have a range of geoscience applications, which includes mineral exploration, groundwater investigations, geotechnical and engineering assessment, environmental site assessment. So narrowing it down to mining and exploration, we know that it supports the three core phases of mining and exploration. In exploration, target gen, identifying and prioritizing subsurface anomalies. For follow-up drilling, we have resource definition, delineating the size, shape, and the grade distribution of mineral deposits. We have grade and ore control, ensuring accurate grade estimations and efficient extraction of the ore during a mining process. So these are very important to note. These points that are important to note in sampling are that accurate reporting is critical, because in exploration and mining, projects must report reliable data to their stakeholders. And poor sampling often leads to misleading results and loss of credibility. So it's important that whatever it is that we share in the space that we're in, we share accurate data. So also to note is that errors accumulate, they do not cancel out. So whenever you do sampling, and you need to know that sampling errors are not self-correcting. They build upon each other, compounding your uncertainties and obviously risking the project lifecycle, or increasing the risk throughout your project lifecycle. And when you go back to understanding that this information, it all adds up, and it's critical for making decisions. So assay data that we get out of this sampling, it drives key decisions in mining or in technical and financial. It drives key technical and financial decisions in the mining space or in exploration. So for exploration targeting to mine planning. So if you base all that information on for exploration targeting to mine exploration are based on assay results. So we need to understand that. We need to understand that all the information that we are collecting from our samples, the assay data that we get out of that, it impacts those decisions, those technical and financial decisions that we make. On the hindsight, incorrect decisions have major consequences. You obviously understand that improper sampling can result in valuable ore being sent to waste. So, or waste being introduced back into your ore system. So this can cost us a whole lot more. You can imagine spending a whole lot of money processing material that is completely waste. Or maybe taking all the material that you mined that you thought was of economic importance, and you put it through your processing plant, and at the end of the day, you do not recover the metals that you are looking for. So this impacts highly on operational efficiencies. Why are we sampling? The key reasons why we are sampling, where do we use sampling? It's when we explore. To explore, identify targets, define targets, or just for general research purposes. For resource estimation, this information that we gather out of the sampling exercise, we use it to define resources or upgrade resources, upgrade or downgrade a resource, or we can use it to generate a reserve. Essentially, upgrading a resource leads us to getting a reserve out of it. For metallurgical test work, it's important for us to understand what components are in the ore so that we can use that information to improve metal extraction. And for mining, grade control, maintaining production efficiencies is important for reconciliation and monitoring our processes. So we use sampling for all those. How well are you sampling? I mean, this is a question that we all ask ourselves. Or when somebody has brought samples to you, that's the question you would ask: how well was this sample collected? When evaluating a sampling quality, it is essential to understand that these three concepts. If you understand the three concepts, makes it easier for you to understand evaluate a sampling process, whether it was of good quality. We need to understand the concept lot, sample, and a whole. So for this, a lot, it's an entire mass or volume of material from which a sample will be taken. This represents a source from which you estimate from, or testing a specific component. So we could be looking at something like a stockpile or just a batch of ore that you're going to estimate from. A sample is a subset of the lot, so selected for analysis. So every portion of your lot needs to have an opportunity. It needs to have an equal opportunity to be sampled or included whenever you're sampling, and in a way you're avoiding bias sampling. A sample can be a single unit or it can be a composite. So a single unit, when you're looking at drilled core, you could be looking at a 1 meter of core as a unit that you've defined to collect your samples. Or a composite, which would be a multiple units several intervals that you combine to represent a zone, an ore zone. So a whole is the total entity being investigated or represented by the collected data. So that encompasses all the relevant lots and samples. So these are some of the terminologies to keep in mind. Your component. The component would be the specific property or attribute of a lot that is being measured or estimated. An example would be, say, in a manganese, if you're looking at manganese content, the chemical concentration of that, or you're looking at physical properties like a density or porosity of your ore or your rocks. Content, it's a qualitative estimate of the component in a sample expressed as a dimensionless fraction or a percentage. So in this case, when you're looking at manganese, you could be looking at 36.5%, which would be 0.365 decimal fraction. An increment, a single portion of material collected from the whole lot. Well, you're looking at, you could be using a measuring tool. Your measure tool could be like the number of scoops that you're collecting with. A scoop shovel could be used as a unit. A drill core interval, you could use that. Multiple increments are often combined to form a composite sample, improving the representativeness of your sampling. So again, we ask ourselves, are your samples truly representative of the lot? Because if they are not, the entire interpretation that is going to come out of it may just be flawed. The primary goal of any sampling procedure is to ensure that samples are representative of the lot, meaning it reflects the accuracy of your composition, your variability, and the characteristics of your material. They need to all reflect in the sample that you've collected. And in practice, when you look at it in practice, however, samples can never be exact to the can never be exactly identical to the full lot. So hence we take a number of samples to try and mitigate for that. There are always differences in the size of your particles, in the heterogeneity of your material, and whatever method that you use to collect the samples has some level of deviation, which is inevitable. So it's important to note that that there's a little bit of a difference in every sample. The objective is to minimize the difference through careful planning, consistent technique, consistent application of whatever technique you are using to collect the sample, and appropriate sample handling, so that the results from these samples can confidently be used to infer properties of the lot, since we know that each sample is not exactly identical to the lot. So there are some errors that we need to understand, and errors consist of two key components. You're looking at systematic errors and you're looking at random errors. So with systematic errors, these are consistent deviations from the true value, and this reflects the accuracy of our sampling. Of course, by flawed sampling procedures, this is caused by flawed sampling procedures and analytical methods. So for random errors, the variability between repeated samples, that's what these errors reflect. And when you're looking at this, you're looking at repeatability and consistency of the sampling and analysis process. So what is a bad sample, we ask ourselves? A bad sample would be that is either biased, one that is imprecise, a combination of the two. When a sample is both biased and imprecise, that is a bad sample. So it's important to also again note that to achieve a high accuracy and high precision, you need to do robust sampling. You need robust sampling procedures and good quality controls and validation of whatever methods that we're using. Some errors are just not possible to remove. So sampling errors arise when samples do not accurately represent a lot, as we've highlighted. So there are fundamental sampling errors caused by the natural heterogeneity of the lot. This can be influenced by just the geological variability of your ore and particle size distribution within your ore. So inherent and unavoidable these are inherent and unavoidable, but can be minimized, and which is what we always strive for in cases like this. You try and minimize the errors as much as possible. This can be minimized through correct sampling design and using proper equipment. There are other errors, the grouping and segregation errors. So this results from non-uniform distribution of particles in a lot. Often this is caused by transportation or when you're handling your material. So whenever you moving material from one place to another, often the heavier material would settle at the bottom and the lighter material would be at the top. And sometimes when we mix or when we're storing our material, we store them improperly. So with this, bearing this in mind, this will lead to a biased sample whenever we're collecting a sample from. So these are errors to pay attention to. Sampling errors that are just not acceptable, that can be avoided, and they are really costly and risky to the decisions that we make. This incorrect, unacceptable errors are incorrect delimitation errors, the poor design of the sampling system, or a poor procedure being applied. So that can be prevented through the use of clear sampling protocols, supervision, consistently marking sample intervals, making sure that they are always correct. Incorrect extraction errors, we're looking at errors where sometimes you find a technician or whoever is collecting a sample is taking too much of a sample than desired, or too little material than desired. So this again can be prevented. We use calibrated tools, proper sample recovery techniques, and we cover up fines to avoid losses with collection systems. So incorrect preparation errors, contamination between samples, sample loss. Whenever you splitting, you need to make sure that your sample splitting process is done properly. You do not have a proper sample that is lost in the process, or you don't contaminate your samples. So this also can be avoided. Sometimes leaving your samples out open in the open, you get physical alteration, material oxidizes, and that also affects your sample. So things like that needs to be noted. Mislabeling of samples, this happens all the time whenever you have a human involved. So these are some of the things that can be avoided. Inconsistency in your splitting processes, it causes bias. So that needs to be avoided at all costs. So to prevent this, again, strict adherence to SOPs that have been designed, and proper handling of your material. Label them properly, and make sure that all the personnel involved are trained to recognize and correct these errors. So this is, again, just a diagrammatic sort of representation of what these errors are like. You can see the first block there, it's the partially segregated lot. So when you look at delimitation errors, you've got sample bias. If you decide when you're designing your sampling procedure that you are going to take samples in the regimen that is highlighted in this in the second block there, where you're taking a vertical sample and one across right at the bottom. The B sample, you're obviously collecting what has settled at the bottom, because we see from the initial sample, there's some material that settled at the bottom. So that introduces bias. So we need to avoid that at all costs. Extraction errors when collecting samples, again, we need to make sure that as designed, that is exactly what we implement. If you look at A on that block, you have A taking half a sample. So that sample has not collected material that is settled right at the bottom. So that again, it introduces errors in our sampling processes. You have B. B again, you can see one has collected some material that was not part of the material that should be designed right at the top there, and some material left behind. So that's an improper way of extracting a sample. Incorrect sampling, again, contamination. You look at foreign materials being introduced in our sampling processes. So we need to make sure that as much as possible we work in a sterile environment, or make sure that when you collect samples, you maintain cleanliness and avoid contamination. Sample losses during transfer, that also is one of the culprits in improper sampling. So we need to make sure that when we sample, material is all the material is transferred, because you could be leaving materials, or this could lead to bad evaluation at the end of the day. Alteration for chemical and physical properties of your material. As I've highlighted earlier on, leaving material open, you could have material that you could have the material continuing to react with oxygen, and you have alteration there, and that also needs to be avoided. If you look at the fifth one there on the sample collection, you look at a faulty sample. There's been a sample swap. Sample A has been taken in the place of sample B. Sample B is taken in a place of sample B. So this also will, at the end of the day, impact in an erroneous way our sampling processes. Why do we need to sample well? To ensure quality sampling is critical, because nearly every decision in mining and exploration depends on the data that we generate from this process. So poor sampling undermines confidence, introduces waste or rather it undermines the confidence, introduces waste to our resources, and it can derail the entire project. In mining operations, these are the impacts that poor sampling has. So, which is why we need to make sure that we sample well. So unnecessary ore losses. Valuable material may be misclassified and added to our waste dumps, and that's a huge loss. This impacts our revenue. Inaccurate grades lead to poor mine planning and forecasting. Increased production costs. Processing waste instead of ore also increases our production costs and at in a detrimental way. I mean, if you're processing waste, you are not going to recover anything at the end of the day. Reducing a life of mine. Incorrect resource modeling can shorten a life of a mine. So it's important that we sample well, and because the information is going to inform a lot of decisions at the end of the day. In exploration, incorrect resource estimations can result from this. Faulty financial and technical assumptions can be derived from this. Wasted investment, where exploration funds often spent based on flawed data. So we need to try and avoid this at all costs. So here's some drill hole sampling techniques that we implement. We've got core sampling, which is in diamond drilling. This recovers a continuous cylindrical core. This is best for geological understanding, structural, as Sarah had highlighted, and geotechnical analysis. So it allows, it allows precise depth correlation and detailed logging. So these are some of the sites that we've been involved in where we are collecting core samples. Another technique, it's a reverse circulation drilling. This produces rock chips instead of core. This is usually faster and more cost-effective than the core or diamond drilling. Common in exploration for preliminary grade estimation. Percussion or downhole hammer drilling uses pneumatic and hydraulic impact to break rock, typically used for hard rock. This one also has limited sampling quality. You could use auger drilling. This is typically used in shallow depth or soft soil, often used in environmental or geotechnical sampling. It can provide continuous or undisturbed samples. Rotary or open hole drilling uses a rotary bit to drill without core recovery, commonly used in water or well drilling and some geotechnical investigations. Limited geological detail can be derived from this. You have sonic drilling, uses high frequency vibrations to advance. It uses high frequency vibrations to advance casing and retrieve samples. Excellent for unconsolidated formations. Usually we use this in rock dumps or stockpiles. You can use this. Provides near continuous and undisturbed samples. So comparing some of the most popular exploration drilling techniques, the rotary blasting drilling or RC drilling and diamond drilling. So usually the rotary air blast drilling is low cost, fast, low quality, usually used from 0 to 125 meters, basically to have a quick look into your ground. This is used in bulk commodities, not everywhere. You have RC drilling, which bears reasonable costs, efficient, reliable, usually from 0 to 500 meters. In greenfields, infill resource drilling. We use it for most of the commodities, well, not suitable for narrow ore bodies. And diamond drilling at high cost, slow. Well, the reliability is very high as you recover our core. Usually you can drill from 0 to 1,800 meters. Some I've heard they can do a little bit more. Resource, green and brown fields, that's where we use it. Most commodities for geological investigations and geotechnical details, you can use this material. For metallurgical understanding as well, you can use this method. Drill hole sampling involves planning. So whenever you plan your drill hole sampling program, these are some of the items to bear in mind or note. Before drilling starts, one needs to define why and how they are going to go about it. Poor planning leads to missed data, or it escalates our costs, giving us unnecessary costs. A well-planned program saves time, money, and derives reliable data. So you need to define your objectives. Define the goal of why you conducting the drill hole sampling. If it's for exploration purposes, it could be for exploration purposes, resource estimation purposes, geotechnical analysis purposes, or environmental monitoring. You need to decide. Select appropriate drilling method that will go with this. Choose based on geology, budget. These are probably the reasons why we choose certain methods. We look at the budget, we look at the required sampling quality, or we look at the geology of the area, and then you decide on what method to use for sampling. One needs to determine the drill hole locations and the spacing at which they're going to do the drilling or collect the sampling. design a grid and a pattern. Use prior data. You could also use prior data to guide the placement of your borehole locations or drill hole locations. Establish a sampling interval. Derive a fixed length interval. Every 1 meter, you could sample at every 1 meter, or this could be guided by your lithological changes. So ensure that intervals balance both resolution and cost. Logistics and access. Consider the terrain, consider permitting, water access, and environmental impact. For example, in some areas, water is hard to come by, and diamond drilling will just not be used in cases like that, as you need water when you're drilling diamond drilling. Plan your rig mobilization properly. Safety protocols need to be in place. Support infrastructure also needs to be in place whenever you're planning your sampling program. Develop quality control plan, quality assurance and quality control plan. Include blanks, duplicates, and certified reference materials in your process. You need to also bear in mind that you need to use the correct certified reference materials and correct blanks for the area or the area that you're sampling, or the material that you are sampling. Schedule your frequency of insertion and track the performance of your performance metric. So that is also crucial. You need to plan that all in advance. Prepare a data management system. It could be digital or hard copies. So standardize your logging formats. Plan a secure storage for physical samples that you are going to keep, or even your digital data. You need to make sure that it's secured where you're going to place it or store it. Your team and your teams and training, you need to ensure that personnel understand all your procedures, understand the safety protocols, and your sampling protocols. So conduct training in advance, and conduct training and briefing sessions before you start your drilling. These are some of the other considerations that you need to have when you looking at diamond drilling and RC or percussion sampling, sample collection. You need to decide whether you're going to collect half core, quarter core, or your full core, or you're going to have composites of your samples. You need to consider your sampling length, or have run considerations when you're designing your sample length. Or are you going to collect your whole core? We've highlighted the full core there. Does your sampling honor lithology? It's important. You're sampling on lithology. Hanging wall and footwall sampling is also very crucial. You do not want to be leaving your ore in your hanging wall or your footwall, because sometimes you do have mineralization that goes beyond just your horizon. Design your minimum width that you're going to sample, and consider things like your internal waste that's in when you're looking at diamond drill core. And for RC samples, you'll have to collect an A sample, a B sample, and a bulk sample. So sample length needs to also be considered. We usually would have every meter run. When you're doing that, you also need to look at, does that honor your lithology? Do you cover all the lithological horizons that you need to cover with your RC drilling? Hanging wall and footwall sampling, it's also part of it. As in this case, you will not be able to always define where your hanging wall and your footwall is, but you need to make sure this is collected. Your internal waste is also covered within there. Also consider your pre-collar sampling. These are some of the sampling aids that we use. Your portable X-ray fluorescence and spectrometers. So when you're using this equipment, again, ensure that they are properly or they are calibrated. This will help you to ensure that you understand that your equipment is, or rather, it standardizes and make sure that your sampling runs do not have drift introduced to them. So you calibrate your equipment. A supplier should give you a certificate once you've calibrated. Use samples with known values to establish the correlation. Whenever you take your samples, you need to make sure that you often take samples of your reference material. Use standards either side of each sample run to check for drift. I've highlighted that. If you look at the diagram that's shown below, it shows the reasons why we're doing this, to avoid spending a whole lot more money sampling every part of the hole. So with this equipment, you are able to identify areas of interest, and we can then focus on those when we actually do the sampling, and that saves on cost. Here are more sampling aids, and you use that as your checkbox to say, okay, if after I've used say a radiation meter, and once in uranium, and that gives you a certain value, that then highlights areas that you need to pay attention to when you're doing your sampling. Portable XRF for measure and trace elements. Trace elements can be used as indicators for deleterious components. Measure elements can be used to identify useful trends for grade control and metallurgy or metallurgical understanding. So benefits of using some of this technological aids is that efficient sample filtering. I've highlighted before that you don't have to sample every portion of the whole. Once you've had this, it guides you in terms of where to sample. This helps in reducing costs as a result. Improved planning and forecasting. Real-time data from spectrometers supports more accurate forecasting for mining, and can also be used for ore blending decisions, optimizing production ahead of time, and enhancing overall efficiency. You can see there's an open pit mine there with spectrometer measures highlighting where the material of economic value is, and that can help in optimizing how you're going to extract this material. Samples are usually in diamond drilling. Samples are processed at a core shed, not where you are drilling, so it's usually away from the drill site. So usually at the drill site, you need to have a geologist that pays attention to some sort of sample markings and random checks that drilling is done properly, or samples are collected properly. Sampling is usually done long after the rig has moved on to another position, which in most cases then it minimizes the opportunity to go back into the hole and resample. And in any case you've collected the sample out of that, you will not be able to resample that or re-drill that at the same position. Sample widths may be adjusted to honor lithology, not usually possible with percussion methods. So that is one of the benefits of diamond drilling. Whenever you labeling your core boxes, these are some of the considerations. Your whole ID. In other places, it's over time, it's amazing to note, that IDs, the shade on core boxes. So when you're storing your boxes for a long time, sometimes there's shade and it's difficult to identify some of these holes. So when you're labeling, you need to consider that maybe have some metals that have engraved IDs, because that will stay for a long time. For later, when you want to relook at core that has been stored, it'll be easier for you to identify the core boxes that you need. Ensure box numbers are also done properly. It's useful. When core is poorly marked and completely sampled, box numbers are useful. So when you go back to a borehole, you know that a certain portion of your meters on there will guide where you are in the hole when you're looking at whatever core is left behind. Meter marks on core blocks and on core are also essential. Drilling direction marks are also important to show which direction that you are drilling. This will also be considered when you are actually sampling. You do not want to be mixing up your samples and having samples in your hanging wall and noting them as samples in your footwall. Sample split lines also, then you need to, those are important considerations to have on your core. Sample lines, if different from meter marks, or in most cases, in any case, sampling will be defined at a later stage after considering your logging processes. So that usually is different from your meter marks. So those sample marks need to be on your core. Your sample IDs need to be also noted on your core after you've split your core and sampled it. There's an image at the bottom there that shows some of these items I've just referred to. Another consideration when you sampling in diamond drilling is your sample width. Convention is usually 1 meter, but for narrow reef mining, narrow samples are usually required. So that is usually defined with consideration to your lithological units or your reef horizons. Underground mining it's expensive. So mining cut must be optimized at all times. So it's optimized for height and value usually. So cross cuts, reef drives, and stopes, all this usually have an approximate 1 meter to 3 meter in height. So when you then sampling, it's important to note where your hanging wall and your footwall dilution is, as this has to be minimized at a later stage when you are actually extracting the ore. So when you sample, you need to mark that mark the hanging wall and the footwall. 10 to 15 centimeter sample widths are common in exploration stages. Sampling intervals, we usually advise wider sampling intervals for both vertical and lateral. This provides flexibility. It helps define your broader economic envelopes. You'll make sure that you don't miss anything. If your samples have covered areas above and below your reef horizon, it helps you optimize or even understand your economic horizons better. Allow for adjustment of mining plans based on market conditions. In PGE deposits, associated base metals are usually have a different sort of peak when you or distributions compared to your PGEs. This base metals that are associated with your PGEs, they usually have distribution that are not necessarily aligned with your PGE peaks. So you need to consider that. I've included some images below to just highlight the peaks. So you can see that it's important to note both that, as that will advise when you are mining. Usually some of this have significant revenue. We usually call them byproducts when mining. So they have significant revenue, so they're important to consider when you are actually sampling. So when you're looking at your PGEs, you also consider those associated base metals. So for example, copper and nickel peaks may occur above and below your highest PGE grades, as highlighted in that image there. So we need to make sure that when you then optimizing your mining, you consider that. Sampling intervals must be representative of the mineralized zones. Bottom profile on this, if you look at it, you can see at the top, it highlights that there has been some samples. There are some samples that are missing there for the hanging wall, as compared to the image at the top that shows your profiles. They show that there's been samples above and below your reef horizon. So the bottom one there shows there are samples that are not covering the top part there, and that could also impact how you are going to mine this, and you could be leaving or above or leaving or when you're designing your mining cut. RC drilling or RC sampling, these are some of the images that highlights the processes in RC sampling. So in RC sampling, you recover rock chips from the inner tube, and this get contained this don't get contained by the wall rock. If rock type is hard to ID, chip color, bulk bags on the bulk bags is often used to define where your lithological or changes are, and this is useful markers when you are drilling when you are RC drilling or sampling in RC. That can help you define when to end your sampling process. Like diamond drilling, the sample representativity of the hole is dependent on the sampling method you're using. Hole must be oriented to best represent the hole. Vertical holes will, in this example, will generate poor sample representatives. If you were to drill vertical holes, in some areas you are going to miss your reef horizon or your ore horizons. So understanding your mineralization is key, and that helps in you designing your sampling at the end of the day. These are some of the driller errors to look out for in RC sampling. Meter marks on the rod inconsistently marked. Some drillers will find that their marking is inconsistent. I mean, that will, at the end of the day, give you samples that, samples with different lengths, and that affects your sampling, and it introduces bias in your sampling. Inattention by drillers in observing the meter marks, you find the driller that sometimes they short drill or have runs that are longer than they should be. So it's important to have an eye on the drillers at all times. Slightly over drilling the last meter of the drill rod to protect the hammer, resulting in the sample support of the last rod 1.1 meter long, while the first rod in the sequence would have been 0.1 meter. So that needs to then be noted when you're doing your sampling. You need to pay attention to that. And if the driller says, I was doing this to protect the hammer, then note those measurements in your when you're sampling. Blowing out a hole too vigorously sometimes between rods, it results in whole wall caving in. So that at the end of the day is going to also contaminate your subsequent sampling. Insufficient air pressure to lift all the primary sample up a rod during the meter advance. Those are some of the issues that you'll be faced with. Typically, insufficient air pressure results in primary sample being excessively reground or pulverized at the hammer, while sample material get lost. Obviously, if it's very pulverized, you are going to have some of this material lost. Advancing too fast through softer lithologies as well, it can affect your sampling or your sample collection at the cyclone. Not allowing time to let samples clear of the system. Sometimes drillers are just in a hurry. They will not allow that to clear, and you end up having samples being mixed up. At the end of each meter, time needs to be allowed to get the cuttings out or cuttings through. In some operations, it is allowed, or you get drillers being advised to pause between sample intervals to allow the sample to properly clear of the system before the next meter is drilled, and this is a good practice. The pause interval needs to be increased with a depth of or it may be useful to tap the hoses and sample boxes with a rubber mallet to make sure it's clear before advancing. So whenever you've collected the sample, you need to make sure that at least there's the cyclone or it's tapped to release all the samples that's within there, so you don't carry those samples over to the next sample interval. Try avoid being pushed in too fast as drillers, because sometimes they chasing the rate, but as a geologist, you need to pay attention to that. Sample quality is of importance. Some operating procedures, as I've indicated, allows 10 to 15 seconds at the end of each meter sampling. The pulling of rods from the bottom to let the hammer fire out, or to let the material come through the cyclone. Sample mass is of importance. Noting sample mass, this introduces sample preparation errors. If you have inconsistent sample mass, the primary sample mass is usually between 35 to 45 kilograms per meter drilled. So when you have that, your samples, your A and B samples are usually 2 to 4 kilograms. Some mineralization types require split samples larger than 4 kilograms, but usually samples from 2 to 4 kilograms are okay, can be acceptable at the laboratory. There are a variety of RC subsampling systems on the market, and all require a cyclone to separate the particulate sample cuttings from the high pressure air prior to subsampling. So splitters typically used in RC subsampling are commonly static cones, rotary cones, and tiered riffle splitters. This sample splitting systems may be monitored, may be mounted onto a rig, or on a separate trailer. I know recently we were involved in a RC drilling program where this was mounted on a trailer. All of the above are suitable for managing, are suitable when managed properly. A sample mass, why does it matter? Accurate and consistent sample mass is essential for the quality data and reliable interpretation. It reflects both the integrity of a sample that has been collected, and also it tells you about your sample recovery, the quality of your sample recovery. So the reason why we measure the samples and check for the masses, for sample mass, is so that we ensure the sample recovery is done correctly. Visually inspect the bulk bags for obvious discrepancies in volume or moisture, flag anomalies, and address recovery issues with the driller promptly. Don't wait for the hole to complete, but as soon as you identify that, if you're supervising a rig, you identify that there's some anomalies in sample recovery, highlight that to the driller, and the driller should correct that. Always weigh both A and B samples, primary and duplicate splits. Target mass is 3 to 5 kilograms per meter, or 2 to 4 is highlighted before, as some laboratories accept that. Sample consistency below this range may indicate under recovery or poor sampling techniques. If your splitting method is consistent, then a low weight of your sample A is likely to reflect a true low recovery. You look at the diagram below, it shows between 2 and 5 most of your sample recovery measurements are falling, and you do have some samples that would fall above and below this targeted zone, and those need to be noted. When you have a sample that is way too big, it might be that there was an overrun with the drilling, or you have sample, maybe your sample recovery process is not efficient. You have some samples that are left within your cyclone, and you're recovering them maybe with the next sample. Hence, the bulk bags become a lot heavier. Or your samples, if for this ones are your A samples, if your samples are beyond this, it might mean there are overruns in your drilling. So you need to pay attention to that. And if samples are below this as well, it means maybe there are some places where they're short sampling. Samples are collected from the cyclone. As highlighted, these are some of the examples of cyclones. These samples are collected from here, and rotary cone splitter, least room for error is the one that would be advised to really go for if you can. Manual collection and manual splitting usually introduces some human errors. So your multi-tier rifle with a cone below also has potential for smearing and contamination. So that needs to be also noted. Your RC sampling, there's an example of a cone splitter and how the sample material is collected. Your A and B samples would be where the two arrows are showing at the bottom, where it says sample and sample, and where it says waste, that's where your bulk bag goes. Yes, usually when you RC sampling, you have water intersections. It's important to note where these intersections are, as water has potential to introduce some contamination in your sampling. Because usually even in your cone, in your collection mechanism, your cyclone, you will not have samples recovered your whole sample being recovered, as some of the material might just start smearing onto the sides of the cyclone. And this, you'll have to heat the cyclone to release some of this material, or use an air hose to blow all that material out before you continue to the next sample. So short or low sample recoveries are usually attributed to water intersections. This also may be a useful marker for alteration or minerals. You must know that ensure that a hole is dry before advancing through to the next sample. So usually when water is intersected, there will be a booster, a booster compressor that is used to ensure that samples that are recovered are dry and not wet. So here if you look at these images, you have a very clean sampling processing area highlighted at the top, where this was a process. This was a sampling process at Creighton. So you can see how things are neatly placed. So that's what we are striving for, because a clean environment allows you to work efficiently, but at the same time, it helps with minimizing contamination. And if you look at on the right, there's a little video that I've just played showing a manual splitting process. Here also there is room for errors. There is room for sample being lost. You'll see as they sample, there will be some material that spills to the sides, just there. So that introduces a bit of sample loss. You want to try and avoid cases like that. And other things to also avoid, and we often see this in places where people are trying to save cost. You find a sieve that is used when collecting your chips for logging. You find that it's being patched with cable ties, and I mean that's not desirable. It has holes. You need to then use a new tool when this tool has gotten to the stage of deterioration. In production drilling, your blast holes, we usually use a downhole probe to sample, or you could use a spear on the mud pile that is generated at the top of the hole, or you can use a mud pile slot to sample the discharge from the hole, or you could collect directly from as you are drilling. You place a tool to collect directly from the dust that comes out from the discharge. That's a hole. If you look at that, and the sample, usually the cone that the mud pile that you'd have on top would represent your hole in that fashion, where your top portion would be buried within the hole, and your bench and your subdrill would be inverted. So essentially, this is inverted compared to what you have in your hole. You need to bear that in mind when you're sampling. The spear method, the sampling device must transect the lot when you are actually sampling. Again, Tanya, I don't know if everyone can see clearly on the slide with this items that Yusuf has put onto the.
No, I am trying to delete them.
Okay. So sampling device must make sure that your sampling device, when you're sampling, it transects across the entire lot to ensure that you've represented your whole correctly. Your errors can be ascribed to dust loss. Obviously, a mud pile, once it's exposed like this in a windy or where there's a lot of wind, some of the material fines will fly off. You could also even have foreign materials falling in that also introduces contamination to your mud pile. So those are things to note. You can have caving of your drill hole, particles bigger than the sampler opening or your spear opening may not be collected when you sampling here. That can introduce errors into your system. Spillages from your sampler can also introduce errors. Your mud pile segment slot, a sample should be scientific and representative. So when you're collecting that sample, ensure that all the material is correctly collected, representing the whole in its entirety. A grab sample is just not acceptable when you, as it's not representative when you're doing when you sampling, either in production or even when you're doing this in production sampling. Okay, there are some QA/QC to note. Your quality assurance is about putting systems in place to prevent errors before they occur. So developing and enforcing SOPs is crucial. Ensuring proper training and the competency of your personnel is also of importance in mitigating quality assurance issues. Quality control focuses on monitoring and evaluating the quality of data after it has been collected. So there are three main components to this: accuracy control, precision control, and contamination control. So with accuracy control, we usually use certified reference materials to check if the assay is giving us correct values. We use duplicate samples to check for precision. And this is usually duplicates that are collected from the field, or it could be ones that are collected at the lab. Contamination control, use of blanks is often it's often used to detect cross-contamination during sampling. So QA/QC includes much more than just looking at assay results. A comprehensive QA/QC program should be addressed, and the following questions must be noted. What assurance do we have that your X, Y, and Z coordinates of your drill hole is correct? I mean, all your samples will be attributed to that position. So that we need to ensure that that is correct, so that the position of your sampling data is attributed correctly. What assurance can you give that your core was logged correctly? If it is not logged correctly, you may submit a reef sample, but in fact, it is actually a sample from your hanging wall. You might be thinking I'm submitting a reef sample while you're submitting a waste sample from the hanging wall or the footwall. So what assurance can you give that correct CRM has been inserted? For instance, if you say you're using an MS089, how can you make sure that that standard or that certified reference material was inserted instead of another? How do you ensure of that? Or maybe somebody could have also put a blank, and how sure are you that it's a blank instead of it's a certified reference material instead of a blank? And that could have been placed with an incorrect label. So that also needs to be mitigated, or it needs to be prevented. CRMs and samples could have been swapped as well. So those are some of the questions that we need to ask ourselves and correct or make sure that we avoid cases like that. What assurance can you provide that material that is being used as blanks is suitable to use in the ore that you are analyzing? So once we've asked those questions, we'll be able to mitigate that in our procedures and making sure that our procedures are followed to the letter. Some of the human errors that are involved as having a sample with 2 tickets. You find somebody has erroneously placed 2 tickets in a sample. How do you know where to attribute that sample? So that needs to, those human errors need to be eliminated. A sample can be submitted without a ticket. How do we know where the sample belongs? So we need to mitigate that. Your sample could be submitted with say you're trying to submit a sample with a certain number and you find that the number has been swapped. That also, it happens. That needs to be avoided. Sometimes the recording of your data, you find that you've submitted a sample with an ID, but you've actually recorded that as a different ID. That also needs to be it needs to be noted and prevented. Assay results considered to be reliable. I mean, this is now once you check in your lab. Assay results are considered to be reliable and fit for purpose when they are precise, when they are accurate, and when they are produced in a contamination-free or contaminated-free environment. So understanding this 3 criteria, and here are their definitions. Precision, looking at the ability of a lab, this is with regard to the laboratory. The ability of a lab to reproduce a result. And usually this is checked by using duplicate samples. There will be pulp duplicates that can be assayed to check for repeatability of the samples. Accuracy, this provides an indication of how close to a known or true value of your lab can report. So CRMs usually come with a known value. So this is used then to check how close are the values that are being reported by the lab to the reference material itself. Contamination, to check for contamination, we usually use blanks. So blanks are known that they don't have any value. So that if you find that your sample then comes with some sort of results that indicates to you that there has been some sort of a cross-contamination or sample swaps. Field duplicates in RC chip that are split on site tests how repeatability they test for repeatability of your sample splitting methods. So when you split your samples, if your samples come with values that are very that are just way too different, it indicates to you that your sample splitting process might be having errors. The fields duplicate is split out from the same bulk bag. Note that your field duplicate is not collected from your A sample. You collect your field duplicate from the same the bag that came up with the very same A sample that you've collected. Pulp duplicates, these are at your lab. This they are used to test how well your lab can replicate its samples to the master pulp. Usually, a 30-gram aliquot is used for analysis, and it represents about 0.067% of your approximate 45 kg of material retained per meter. So when you have samples that are floating way outside your regression line, that indicates that your samples have been swapped. You can see on this on this chart, you have 2 or 3 samples that are floating outside that sort of area. They indicate that the samples might have been swapped. So looking at your certified reference materials, the results that come from your certified reference materials, you have out of all this 24 samples, you've got about 18 that plots within your standard deviation or your allowed sort of deviation. So that you've got 18 that passes that, and you've got about 5 samples that are just on the borderline that says, you need to start looking closely into your processes, and you've got 1 that has failed. And if you look at the image below, it shows 23 out of 24 that has passed, and only 1 warning, and that's sort of like your desirable scenario where all your results plot within first or second standard deviation. In a case like this where you have this correcting to a mean, you do not need to repeat the sampling. But if all this if your outliers then they correct to outside your mean, then you need to repeat your batch. We also have to sample for SG your specific gravity, and the reason is we use this information in mine design when you're doing your cost calculations, selecting the equipment that is going to be used for mining purposes, and understanding your metallurgy. So your specific gravity samples need to be collected, and how we usually collect them, you collect them noting the rock types that they represent. You collect some samples in your overburden to check for specific gravity, and you'd have your material, your waste material that you check for specific gravity, your rocks above and below your ore horizon, and also what you've regarded as your ore. You need to also check for specific gravity of that material. In summary, some errors are inherent and cannot be managed or mitigated. Human and equipment-induced errors can be managed, reduced, or removed. Sample errors are the compound. So you need to get it right in the beginning. Quality control can help identify sampling errors as well as analytical errors. Certain sample splitting methods are better than others. Certain drilling methods are better than others, but it all comes down to time and cost. Quick and cheap drilling and sampling sometimes means more labor costs and more hands in the pot to introduce errors. Sample the same side of your core when you're sampling, whether you're doing your core or your quarter core. You need to be consistent in how you sample. make sure that all the time you sample the same side. Weighing of your RC bags is important. Having someone else not involved in the sampling to check your sample sheets and your shipping bags before you dispatch is also of importance. So in a nutshell, those are things to note when you are looking at your drilling sampling. Are there any questions?
Thank you very much, Rams. It looks like there are a couple of questions in the chat.
The portable XRF, it can't read directly from the core, correct? You can use it on the core. It just depends again on what commodities you are looking at. It's usually a little bit more accurate when you're using it for your base metals. So that will give you a whole lot more accurate reading than maybe for your precious metals. So you can use it for just to get an indication on your core, but it will not give you like a definite answer. You still have to take your material into the lab for for assay.
There are two questions just above that.
I think there's been some. Okay. Hi, thanks for a good detailed presentation. I have 3 questions. One, how do you prevent cross-contamination in chip trays? And as a follow-up, which is the best practice in logging from the 1 meter bag or from the rifle splitter? Okay, for logging, what we typically do is we collect samples and place them on a mat, and those samples you can use them to log, and those will be collected from your bulk bag. So we collect material from the bulk bag, we sieve them, and as you collect a sample into your chip tray that you place in your chip tray for reference, you then use that other material to log. You place it on a mat so that you can refer to when you're doing your logging. And then to avoid cross-contamination, as I've highlighted, I think you need to pay attention to the collection on your cyclone. Usually that is caused by, say you'd have water. If you intersect water, you need to pay attention to that, because you'll have material getting stuck onto your cyclone, and that will then go into the next sample when it's collected. So ensure that your drillers, they either use a hose, a high pressure hose, to clean their cyclone before the next sample is collected. And also make sure that there's a robust procedure that your people are trained on, to ensure that whatever sample that they collect is collected from the right bag. For example, you find that a technician would go onto a wrong bag and collect a duplicate sample that is supposed to be for a different sample. So your SOPs and training for your guys usually is the best way to make sure that doesn't happen. And as I've said, with the cyclone, ensure that your drillers are not in any rush, and between samples, they clean the cyclone. Oh, sorry, no, I think that they're talking about. I see only 2 questions.
Yes, there were. The first section by Munawazwa, there were 3 questions in there. Otherwise, okay. It's just him and.
Oh, okay. There's one. In place where you are drilling and a hole is caving, there's consistent flushing to prevent the drill bit from getting stuck. How do you make sure that there's no cross-contamination? What happens is when a hole is caved in and they are flushing, you remove your sample bags from the cyclone, and the flushing will happen until it's completed. So once the sampling is completed, one needs to then using a pressure hose, blow the cyclone to ensure that there's no foreign materials within the cyclone before you insert your sample collection bags for continued drilling. When you're drilling through solid rock, then you retrieve small sample, and the driller says it's because of the cavity. How do you confirm that this telling the truth, as a driller never tells the truth? It's not always the case. Some drillers do tell the truth. And for them to say there has been a cavity, you can observe the penetration rate. If you're going through a hard rock and then suddenly your rods are just flushing in and your sample recovery is then low, say it's in a case where you haven't intersected any water. So that can be a telltale that you're going through some sort of a cavity. Other than that, you'll have to pull out, if you're drilling in an area that has been worked before, you can also look at the plans that exist, your historical data that might highlight to you that you are going to drill in areas with cavities. So be on the lookout for that. So I don't know if that sufficiently answered you. Yeah, I think I've addressed all those. Are there any other questions?
There's one at the very bottom.
The very bottom. How do you integrate XRF data from drill hole samples with geological logging data to improve the interpretation? Your XRF, when you collect when you're using XRF to assay, you usually use it at an interval. For example, if you're looking at, if you are in your RC, if you're doing your RC drilling, your XRF, you take readings of every meter interval. So you collect samples and place some of this, like your A sample, you use your A sample, which represent a meter of your drill hole. And that meter will also be logged on the map that we've referred to. So you can then easily then correlate the geological logging data that you've collected with your XRF data, as your XRF data will be representing the very same meter that you are logging. Yeah, I think I've answered that.
Thank you very much for your time and expertise this afternoon. We really had some very interesting presentation. Thank you very much.
Thank you, Tanya.
Okay, thank you all very much. Enjoy the rest of your afternoon. Thanks. Bye.